bill?
Let's see, the sensors themselves are what, $60 a piece, isn't that right, Whit? And then if you, depending on the options and things you buy, I think I ended up, the whole thing with 3 sensors in the box. I bought everything that you offer to go with. It was like $400 or something like that.
Now this, I'm sorely tempted to clone this interesting thing. There's so many, I live here in New Mexico, and so many things are possible here. And I have 80 acres out near the VLA. It's annoying to some people buying property in the area. It's how often property comes with a free mine shaft. I was scouting mainly for a hilltop, and I negotiating with my spouse, who's more interested in flatland for her divorce. But we compromised. But we have both a flatland and hilltop, and also a mine shaft.
Oh, nice.
It goes in about 30 feet or so, and I just feel almost morally obliged to clone your system. So I want to talk afterwards.
Yeah.
But folks who are interested in the big picture with magnetometers and space weather, I couldn't recommend more the historical book, The Sun Kings. That's a biography of Carrington, the fellow for whom the Carrington event in the 1850s is named. And he was a very interesting character, and that was a profound event. And when the next one hits, hell will surely break loose. I'll be very glad I have a mine shaft.
That's right. That's right. That's right. That's right. That's a good idea. I like that. I like that. All right. Any other questions?
Just
Go ahead.
one, thinking of the mine shaft
Yeah.
and the issues of varying temperature and rain. Does it help at all to have a roof over this sensor so that it has less variability?
Well, yeah, that's actually a good point, right? So if you had some structure that shaded that sort of immediate area, I think though, with it being down a meter, you would have to have a large shade area for it to help a lot, right?
Like inside a mine?
Yeah, inside a mine was perfect. That's ideal. I wish I had a mine shaft.
But come visit.
Yeah, there you go. And that's a good idea. I think in my case, now in some cases, sheltering it from the rain would help. In my case, it's a large flat area, and so really it's the, like I think he said, it was the water table coming up with the rain more than the hole filling with water. So which is why I said it might take a while to empty it. You know, it might be one of these things like, okay, that's empty enough, we'll get the thing in there and seal it before the water comes back up. Yeah, go ahead, Russ.
If you were to obtain a large diameter PVC pipe with a cap on the lower end as a sleeve, lower that down into your pit of despair, and it would be a permanent liner, then where you could just set your sensor box down in.
Yeah, I considered variations on that theme, but the problem I worried about was thermal siphoning from the bottom to the top. If you didn't fill it, I think you'd still have to fill the inside of the PVC with something.
Yeah, but it would be dry.
But it would be dry, so you could fill it,
Yeah, you could fill it with your builder's sand.
Yeah.
Or fiberglass.
Yeah, or something, foam,
Yeah.
could be foam, fiberglass.
But then that would be a permanent seal around your sensor box.
Yeah, that's a good idea, really. I may consider that. Yeah, go ahead.
Sorry, I was a little late to your opening. Could you tell me what was your data acquisition device and the program that you used to import the data into?
That comes with the SAM3. I don't have a picture of that, Whit, but anyhow, it's a small, sort of a console type box where they have this sort of sloping thing for a keypad and a display. The footprint's about like so. It has a couple of circuit boards in it, and it does, it takes the incoming digital signals, measures the frequencies, converts it to nanotesla, and does a bunch of other things, real-time clock and that. And then there's a serial link to a computer and software that comes with it, the system that you run on your computer, which basically, that's where this plot comes from, is from the SAM software. That works pretty well. You can scale this, and it archives the data to the hard drive, and all those things you sort of expect. It does that pretty well.
Is there an organization that wants this data, that you can give it to,
You know, I wish, there isn't really. There's an online user group, but there's nobody gathering and archiving data from other places that I know of yet. That would be nice. I think that would be a cool next step if we get enough people, would be to have a server somewhere where we can store this data. Because the data is not very large. The data files aren't very big, right? Because the sample rate's not real high. So, you know, it would be feasible to have, I have a Dropbox Pro account or something. I think you could actually do something like that.
Just like your SuperSIDs.
Yeah, SuperSID, luckily Stanford is providing the servers for that. But yeah, it would be great to have some facility like that. Great. Yeah, back there.
So in the interest of being an amateur, and
Yeah.
not having a single clue what I was doing, about 8 years ago, I bought a piece of steel iron to the best iron I could buy. It's 2 inches in diameter, 24 inches long, and I wrapped around that in a 1-foot section about 8,000 feet of 20 gauge wire.
Oh, yeah.
And my idea was not understanding or not knowing, but just wanting to do something to try and measure something with the magnetic field. I'm not trying to say anything about your presentation. But
No.
sometimes an amateur's mind can really go wild trying to figure out how am I going to do this.
Yeah.
It really didn't work that well, but it makes a nice magnet.
Right. So that sounds like, if I have to think about some of the frequency response issues, but it seems like you would at least get the transients. The good thing about these magnetometers is that they do measure the DC field. So it's, once you remove the temperature coefficient and the power supply coefficient, then you end up with DC.
What are the devices made for?
For this, really, I mean, there's a lot of applications for a magnetometer. But yeah, basically for doing this kind of thing. Yeah. When they drink.
Well, weren't they originally, I saw an article in the magazines, weren't they made for driveway detectors too?
Right, so you can do things like that.
Yeah.
So find out when the car drives up to your area.
Yeah, you don't need a really carefully calibrated magnetometer for that. I think that's just sort of an art. That just sort of falls out of the that they were acting. All right, well, great, thank you. If, pin me up against by the coffee machine and if you've got any other questions. Okay, who's next? Is that you, Whit?
Yep.
Is your laser pointer working?
Yep. Yeah, I got it all working.
Got it?
Good.
Okay, okay.
I think it'd be yeah, we're kind of interested in magnetometers.
Being a separator, they're no good at it.
Well, all of a sudden, I will never forget one day we had a very rare school, and our commodore was conducting it. Somebody said, well, how do you guys report this? Okay, well, let's let's get back to work.
Oh, come on. Jeez. All right, let me sneak around.
I'm Whit Reeve. I'm a contributing editor in the for the Sarah Journal. Been a member of Sarah for almost 10 years. I think since 2007, 2008 time frame. And when I actually worked for a living, I owned a telecommunications engineering firm. So my presentation for today is receiver stability analysis. And we're not talking frequency stability, we're talking output data stability. And my clicker was working earlier, but not anymore, so let's do this manually. What I'm going to talk about then is just some stability concepts, instrumentation, and then measurements. And I've made quite a few measurements on different types of receivers that are popular for Sarah members. And so what I'm going to do for the concept section is I'm going to derive these equations for you from first principles. We're going all the way back to the Big Bang and working our way to these equations. I'm just kidding. So some of the key concepts are we're going to be working with total power receivers, and that's just a kind of a fancy name for just a regular receiver in the way we use them. It's a receiver that measures the power of the incoming signal within its bandwidth and over some integration time. So you're going to average the data somehow with an output filter. And so we're looking at total power receivers where the idea is that we want to average our output data to improve the sensitivity of the receiver. And I'll talk about that in a minute. One of the key concepts here is that the receiver noise, the noise generated by the receiver itself, is assumed to be a white FM noise or a Gaussian noise. And there's lots of other names for this, pure noise, but really what it is, it's a type of noise that its amplitude averages out to 0. And one of the other concepts that I'm going to be spending a little bit of time on is this Allen deviation. We're not using, in normal statistical analysis, we'll use the standard deviation to determine the average of some data quantity. But it turns out that we want to use the Allen deviation, which is slightly different than that. So I'll be explaining that as we move through this. So total power receivers, most of us use total power receivers because they're cheap, they're relatively simple. Another name for them is radiometer. And again, that's just a fancy name for the types of receivers that we use. And it measures the average noise power received within the bandwidth and integration time of that receiver. And the stability then determines how long its output may be averaged to increase the sensitivity. So what we're trying to do is we're going to average the receiver output, which is white FM or Gaussian noise, and that's going to reduce its amplitude. And now when we have the signal coming in from a celestial radio source, it's going to increase the noise above this minuscule receiver noise. And we've made that receiver noise minuscule by averaging it. Here's an example of a total power receiver, and I'm using a software-defined radio as an example. And if you have any kind of a halfway decent SDR receiver, it's going to have some type of pre-selector and RF amplifier. And by pre-selector, I mean it's got input filtering. And then we've got an RF sampling analog to digital converter. And typically, if you're working with any kind of higher frequencies or higher bandwidths especially, you're going to have a digital down converter to reduce the data rate down to something that you can use in your digital signal processing software. And this part runs on your PC, and this part is the receiver itself. A couple key attributes to a total power receiver are the noise bandwidth, and this is a pre-detection noise bandwidth. and the output time constant, and this is a post-detection time constant. So those are two key parts of our digital signal processing, and we're going to be taking a look at this part especially in this presentation. So the celestial emissions that we're trying to receive are almost indistinguishable from the receiver noise itself. So the idea is to reduce the receiver noise so that these tiny little celestial radio emissions that we're trying to receive will cause an increase, a bump in the night, as it was called yesterday. And so we're going to average the data output to increase its sensitivity. So data averaging is a key concept here. The assumption is that the receiver output noise is a Gaussian or close to Gaussian type noise, or white FM noise, and that actually turns out to be a pretty good assumption, and I'll show you that in my measurements that I'm going to go through later. So white FM noise in the frequency domain looks like noise. In the time domain, looks like noise. Noise from the ground, and also we have noise added by the receiver system, and this is the one that we want to reduce by averaging. And receiver output stability is to the extent that the receiver electronics are halfway decent, the power supply is halfway decent, and the environment is halfway decent. In other words, by environment I mean temperature and humidity and things like that. One of the problems that we encounter when we're trying to average output data is that the ordinary standard deviation can't be used because what happens when you start going and using long averaging times, the standard deviation starts falling apart. So instead we use the Allen deviation, ADEV, and it turns out that ADEV and standard deviation are the same if the noise is white FM. You probably recognize this as the ideal radiometer equation. We have some type of a variation here, a fluctuation or a deviation in our signal, and it's equal to, or approximately equal to, the temperature of the system, the noise temperature of the system, divided by the bandwidth times the integration time of the output, post-detection output. And so if we just forget about the system noise temperature, we find that these fluctuations are proportional to the bandwidth, 1 over the bandwidth times the integration time, or averaging time. So we can reduce those fluctuations by either increasing the bandwidth or increasing the averaging time, or both. Well, it turns out for maybe any given measurement, we're going to have a fixed bandwidth. So that kind of drops out of the equation, and now we're going to only be worrying about averaging the output data. And by averaging, what we can do is we can either put a low-pass filter on the receiver output and just increase the time constant of that output filter, or we can sample that data and then just average those samples. And so effectively, that's what we're doing here, is we can equivalently average a block of n samples of output data. And all the measurements I did were according to that. Now, if we take that ideal radiometer equation shown previously and plot it on a log-log graph, we get a straight line, and its slope is -1/2. And that's a given. And so if we have any white noise on our receiver output, as we average, what happens is that the fluctuations decrease the more we average. And so that's the ideal case. But the trouble is that there's always non-Gaussian noise present in the receiver output. And it may not dominate at first for low averaging times, but for long averaging times, it may start to dominate, and now we don't have a white noise output. So what happens if we take actual data and plot it? At first, everything follows the radiometer equation quite well. But then all of a sudden, when this non-Gaussian or non-white FM noise starts to dominate, it starts to take off in another direction. So ideally, if the receiver output was white FM noise, no matter what the averaging time, this would extend down here and keep on going down as far as it can go. But what happens in a real receiver is that we have this knee where we can't average anymore. So in this particular, this was an AirSpy receiver here that I did this measurement on. And you can see that the AirSpy does pretty well until we get out to about 1,000 seconds. So we can average a little bit over 15 minutes of data from the AirSpy, and to reduce its fluctuations so that the incoming signal from the antenna, then if it goes bump in the night, we're going to see that. So the Allen deviation is shown here, and there's not a lot I can say about that except that it's different than the standard deviation. But when white FM noise is involved, these both give the same results. A guy named David Allen is the one who actually developed this concept, and he built, like most things, he built it on the work of a lot of other people. And it was done in his work was done originally in the mid-1960s, so this is not a new concept. And it was originally, he originally invented this for measurement of extremely stable and accurate clocks and oscillators. He worked at National Bureau of Standards, which is now NIST, and they, one of the things they do is time, and time and frequency, and so his work was centered on that. And that's where I got introduced to this maybe 20 years ago when I actually worked for a living. Now, as far as instrumentation goes, we're going to look at quite a few different receivers, and the measurement setup was pretty much the same for all of them. You can see that we have a noise source. I put in a low-pass filter to keep from overloading the receiver input, and then I connected up various receivers to my PC with the appropriate software and ran them. Now, the reason I used a noise source is that I wanted to put the receiver in a condition where it was actually all the active components were activated to simulate an actual signal. And I use 46, roughly 43 to 50,000 Kelvin noise temperature, because that is the galactic background temperature at about 20 megahertz. And all of these measurements were done down in the HF range. And originally, this whole idea for this project came up because I worked quite a bit with the Radio Jove project, and we have a spectrograph user group. And that one of the things that's coming up is this total eclipse in August of 2017. And at first we were going to be looking at the galactic background and making measurements of that during the eclipse. And we wanted to be able to average our data to improve the receiver sensitivity. And so I thought, well, why not do this on a couple of the popular receivers, the Radio Jove receiver. I think there's one sitting on the table over here, and the FSX series spectrometers that we use in the SUG. I extended it way beyond those two simple receivers, though. I'm gonna have to get a glass of water here. So what I did is I terminated the receiver RF input with a stable noise source. I used 40 to 50,000 Kelvin because that's the galactic background at 20 megahertz roughly. And so this was meant to mimic an actual operating condition for these receivers at around 20 megahertz. And then I sampled the receiver output for at least 24 hours. And when you're doing these kinds of measurements, the longer you take data, the better. And so I chose 24 hours as kind of a compromise between my patience and the data file size. Now these data, the file sizes ended up being about well over a gigabit each. And when you try to import that into like an Excel spreadsheet for analysis, the program runs out of steam in quite a hurry. And then the last step is to compute and plot the Allen deviation. And there's software to do that. So now it's working. So basically here's the setup. We have a receiver, a PC, some software, and the noise source, shown in this chain right here. And here's a picture of the AirSpy with the SpyVerter up converter input. Here's my noise source. Here's that input filter. It corresponds to that block there. And then the SpyVerter are these two little black boxes here connected to that PC in the background.
What was your source for the noise source? Is it something?
This particular noise source here is inside that box is called a Hot One, HOT1 noise source that Dick Flagg makes. Dick Flagg is a member, is one of the principals of the Radio Jove project, and so he manufactures these. And then what I did is I put it in a box with an attenuator so I could adjust the actual. It's his noise source. The Hot One is a fixed output. And so I put that attenuator then to adjust the noise temperature to whatever I needed. And there's an article in the Sarah Journal probably a couple of years ago now, maybe 2014, where I wrote up all that work there. So that's the digital setup for a digital receiver, a software-defined radio receiver. And then I also did some measurements on some analog receivers, the R75, the Radio Jove receiver. The ICOM R75 is actually a really, really good receiver for the Radio Jove type stuff and anything up to about 60 megahertz. It's a high performance receiver, actually. But you can see that with the analog receivers, there's another block in the diagram here, and that is that the narrowband receivers, the output of those is going to be some audio frequency output, an audio output. And in order to digitize that, then I have to put that into a sound card. And I ran a whole bunch of tests on internal sound cards in the PCs that I had. and I had 4 PCs. And I also ran some tests with some external sound cards as well, with a USB interface. And I probably spent 10 times more trying to get good measurements out of the analog setup compared to the digital setup. So here's a list. I think I might have a picture here. Here's the receivers that I measured. The SDR Play RSP1. This is the early version in that kind of a funky blue box with an F connector on it, which I replaced with an SMA connector for RF input. The AirSpy, those two are relatively inexpensive. We're talking a couple $100 for those 2 receivers. I also have the RF Space Cloud IQ and Net SDRs, and those are a step up in price in the no, more than that, probably $600-700 range. The FXX5 is a custom device built by Dick Flagg as part of the Spectrograph users group. And so I measured the one that I have, the R75, and then you recognize the Radio Jove receiver itself. Sound cards and data loggers apply only to the analog receiver measurements. And I had a whole bunch of these Lenovo A61Es. These were manufactured, I think, about 2008, 2009 time frame. And I've had a bunch of them since then. I also used a Lenovo Tiny Think Center. This is a Windows 10, a brand new Windows 10 computer. So I worked with those internal sound cards there, and then I also used a StarTech USB sound card and an extremely cheap sound card I bought from eBay, which is probably not that much different from the StarTech unit. You know, these things are less than $10, and I wasn't expecting much from them, and I'll show you that I was right. I also used a data logger, and I used a data logger because the Radio SkyPipe program that I used for the data collection is compatible with the LabJacks, and so I used that as the analog to digital converter on some of my measurements. And it performed actually much better than the sound cards did. The software involved here, there's kind of a modest laundry list of stuff. The Radio Sky Spectrograph application software, which is free, that's a Jim Sky production. Radio SkyPipe application, which there's a free and a paid version of that, also by Jim Sky. Used SDR Sharp with the Radio Sky Spectrograph plug-in, and that's used with the AirSpy receiver. There's another custom piece of software that's free called SDR Play to RSS, and it's a tool that works with Jim Sky's Radio Sky Spectrograph. That works with that RSP1. I used Microsoft Excel, and I had to use a later version of that, I think the 2013 version, something like that. No, I'm sorry, a 2016 version, because I had so many lines of data that I couldn't import them into any other version of Excel. I had to use a text editor. In my case, I like Notepad++ because it formats everything for you automatically. And then Alivar is the Allen deviation software that actually does the computation. So you collect the data using these guys up here. You post-process the data a little bit with Microsoft Excel and maybe a text editor if you have to, and then you just import this into Alivar, and then it produces the nice graphs for you. So it does really all the hard work. There's no brain work hardly involved here at all. So here's a typical piece of the software that I used, the Radio Sky Spectrograph. If you've ever used Jim Sky's spectrograph, you've seen this before. And what it does is it's kind of the back end of the back end. The front end of the back end is going to be SDR Sharp or SDR Play to RSS, depending on the receiver that you're using. The SDR Sharp, in order to be used with the AirSpy and Radio Sky spectrograph, has to have the RSS plug-in. And this is was written by some guy that was really interested in doing these kinds of integrations, and he published it on his website, but then disappeared. So I happened to have saved a copy of it, and so I was able to do all this production. The SDR Play to RSS was written by a guy named Nathan Town, and he wrote this to interface the RSP, the SDR Play RSP1, with the Radio Sky spectrograph software. So this is the front end of the back end. And again, the Radio Sky spectrograph is the back end of the back end. And it's got a real nice block diagram here. Here's coming in from your antenna into the RSP1, and you can adjust the gain of the input. You can adjust the center frequency, the sampling rate, the bandwidth, and the frame size of the fast Fourier transform that's done by his program, and then it just streams this data out to our to Radio Sky spectrograph, which then gives you the display that you're looking at. Radio Sky Pipe, I don't know of anybody that doesn't use Radio Sky Pipe. It's primarily used with analog receivers because it interfaces to a sound card. And so that's what I use with the R75 and the Radio Jove analog receivers. Microsoft Excel, probably everybody that's got a PC with Microsoft Office on it has used Excel. And it turns out that my data files had well over 1 million lines. And I didn't realize it, but you can't, even though Excel can load a file with over 1 million lines in it, it can't process 1 million lines at a time. So that was one of the things that kind of surprised me, but it didn't cause me any problems. Notepad++, sometimes I had to, when I got data in Microsoft Excel, I would have bins or frequency channels that the fast Fourier transform had derived from the data or from the receiver. And so I would pick one of the frequencies, like this is 21.19 megahertz right here. I would take that column of data and copy it from Excel into Notepad, because it just happened for me to work that way easily. And then I could save this file as a .dat file. It's actually just simple ASCII text, but I gave it an extension of .dat, and then that allowed me to just drag it over and drop it right into Alivar, which is this program here. And again, this is a free program. So all that software is pretty much free. You just have to pay for the hardware to make these measurements. So the Alivar gives you plots of the data values, so you can look at the data, and this looks like pretty good random noise here, which is what I was kind of expecting. It also gives you power spectral density plot, and for our purposes, the Allen deviation plot. So my protocol was pretty much the same for all of the receivers. Set the noise source. I actually used 2 different noise sources, and collect data for at least 24 hours. Sometimes I went to 72 hours or more. I set that up for timed observation, so basically I'd get everything arranged and set up, and then I would, in the software, I would set up a timed observation to start, let's say at 1600, and then end the next day at 1600. And so I just hit go, and then I'd go off and do something else. And I actually had 4 PCs running 24/7 for about 2.5 months, gathering this data. And a lot of it I had to repeat, especially for the analog receivers. So the protocol was pretty simple, and it was a no-brainer. I didn't really have to think about doing it. I just did it. Some things that you need to, that I did have to think about beforehand, though, is the sampling rate. And I chose to use a 100 millisecond sampling rate on all of the receiver, on the output data. So the receiver output is coming into the software at whatever is determined by the streaming rate. And what I'm just doing is taking a snapshot every 100 milliseconds of that data. And then I'm, because the assumption is that it's random noise, then I can average that out later. Receiver bandwidth and gain. The software-defined radio receivers are really sensitive, quite sensitive to bandwidth and gain settings, especially the gain settings. The SDR Play and the AirSpy receivers both, they fall apart. If you don't have the gain setting correctly, they fall apart pretty fast.
Did you have to account at all for, in any of this, for the difference between some of those SDR devices being 8-bit and some being 12-bit?
No, I didn't account for that at all.
Because that does have an effect on the signal-to-noise ratio.
Yeah, and I think that all the receivers I had were either 10 or 12, but no, I didn't. Remember, we're not looking at signal-to-noise ratio. We're looking at noise only,
right,
in this case.
Right.
So I used 100 milliseconds wherever I could, but because of some of the other limitations in the software, like the FSX5, the way that interacts with the software, I ended up having to use some kind of odd numbers here. With the RF space receivers, I couldn't get the software to sample at 100 milliseconds reliably. Even though it'll go down, and I think the drop down allows you to go down to maybe 10 milliseconds. I found that I had to use a half a second and 1 second for the RF space receivers, the Cloud IQ Net SDR. And with the timed or scheduled observations, no intervention is needed, so I could just go and then go to the next PC and get it set up and so on. So had all the receivers, I had 2 noise sources, so I could run a lot of things for simultaneously. So now let's take a look at some of the actual measurements. And again, here's the list of the receivers that I did. These are fairly common receivers, I think. The analog receivers are pretty common as well, and then the sound cards and the data logger. And I used some abbreviations here. Tau is the averaging interval, CF is center frequency, BW is bandwidth, FFT channel width, that's with the channel that's used in the ADEV calculations, and then my actual noise temperatures, which were determined by the attenuator settings on my noise sources, worked out to be these 2 values here, which for practical purposes, there's no real difference between those. Here's the SDR Play RSP, and this is the RSP1 model. I think Ken had the RSP2 up here as well, but this is kind of a funky receiver, but it actually works quite well. And I found that I could get good averaging out to the knee, and this varied from around 400 to 1,000 seconds. Now, 1,000 seconds is about 15 minutes, so you can scale that. All my measurements were done in seconds, so you can scale that to whatever whatever you need. I encountered things like this where it wasn't a perfectly straight line with a perfect slope of -1/2, but still averaging continued on down to this point here to about 900 seconds, 15 minutes, and then took off from there. So what this means is that for fairly short averaging times, less than say 15 minutes or so, the receiver output is pretty close to white FM noise. And you can average the receiver noise out of the measurement. But beyond that, other noise types start to take over. Flicker noise, 1/f noise, and there's all kinds of different categories of noise. Those start to take over in the future there a little bit. Now the AirSpy, all my measurements I made in conjunction with the SpyVerter, because the minimum frequency of the AirSpy is 24 megahertz, and I wanted to actually measure 20 megahertz, so I used the up converter to get down to 20 megahertz. And I used a center frequency of 20 megahertz. The bandwidth was 10 megahertz. I used that in all my measurements, and that gave a channel width of 50 kilohertz. So these measurements here are based on an individual frequency bin that pops out of the fast Fourier transform when you're processing the data. And you can see that the AirSpy, in conjunction with the SpyVerter, has almost a perfectly straight line with a slope of -1/2. So it's, in other words, it's really close to ideal, all the way down to 200,000 seconds. And that's actually quite good. I don't know what 200,000 seconds works out to be, but it's probably in the 10 to 12 hours. Who can do that in their head?
2.5 days maybe?
Is that 2.5 days? So yeah, but not all the measurements were that good. So there's other things that come into play here when you're making these measurements. Things like maybe temperature. A lot of the digital receivers were done in my lab, and the temperature there is maintained within, I don't know, within 1/4 of a degree or 1/2 degree Celsius. So it's actually really stable there. But there's other things, power supply, maybe somebody walked by or something like that. So the AirSpy actually is a pretty good performing receiver as a radiometer.
What's the sensitivity mode gain differences? One's 18 and one's 10.
Oh, yeah. When you have to use the SDR Sharp software, and it gives you the ability to adjust the gain of the receiver. And so I've never been able to determine if that's a gain of 18 dB or it's just some relative number, 0 to 20 or 0 to 100 or something like that. So, and they have the AirSpy or SDR Sharp software also has a couple different gain modes. It has a sensitivity mode, a linearity mode, and a free mode where you can play with the individual components in the radio. And both of these were made in sensitivity mode, and with the gain setting of 18, that would be kind of a modestly high gain, and the gain of 10 would be a lower gain. And so I can't really explain why the measurements would be different for the two gain modes, but probably because the receiver generates different kinds of noise with different gain settings.
I may have missed it, but how were you adjusting tau?
All I'm doing is sampling every 100 milliseconds, and then I take those samples, and I might take 10 samples, 100 milliseconds, average those together to come up with a number, and then another 10 samples and another 10 samples.
You're doing that in Excel to get those averages?
No, the Alivar does that.
Alivar does that. Okay.
Yeah, so this, if you look at this graph here, you see 0.1, okay, that's 100 milliseconds, right? So that's where the data starts at 100 milliseconds. And then Elevar does all of the averaging. And here we've got 1 second, so we've averaged.
That's why you need Elevar, because otherwise you'd be.
Yeah. You can do this manually, and I have done it in a Excel spreadsheet, but it sure makes it easy just to drag and drop and bang, out comes a nice plot.
So basically, you just did one super long collection. And then
You get one super long collection of data and then drop it into Elevar, and then it does the averaging for you. And this Elevar, or the Allen deviation, there's actually quite a few different variations of that calculation. And the one I use is what's called the overlapped ADEV. And what that means is that the data, when it's averaged, you'll take a block of, say, let's say 10 samples. We take 10 samples and determine the average of that, and then we move one sample, take another 10, average that, and so these are overlapping. And it turns out that for a lot of the kinds of things that in the time and frequency arena, and also apparently here, is that the overlap calculation gives you the best results. So, and Elevar can be set up to do overlapped and then several other types of deviations.
I think that that gain setting may be in dB, because if you use the for example the Osmocom source block in GNU radio, that it represents that gain as dB for well, a number of devices. But
Okay, yeah, that's good to know. Yeah, dB are extremely easy to work with, and so here apparently in a higher gain setting, that receiver performs better than at a lower gain setting, according to this chart here. Now, one of the problems in the AirSpy and all SDRs is that you crank up the gain too high, and then you start getting all kinds of artifacts, aliasing and things like that. So there's a danger in taking this, a plot like this, saying, okay, yeah, I'm going to always operate at a gain of 18 dB. Okay, so that's the AirSpy with the SpyVerter. I also made some measurements of the AirSpy by itself at a higher frequency, and I got comparable results. So it looks like the SpyVerter doesn't degrade the receiver in any way. And of course, if you were really thinking about this, you'd say, well, what about that noise source? Aren't we measuring the stability of that noise source here? Well, yeah, we are. So I was quite worried about that at first, but I made measurements of the receivers with and without the noise source, and I was getting pretty comparable numbers. So I figured, okay, well, the noise sources aren't making it any worse. So Dick Flegg did a good job on my noise sources. The RF Space Cloud IQ, it surprised me. They didn't. The Cloud IQ didn't perform as better as those cheaper models. But of course, this is a higher performance overall radio than AirSpy. But you can see that it's pretty much an ideal plot down to in the neighborhood of 15 minutes. So that's comparable to the AirSpy there. I also made some plots that, or ran some data that were down to about 600 seconds of averaging before I hit the knee. And then I also saw things like this, where it would be ideal down to about 1,000 seconds, and then it would jump back up and then taper off again. Now, one of the things that I think causes this, and because I started looking at the error bars here, I noticed that the error bars got much larger at the end of the averaging. And that's because when you're doing averaging, overlapped averaging, at some point you run out of data. And so the potential error then gets much larger. So this hump here may be an artifact of that type of averaging. Okay, so that's the Cloud IQ. The net SDR was roughly the same. In some cases, it was worse. Here's a plot here where it looks like we hit a knee at about, maybe 200 or 300 seconds. That's not quite as good as the Cloud IQ. This is the net SDR is kind of the generation before the Cloud IQ. So it's a slightly older receiver than the Cloud IQ. And I mentioned already, though, that I couldn't get the output data sampling interval faster than a half a second or 1 second. I would have liked to have gotten down to 100 milliseconds, but the software just wouldn't handle it. Or maybe it was the PC. And the software used with RF Space in both cases is the SpectraView on the Cloud IQ and SpectraView on the NetSDR. And that's the software that comes with the radio. And I think there's other software out there that you can use with the RF Space receivers, but I haven't had very good luck with them. So I always stick with SpectraView when I need to do something. And you can see the bump at the end of the data here. I don't have error bars here, but on this plot, but you can see that it looks like it's kind of dropping off at the end, and I don't believe that is really what's happening. It's because of we're just running out of data. The RF Associates FSX5, that's designed by Dick Flagg, and we use that in the Spectrograph users group. And it's a kind of a modular receiver. Each component, like the RF amplifier, is built into an aluminum box. The filters are built into individual aluminum boxes. The detector is its own individual aluminum box. So everything is really well shielded with this receiver, and it really does work well. And you can see that we have an ideal plot all the way down to in the neighborhood of about 5,000 seconds or so. That's really actually quite good. And what I've shown here is a plot on the right-hand side. I've shown a plot of the receiver Allen deviation with a 46,000 Kelvin noise source on its input, and also with just a 50 ohm termination on the input. And of course, the 50 ohm termination's at room temperature, so about 290 Kelvin. And you can see that there's no difference between the two until we get out at the end here. So I just did that for fun. The R75, now I was expecting these radios to perform very well, and the problem is that these measurements are determined by the sound card that's used with it. So the receiver may be of really high performance, but the sound card, if it's a piece of junk, then you're going to get junk data. And so you can see, though, that in this plot, I was getting down to in the neighborhood of maybe 1,000, 2,000 seconds. But I've got other plots where it was down at 100 seconds, so not nearly as good. So quite a bit of variation. And I don't think it's the receiver's fault for those variations. I think it's the sound cards. The Radio Jove receiver performed pretty good down to around 1,000 seconds. I actually ran it with a lab jack and got down to, it looks like maybe 20,000 seconds or so. So that's an analog receiver, and really inexpensive, easy to build, real simple. It's a direct conversion receiver, and actually performs pretty well. But again, it's dependent on the sound card. Now here's some sound card measurements. The internal sound cards were all done on this A61E. There's a kind of a small desktop, and so this is just a sound card by itself. Nothing hooked up to it except a 4,700 ohm resistor on the input to terminate the input. And actually saw some fairly decent data. This gray line here is the ideal radiometer equation. So the data looked pretty good for the internal sound cards, but the external sound cards were basically useless for this purpose. And I can't explain why that is, but the StarTech is actually not cheap. I mean, it's like a $50 unit, maybe $40. This is maybe a $7 unit, but they're roughly the same. You can't do any data averaging at all with those sound cards. Now the LabJack, different story. It's ideal all the way down to well over 1,000 seconds. So the LabJack, and what this is telling me is that if I'm going to do any kind of data collection from a celestial radio source using an analog receiver, I don't want to use a USB sound card. What I want to use is something like the LabJack, which is just an A to D data collection device.
How much do they cost?
The LabJacks are about $100. So it's not going to break the bank, but they're not free. So the conclusions then are we can use Allen deviation for stability analysis just like they do in the time and frequency world. The measurement setups are quite simple. The software is free, that's always good. The SDRs perform generally pretty good, pretty well. The analog receivers, like I said, I spent 10 times as much effort trying to get some decent measurements out of my analog receivers, and it was because the sound cards were the problem. And possibly limitations in the software. And by limitations in software, I use Radio SkyPipe for all of the analog measurements. And one of the problems that SkyPipe has is that, at least the problems that I've seen with it, is that you'll be going along, it'll be collecting data every 100 milliseconds, and then all of a sudden it'll skip or freeze. And meanwhile, it's not collecting any data at all for up to 30 seconds. Usually maybe a second or two, up to 30 seconds, and then it starts up again. And that's because some process in the PC is taken over, and the Radio SkyPipe is of lower priority apparently. Now there's ways maybe to get around that. I didn't explore that at all.
Have you talked to Jim about that at all, or is it?
Yeah, I have over the years because it's been a problem since day one, and that's why he's got in his options you can set the priority for CPU usage. I think he has 4 levels of priority, and I ran mine at normal. And so it would be worth, if you're going to do these kinds of measurements, it'd be worth looking at the other priority settings for the software. Measurements should be made using actual operating conditions. So in other words, if you're going to be doing these kinds of measurements, you want to get everything set up as if you were going to be actually collecting data from your antenna. And then make your measurements, because now you're operating your receiver in its actual operating condition. And all you have to do is hook it up to the antenna, and now you know that the data you get, if you're going to be averaging it, you've got some measurements that are going to work for you.
One of the things that we found too is trying to use any type of external sound card for Radio SkyPipe or with SID, Radio Jove or SID, not worth it. Also, don't try to do it with laptops because again, you get into too much variability. Another thing that we found, and talking with Jim, Radio Jove does not like the high sample rate sound cards. For SID, particularly if you're trying to use the US low frequency stations, you gotta have it. Radio Jove does not like it. We've had really good luck with the fairly inexpensive internal sound cards. We use Micro Center just because that's real close to where our lab that the high school has given us a classroom to use.
Yeah, and I agree with that. If you have a PC where you can actually plug in an internal sound card into it, then and you can get a high performance one, you're probably better off. All PCs come with some internal device which may not, especially in laptops, may not be suitable for you. And it sounds like your experience with the USB sound card is pretty much the same as mine.
Yeah, and not only that, we've started getting some computers through surplus, through NCAR and UCAR. Believe it or not all computers come with sound cards, and not all of the computers that have sound cards, sometimes the sound cards either, because we're getting them surplus, they either don't function or they're so rudimentary that they won't work for Jove.
Yeah.
Which we
I
found
believe it.
very surprising.
One more question.
One more?
Whit, thank you for the presentation. I'm surprised that you didn't include the RTL, STR, stick dongles. They're so common, and people are using them for long observations and pulsar work.
Yeah, and if you look at the number of receivers that I did, that would have just added to my workload. So no, I didn't want to mess with them. I don't use them. These I do use, all of these receivers I do use, but I don't use the RTLs. I guess they're too cheap for me. Okay, so that's it then. Thanks for your questions.
Can you take it offline?
Yeah, let David, we'll do it offline. So.
Okay.
Thank you.
What I wanted to make a comment about, please eat the food because we're getting ready to bring in lunch pretty soon. So we were supposed to have a half an hour of break, but we lost 15 minutes, so we can meet back at 11 so we can stay on schedule. Yes, eat
Sorry, but thank you. That was.
No problem at all. It's a typical David Fields. Say one more question, but he always.
And it's like I'm not going to let him get that. It's a great talk.
Nathan Town.
Oh, Greg too.
Oh, Nathan. Okay, great.
He's a great talk.
I didn't know you were coming here.
I work here. Personally, I don't.
Oh, you do.
We just started 4 or 5 months ago. Because that's what he did. So very easy. My office is downstairs. So.
Oh, cool. That's cool. Hey, thanks a lot for coming up here. I didn't know you were here. Great software.
Yeah. Thanks. I'm Skip. Yeah. You know those really poor flat was there something wrong with the spectrum? In other words, maybe there was some noise.
Okay, you know what I think it was. And I didn't waste any time trying to figure it out, but I think what it was is the sound cards have a noise suppression. I think they have a noise suppression so that when there's no signal input, they do something different. Okay.
Hey, good to see you. Skip. Yeah. Hey,
but
sorry.
I terminated them all with a 4700 ohm resistor, so that eliminated that open circuit on a high impedance that could cause problems.
Oh, I see.
So they were terminated.
They kind of have their own built-in AGC of some sort.
But yeah, I think they do some injection or noise injection or something that really screws it up. So. The only way to get around that would be to inject an AF noise source that actually brought it up above the zero level input and then make a measurement on that. But I didn't have that. I don't have an audio frequency noise source.
Over the years, have you tried things like a conventional instrumentation oscilloscope?
What?
A picoscope, like an instrumentation oscilloscope.
Oh, yeah, I've owned picoscopes in years past.
Could they be applied to your...
Yeah, as a data collection device, certainly. Yeah, I don't see why they wouldn't be. As long as you can set your sampling interval and get in all these cases I had power amplitude And so, yeah, I mean, as long as you can get that out of the device, then
The 100
sure.
milliseconds was the post power detection averaging.
Right.
And
now
then
that means
the filters associated with that power detection averaging, were you making sure that you were Nyquist sampling that output? In other words, that you were doing it quickly enough to capture the wiggles?
And I mean, it just gets
Yeah,
to the point where it's
I
like,
think it's like anything else. Before you.
what I, the
That's what I like about his paper. Like the way you.
the FFT gives you a bin width of X kilohertz. And so I was just sampling that at super low rate, 100 milliseconds, right? So,
I think it wouldn't matter for a long time, once you're averaging over a long time.
Yeah, I was just thinking that in the conventional sense, if it was like an analog system, your output sampling is the stability of the detectors.
I wasn't using any analog filters at all. I mean, it was
Yeah, it was all
totally
digital, but it's the same
right.
concept
Yeah,
applies.
but that's what the averaging was doing, was essentially extending out the time constant of an analog filter equivalent.
The thing I'm thinking about is that in the square root of PT, you're always better trying to take as many samples as Nyquist will give you, right? In terms of the wiggles of the output, because then you square it.
But I wasn't really looking for all the
You weren't
wiggles.
looking for that.
Yeah, I was.
You're looking for the stability of the output.
Right.
Yeah.
Great, Whit. Glad to see you. You're. Are you on next or?
No, I'm on.
I'm on next. Which computer are we using here? Does anybody know?
This is my computer. I don't know who belongs to that guy. So
these are my speakers. I just left them there. I was showing him all sorts of things yesterday.
Oh, okay.
yeah, he was here, and he's probably around here.
Kevin gave us a
somewhere.
pulsar talk. Did you guys like sitting on that?
Yeah, I did. In fact, there were a lot of good talks yesterday.
Yeah.
So I'd like to talk about DRX if I can.
Yeah, sure. I was just gonna ask, wait, are you still selling LWA antennas?
Yeah.
Okay. How many of you, like, how often?
Oh, it's not
One a
super
year?
hot.
I mean, not, yeah.
Yeah, probably a couple a year, maybe 3 a year.
Okay.
Yeah.
Cool.
Yeah, let's see, I actually sent 3 of them to Los Alamos here last December or so.
Okay.
And they're putting them down in Mexico for some lightning research project.
Okay.
And the first thing they did is burn out the front end.
You're going to use yours?
And I wrote you about that.
You want to use
this? So yeah, I repaired all those boards for them, and but those were the last ones. I've sent a couple to Denmark. One of them ended up in Greenland, and Spain, down in Roswell. A guy down in Roswell, Stan Nelson, has got one. Let's see, where else have I sent them?
No, I was just curious. I don't need a CD.
I've seen this gentleman this morning.
Yeah, that was low-fast. That was low-fast.
Did they use that antenna? Your antenna?
Plug it in right there.
You know, it was funny because I was in Green Bank one day. I was walking around with a guy, and he pointed to something and said, "You see that bracket from there? I helped add that bracket to this design." I don't know who he was. I can't remember who he was. Just telling me what.
Yeah, well, you never know, right?
I believe so. Yeah.
And it's in a.
But it could be.
You're going to open it. It's in a.
Hold on, I gotta
Memory
get
has to
access to this.
Sometimes.
Yeah, I'd like to be selling more of the LWA.
Well, maybe we will after my talk.
I hope so. It's a wonderful antenna. I mean, for doing things more than what, or in addition to what you guys do. With them. I mean, we use them in single units, right? And it's for solar, and it's great for that.
Yeah. Good. Glad to hear it. Yeah, there's a couple of different places that are talking about installations. I got email from a guy in Portugal. They want to put an LWA station on Madeira. I'm not sure what they're going to do. I mean, with the back end and all that. And then Vietnam, Vietnam wants to build another station. Another guy in United Arab Emirates.
He said he thought he was on there.
There's interest in antennas, like, you know, when I get those every once in a while, I usually just send you. And then there's interest in station. Well, we'll see. We'll see where that
Yeah,
goes.
good, I appreciate that too, just put them in contact.
No, it's great, it's great. We can't, UNM proved a long time ago that you couldn't do anything. As far as
I
like
have to
one-off.
something other than a PDF apparently.
Single antenna stuff, or, you know, like, we were talking about, like, we'll make a little business.
That's the PDF.
Yeah, and you know, the one-off stuff is perfect for me
No,
because,
no.
you know, I do so many different things that I could never handle.
No, I think you said.
Yeah, you wouldn't want to build 256.
Yeah,
Right.
I could never do it, you know.
Right, but just building one is.
Oh, pardon me, sir.
I think you said that Acrobat was on the
Yeah, so we should think about it, although I guess you don't really need to, if you're talking about the solar
This is
eclipse,
gonna be
it's only last a few minutes, right? You don't need to integrate for
Well,
Yeah, that's,
I
you
don't
know,
know
if you're
how
doing
it
the eclipse, it's just
But
that
somebody else wants to use.
15 minutes, well, it's over.
Well, I have my own laptop, but I'm not sure if it's.
It's good to know how
Why don't you go try to put it on?
Yeah.
Point of information, I had the opposite effect with the sound card. I don't know if you caught my presentation yesterday, but I was getting that artifact where it was dropping down before the signal actually was present. And that went away when I used an external sound card. But I've got an older PC, I've got an old, for the input processing, it was just an old XP machine with a sound card that came with the Super
Well, you
Sync.
send me your slides, did you send me?
Yeah, and the, you know, those were the only externals that I tried.
Yes, and I tried the one you had too.
And, but no, I just couldn't get them to work. And I think it's because what I was trying to measure, I was trying to measure white noise. And I have a feeling that those sound cards, when there's no input, they have a noise injection or an AGC, you know, maybe the gain gets cranked way out of sight. I did terminate the inputs to eliminate problems with high impedance, you know, on the input, but as far as the noise goes.
Bring back some previous nightmares with communications lines where if you didn't have a signal on the line, it behaved differently from when you had a
and
signal.
I think that's what was happening here.
Absolutely, yeah.
But I didn't, you know, I was more focused on getting measurements for all of that stuff, and I didn't want to stop and troubleshoot, because I'd already spent, you know, 100 hours trying to figure out what was going on.
Sure. You might want to do another presentation on how the hell you got computers to run for 2 months.
You know, I don't have any problem. I use the Lenovo brand, and they just run and run and run and run.
Windows has a habit of just sort of, you know, getting so fat and falling apart on its own weight.
Yeah.
Well, thanks for your presentation.
I noticed all of this, you did data collection and then you did all the calculations after the fact, right?
Right.
Did you give any consideration to, and I don't even know if it's doable, but I suppose it would be, to doing those calculations in GNU and like GRC and doing those?
No, I don't.
Using the GRC blocks?
I didn't give any thought to that at all, because I wanted to do it the way that most of the people here are doing. You know what they're doing. Most of the people aren't using GNU. You know, so.
Okay.
And I don't use it either.
All right.
I stick with.
Is there, I mean, in your opinion, is there a particular reason for that?
Setup. The setup, and if I remember right, all of the implementations I've seen of GNU run under Linux.
Yes.
And so the vast majority of the people in this room use Windows. And
okay.
So that's why I stuck with that.
Okay. Well, that's fair enough.
I'm new to this, and so I just realized you have the website where some of these kids are available. I look forward to visiting it.
Oh, yeah.
The magnetometer.
Oh, yeah,
It really
yeah.
would be fun, so thank you.
Yeah. Tried it. Works great on mine.
Well, the main reason I got it was Series 65.
something in the well, it's worth trying. I have not been impressed with
No, it comes with its own software, but it does. Yeah, the software that comes with it is free, and I think it's not an app for sure, right. Yeah, you might want to look at the LabJack because it works with actually quite a few different software, and it comes with free versions. They also have something like that that doesn't offer, so it's pretty self-contained.
Okay, everybody, come on, back to your seats. Lori's going to be giving us an overview on the DLA, some pointers and such.
Okay, hi everybody. I just wanted to step in here and give you some information about a few things and then answer any questions about tomorrow. Okay, so I put on the board our National Radio Astronomy Observatory Education and Public Outreach Director. Her name is Susie Gurton, and it's sgurton@nrao.edu. If you want to volunteer, you want to participate, you heard about the VLAS, you heard about that program that we're doing. If you want to get involved in doing some of the data products or science with that instrument on our behalf, or you want to do anything associated with NRAO Education and Public Outreach, please contact Susie Gurton, okay? As far as tomorrow, the VLA tour, I know I've had a lot of questions about it, so I want to answer some things right off the bat. For the tour itself, you should not carry your backpacks or your cameras. Remember, the cameras can be used on the outside of the facility, but once you go inside, which is what you're doing with the special tour that I've arranged for you for tomorrow, you can't take pictures inside the technical areas. Okay, so you'll want to bring your cameras for sure, but I will have a place for you to store your backpacks and your cameras for you to go on the 2-hour tour. So that 2-hour tour starts at 10 a.m. So please try to make sure that you're there by 9:45 at the latest, 9:30 if you want to store some bags, because we'll meet in the visitor center parking lot. Not inside the visitor center. You'll have time to go tour that in the afternoon, but in the parking lot, I will meet you there. It takes about an hour to drive from here. Make sure you gas up your car. It is isolated out there, so you are not gonna find gas along the way. It's really sorry. In Magdalena, but you should make sure that before you head out into the desert that you have, I would recommend that you get cheaper gas maybe in Socorro, but if you want to take a chance, you can pay a whole lot of money farther out. Let's see. It'll take you about an hour to get there. Don't speed. Highly recommend you don't speed, because they look, you're out in the middle of the desert and you're like, this is really boring, I can just get there faster, and the police are just waiting for you to do that. They will track you down. So you will have time in the afternoon. So the deal is we have tours, 4 groups, 15 people each at the most, that will be getting all the behind the scenes tours. So we're going to split up into 4 groups in the parking lot in the visitor center, and those tours start at 10. So by noon, after your tours, we're going to meet in the cafeteria building to have lunch. And then once we have lunch, then you're free to go to, there's going to be an additional LWA activity.
I'm not sure about that. I have to talk to Greg about that.
Okay.
But in any case,
Not sure about that right now.
Okay, so there will be a chance for you at that time after lunch to do the visitor center, the walking tour around the area. Take all the photos you want at that point. You can use your digital cameras all the way up to the point where they say you can't. There's gated areas that say no photography past this point. And of course, no photography inside the buildings. The visitor center is really anxious to see you guys. They do have some little snacks and drinks, but other than that, there's not really a lot of food out there to be had. And I guess that's all I really wanted to let you know, unless you have any questions.
So the afternoon is completely free form.
Free form. You can take, all the time you want out there, and yeah, it's up to you.
What do they charge for the tour?
You guys, I have negotiated a special price of free.
Thank you.
Yeah, very happy about that. The normal price is $5 per person for a normal walking tour, which has nothing to do with the behind the scenes that you all are getting. And so when you are getting your tour from the 4 volunteers, know that these are our engineers and science staff, that they have dedicated their Sunday to come out and do this on their own for you. So please be very thankful to them for their time. Yes?
Any possibility of ride share?
We don't have any transportation out there, but there is a big group here, and I would say if anybody's... Absolutely, you guys should do that. I don't know how you want to coordinate that. Maybe a sign-up sheet if you guys want to do something like that.
We can do that during lunch. We can put something like that together. But I know that my vehicle we're going to use to take stuff out there. I need the food I was talking about.
Yeah. So I'll be there with you dealing with the food. Uh-huh.
What's that? I said I want to be next.
Any other questions? Yeah?
I just want to make an announcement, I guess. For anybody here who might be especially interested in the history of astronomy, especially 19th century telescopes, I have an unusual collection of telescopes in the old Magdalena School Gymnasium on Main Street, which I now own. So if anybody wants to stop in and see this sort of warehouse-like informal presentation, tomorrow afternoon on the way home, we can improvise that, and I'd love to see you. So just speak to me afterwards.
Can you maybe post the address for those of us with GPS?
Yes.
Locate us?
Yes.
Thank you.
Okay, I'll be around if you guys have any other last-minute questions. Otherwise, yeah, have a great rest of the day.
And now, Wayne McCain.
Okay, well, hello everybody. I'm Wayne McCain from Athens State University in Alabama. We're up near the northern part of the state, just about, 20 miles from Tennessee. I'll tell you a little bit more about that. This is going to be an overview of what CubeSats are and how we might utilize them for radio astronomy. They've been around a long time. Dr. Bob Twiggs, who was from Weber State out in Utah, is now at Stanford. He set the standard for what CubeSats are. They're basically 4 by 4 by 4 inch cubes, and over 500 of them have been launched, probably getting closer to 800 CubeSats now. India, a couple of weeks ago, launched 104 CubeSats on one launch. So that's pretty phenomenal. Athens State, the oldest higher education institute in Alabama, established in 1822, have about 50 BS degrees, 2 master's degrees. I'm out of the College of Business, which sounds a little strange in technology, but we do have a Management of Technology degree program, which I'm a part of. So with my engineering background and so forth, I try to bring as much of that to play. I believe in hands-on learning, so we incorporate radio astronomy and lots of other things, rapid prototyping, amateur radio, all kinds of things like that to give students hands-on. This is some pictures of our radio astronomy laboratory and some of our antennas up in the attic of the building that we're in. My dean has been very gracious and cooperative, although she has no idea what we're doing. So far, so good, right? So what is a CubeSat? A CubeSat's a small, standardized satellite, but it packs a lot of bang for the buck. They're very small, and they are cheaper, 2 quotes my little daughter says, to launch, and we'll talk about that later. They have a very standardized structure. Probably some of you are familiar with them. The amateur radio community through AMSAT has been launching satellites a long time. They are now doing CubeSats as well. They come in lots of sizes based on the standard cube and multiplications of that cube. A standard unit, a 1-unit satellite, is the 4x4x4 I mentioned about. I think you can get up to like 6 cubes, 6 unit size. Each unit weighs about a little less than 3 pounds. They're self-contained, totally self-contained, no umbilical cords or anything running out to the launch vehicle. They have the typical subsystems you might expect: the attitude determination control system, power, avionics, structure, thermal control. All this in a little tiny CubeSat structure. We have a little model somewhere back there in the, where's the CubeSat model, Colin? CubeSat model? Okay, bring it up to me. Anyways, here's some people assembling a CubeSat into one of the launch system called a P-Pod. Actually projects these things out of the launch vehicle. This is a little cardboard model. This is approximately the size of a 1-unit CubeSat, although as you can see it's not exactly a cube, but this is basically what it looks like. You see a launch vehicle configuration over here, and the CubeSat P-Pod launcher is right down there on part of the payload adapter. A typical CubeSat launch is, for whatever mission is going on, whether it be commercial, military, NASA, whatever, the launch vehicle does its regular mission, and typically once the main payload is deployed, then the CubeSats are dropped off out of the different kinds of little launchers. And ULA, Delta, Atlas, SpaceX is doing some of them now. The Russians have been doing them. So a lot of people are doing CubeSats. A very popular educational tool these days. Here's that one of the launchers ejecting 3 CubeSats from the space station. A lot of the CubeSat satellites are actually carried up as part of the payloads going to ISS, and then they're ejected from the space station. This is a little Japanese made robot deal that picks up the payload deployment thing and ejects them out. So here's a chart showing the popularity growth of CubeSats from 2000 to present. Notice it's kind of spiked up here over the last few years. Here's 216 and projection for 217. This is pretty up to date, only February 26th. And like I say, I think this does include the India launch, so several hundred a year. Who's doing CubeSats? Well, universities started out doing most of them, as you can see, but it's grown quickly into commercial and military applications. So commercial, we're going to see in a minute, it's very strong. The EDU has been declining, actually, as you can see over the years, so maybe we can help them fix that. Anyway, what's the reliability? Well, a fairly large number of them actually don't achieve their mission. Some of them just sort of disappear. 21% of them are just ejected and never heard from again. 15% of them have some kind of failure associated with the deployment or launch. Some are dead on arrival, early losses, but so they either mission achieved or mission in progress is, you know, 30-something%, I guess, almost 40 percentile, which is not too bad considering that these things are built to a whole different standard than what a typical spacecraft would have to adhere to. And so here's another chart that shows the makeup through 2015 of universities, 131, NSF, go NSF, 13, NASA 34, military 55, 177 commercial, and as you're going to see in a second, a lot of those commercial launches have to do with developing technologies. A lot of it is associated with making the CubeSats more reliable, more radiation resistant, lots of things like that. And so it's pretty cool. And again, here's some education. The technology, as you see, is growing over the last few years. Education kind of decreasing. Communications related, imaging. There's a whole different sort of set of requirements you have to meet if you're going to take any pictures from space. So that complicates that a little bit. What are they achieving in terms of science objectives? If you're like me, I can barely see the thin little line here associated with astronomy and astrophysics. It's just non-existent almost. So there's a wide opportunity, I believe, here to incorporate this technology into our most fond hobby of radio astronomy. We'll talk more about that. So students, it's a big tool to use in science, technology, engineering, art, and math, STEAM or STEM, depending on how you're looking at it. And so you see some student involvement here. We're working some with Vanderbilt University. We just met with them a couple of weeks ago. Here's NASA is involved too, of course. They have what's called a CubeSat Launch Initiative. Here's some of the selections for people who are selected to participate in the NASA program. And you know, this is a 1 or 2 or 3 year process really to get even selected, and then it might be another year or so before you're able to fly. Again, here's what it looks like. This is from one of the specs that Dr. Twiggs helped formulate, showing the typical interface. And this, I think these drawings came out of one of the CubeSat kit manufacturers. You can actually buy a CubeSat kit. They're not cheap. I think this lowest cost one starts at about $20,000. But it includes everything, including some of the standard and flight qualified avionics and such. So you could spend 10 times more than that if you had to develop all this stuff. So, you know, it's a trade-off. But when I said cheap, $20,000 is not cheap for us guys, I suppose. Here you know, rapid prototyping technology in terms of additive manufacturing is being used. You can actually print up your own hardware. This is an example of a 3D printed shell with cutouts for connectors and solar cells and such. So there's lots of different ways to skin a cat. As I said, Dr. Fields, David, and Bogdan over there, we met with Vanderbilt a couple of weeks ago, the Institute for Defense and Space Electronics. They have one CubeSat in the air now. They're working with AMSAT. It's AO85. They have 2 more CubeSats in the queue, and it's possible that we might piggyback with Vanderbilt on a launch, which could cut years off of the process of getting a radio astronomy mission. This is what AO85 looks like, and I'm going to show you a lot of pictures. This is the Fox series of AMSAT satellites. Here's some of the specs on that. It's a 1-unit cube. Here's a better picture of it. It has 6 solar cells. Operates on standard frequencies there, 435 megahertz uplink, 2-meter ham type frequency, 145 downlink. Vanderbilt tells us really the toughest job is to meet the interface requirements with the standard AMSAT stuff. Vanderbilt research is centered on improving the radiation hardening capability of the hardware. One of the biggest problems is you go into space, you're not protected by the Earth's magnetosphere or the atmosphere, and typical electronics like your iPhone might last 5 minutes, it might not, because it gets bombarded with a lot of high energy radiation, and there's a lot of things you can do to make electronic components compatible with high energy radiation. This is what they're studying at Vanderbilt. One of the students we're working with is an all but dissertation young lady, Rebecca Austin, who her dissertation is on this topic. So we're very lucky to have connected with her. Here's typically what the avionics looks like on a AMSAT Fox. They have a complete system set up with ADAX, uplink, downlink, power, data, and they have an interface card here that I guess you basically have to develop to be compatible with your science payload. And according to Vanderbilt, that consumed most of their effort, in fact. But with a 2-meter quip, that's the download antenna. These are all little deployable antennas from measuring tape, metal measuring tapes, or some other cool ideas that have come up with. This is the receiver card, this typical transmitter card, attitude control, passive magnetic system. A lot of these things actually use little ion thrusters and different things, but those are the larger satellites. And this is one of them. This is about a 6-unit, I think, isn't it? So you can see how complex it can become, and a lot of the commercial satellites are in this category. Okay, so how many radio astronomy satellites, CubeSats, have there been? Well, you can count them on one hand, apparently. Here's 3 of them. The CIRA, and here's some of the frequency ranges that they're looking at. Solera, SARA, and SARA doesn't have to do with our SARA. I'll tell you more about that. And then a European satellite. So a lot of this information is available, and you can find it online. This has a lot of detail on what the mission of the Solera SARA is. A lot of it has to do here with monitoring some of the frequencies that we can't hear on Earth due to the atmosphere. This gives a lot of the detail. They're basically looking at solar activity and VLF and LF stuff. So, what is an opportunity for us to become involved with radio astronomy and CubeSats? Well, there's one part of the spectrum here in the LF, VLF range that is completely obscured from Earth by the atmosphere. So the opportunity is if we put a little CubeSat 300 kilometers altitude or higher, then we're above that blocking feature of the atmosphere. So that is a wonderful opportunity right now. MIT, by the way, has proposed something similar to that. We'll talk more about that. So what are some of the things you can do in this area? Well, non-thermal processes we could monitor. plasma magnetic fields, high redshift, all kinds of cool stuff. There's solar bursts, CMEs, planetary and exoplanetary radio emissions like Jove we're interested in, high energy objects like the AGN, supernova, pulsars. I know a lot of you are interested in that. Going all the way back to the beginning of time, pretty much, the epoch of reionization, first stars and galaxies, lots of real science to be done in these areas. And if you notice, there's a whole lot of planetary emissions just beyond Jupiter, but most of it is blocked. So we can't hear a lot of the stuff that comes from Neptune, Uranus, Saturn, all these things. So there's a wide opportunity there, I think. CMEs, one of my students a couple of years ago gave a paper here at SARA in the Eastern Conference on the dangers of CMEs to civilization as we know it. So we can directly monitor CMEs and solar activity from space and relay that back down to Earth. And it would be cool to be able to compare that with what people at SID project are picking up, right? SID is measuring CME activity indirectly. We'd be measuring it directly. So that would be kind of cool to compare those results. MIT is interested in doing interferometric studies at these LF frequencies. They're proposing to put up a constellation of small CubeSats, like 20 or 30 satellites or more, and kind of do what they're doing here at the VLA, but do it with CubeSats in orbit above 300 kilometers high. And with that capability, they're able to do imaging just like the VLA, a lot of really serious science. But this is Dr. Roby's work out of MIT. This was proposed last year, really, at the Small Satellite Conference, I think. Okay, so what could we do as an organization? David and I and Bogdan and Tony and all of us have been thinking about this for a while, and some proposed objectives would be the primary objective we think could be a VLF, LF, HF reception with data storage to retransmit, and this should be a 2-meter downlink instead of 70 centimeters, on command or on a periodic schedule. And how we actually do that would be determined on whether we're piggybacking with AMSAT, where we have to interface with their standard avionics, or where we build our own entire system, and we'll show you some of that. Then, of course, you want to be able to do systems operation, data downlink, what's the status of the receiver, how do we control the receiver. Obviously, we'd probably want to use a software-defined receiver of some kind that we can command to go to different frequencies, change some of the operating parameters, those kinds of things. Another thing that Dr. Fields has suggested is let's fly a low-power 1.42 gigahertz calibration beacon. This would give you guys, and all of us really, something to calibrate our hydrogen studies with. We've got a known source, known power in low Earth orbit, calibrate your receivers, and then look out into deep space. So that would be easy to achieve. And then, of course, every CubeSat, certainly every AMSAT CubeSat, has the standard 70 centimeter, 2-meter repeater capability where, and it's a unique way they download data. David is going to come up now and talk more about the ideas that we've considered, more on the research objectives and how we might incorporate that with some light cell technology and so forth. So take it away, David.
Okay, thanks, Wayne.
I'll flip slides for you.
I think you covered most of it. I just want to say thanks to Lori. Lori, thank you. It's a great conference. Thanks to David and to Gary for putting together this, and to Ken and to Tom for keeping SARA together really well, and to Kathy Hagan for putting together our journals. So anyway, it's a good group and the conferences are good.
Good job.
So just going on with this, and sometimes when you hear something a second time, it gets more interesting. Or I say things that are wrong and you catch it. So I'll tell you about light sails. Just to define them, light sails are sails, flat pieces of stuff in space that are propelled by sunlight. So light pressure, as the light's reflected, that impulse propels the sail, just like wind propels the sail in the ocean. You can navigate with these things. There's no onboard fuel. Why don't we use them? The answer is they're hard to deploy, they're hard to navigate. There have been about 9 attempts. One notable success, that was by the Japanese and JAXA, and that one is still up. The graduate students that put it together called it Icarus, and it's on its way to Jupiter. So the things work. We can, I mentioned that, why do we mention that for radio astronomy? Because if we are serious about launching a radio astronomy satellite, we've got to have a research component. We don't have to. But if we do that, the cost goes from $10 million as low as we want to go. So we pair with people to do the research, and we pair with AMSET, the knows how to pair with Vanderbilt. Or can you hear me in the back okay? Yeah. I just realized, okay, I'm making a problem. So these are small. Wayne's told you about that. We launch initially into low Earth orbit. Gets us above the atmosphere and the ionosphere. It's a known region. Lifetime's not very great, but it's very useful. We partner and we put up something that has a set of boards in it. We use a few boards as research components other than radio astronomy. Use a couple of boards. AMSAT uses a couple of boards. Communications is piggybacked on AMSAT. They don't even know it. No, they know it. They know it. But the people that use their software for communications, calling CQ, this sort of thing. There's a subaudible carrier that transmits our data. This sort of thing works. It's been done. Okay. Why do we want to do radio astronomy? As Wayne said, we get above stuff. We get below in frequency the cutoff, which most radio astronomers agree is around 5 or 10 megahertz. Different types of dissipative mechanisms result in the lower frequency signals not getting down to us. If we can get above the ionosphere, we support Jove Research, we support SuperSim people. We watch the sun. We're always going to watch the Earth. We get the galactic background in Jupiter, and I usually think Jupiter peaks up above the galactic background sometime. We can see Saturn, Uranus, Neptune, and when we're back. The thing I like this plot for is not only because it's got a lot of stuff on it, but here's the little plot for distant radio exoplanets, 10 Jupiters at a great distance. Could we see them? Well, not without some difficulty. But anyway, they're on the plot. Okay. The other thing you don't often think about is that not just the low frequencies, but the atmosphere and the ionosphere interfere with anything we want to do at wavelengths below about, let's just go frequencies above about 8 gigahertz, 6 gigahertz. We've got a lot of absorption and a lot of atmospheric noise, and we get above that if we go into space. So there are 2 different regimes that are really useful to us. What kind of research can we do? We can look at the threats and the science behind coronal mass ejections. The CMEs from the sun don't follow nice paths. They curve out along the magnetic fields, and they are a major threat to Earth. Carrington events will wipe out our 3-phase transformers. So lots of problems can originate. So here's little Earth. There's the big sun, not to scale. And we can start out by doing some measurements from low Earth orbit. And once we get some respectability and some data, contribute to some programs, we can do this in 2 or 3 years. We can do other things. We can start looking at what's contributing to climate. Well, the sun contributes to climate. What we do, volcanoes cool us off. Water, carbon dioxide, methane heats us up, and we can translate that into the forcing functions of watts per square meter. We can actually measure what the Earth is doing. We can make questions. This is going on 50 years. What if we put a shade out there? It's a thermostat, things like that. So I think we should be looking ahead. We should say, what can we do in the short term? Plan it in 1 year, do it in 1 or 2 years. We can do a satellite for radio astronomy. We can do piggyback research that moves us ahead toward being able to do some things with solar cell propulsion, thinking about it in 5 years, doing it in 8 years. We can look at laser propulsion on the light sails. I mean, we can experiment now. When can we do it? 40 years, 50 years, something like that. Okay. So, two? Okay. So, we can look at putting a satellite far beyond Earth orbit. There are other stable places to put it. And I like the Helios project. That's the thing I'm kind of interested in. But we can put a stable satellite at L1. So this is the Lagrangian L1 point, predicted by the French mathematician Lagrange, end of the 1800s. And these stable points are just put all the forces together, gravity and centrifugal force. And there are a number of these that could be nice orbiting points for watching the sun. Looking ahead, 40, 50 years, we can propel these things, the solar sails, anywhere. And you say, this is totally blue sky. You can't afford it. You'd be right 2 years ago. Now, $100 million effort. So the Breakthrough Starshot project, if we work with these people, and I know some of them, I've talked with some of them, and they'll be in Huntsville, October 3rd. If you want to join the conference, pick up a little postcard I've got. So there's a lot we can do. So I think what we do looking ahead, we want to set up a little committee or satellite group, establish some goals. We start talking with other people, and as Wayne said, Wayne and Colin, from Don, and I went to Vanderbilt, and we've talked with some of those people. AMSET is a good group. Wayne and I are members of that. We can look at some engineering studies. We can look at ways of doing this, make some models, refine our ideas, and build something. So what we actually might build could be a little 4x4 cube. This is a working model, except it's made of cardboard. Okay, so what it might be is a couple of boards to take care of communications. That's AMSET, some control, power, and power backup boards. Ours might be one board, or maybe two boards, with another 2 boards or 3 boards for an additional research project. And you've seen something like this because we didn't make this up. This works, except this says SARA now. So a lot of approaches, but these things are real. We can do it. We can get started with some planning. So I think we're both interested. If you want to talk with us, that'd be good. So turning it back over to Dr. McCain.
Thank you, David. Well, the last slide that I showed you earlier, David just showed you, is basically the yellow cube here is where the science experiment is. We have to have an interface card. Here is a notional block diagram of things, and depending on whether we flew with AMSAT or flew on our own total CubeSat, this whole architecture, of course, would depend on that. So this is just thinking on a piece of paper, so to speak. So who are our potential collaborators? Well, hopefully we're sitting in the facility of one such potential collaborator, our favorite National Radio Astronomy Observatory. We have contacted, as we said, Vanderbilt. We're working a memorandum of understanding with them as to how they're going to support us, and we will interact with them. Of course, Athens State's on board. Alabama Academy of Science, STEM Education Committee, I happen to be the chair. So there's a good chance that AAS is going to participate with us. AMSAT, we feel very certain that we can work with AMSAT and possibly piggyback on one of those flights. Florida Tech, that you've heard from me about before, they're the director of their Space Systems degree program, Dr. Donald Platt, has agreed to serve on an advisory board, our advisory board for this. So has Dr. Robert Reed, James Reed, who is the director of the Vanderbilt program. They've both agreed to sign on as consultants and advisors. We've got an astronomy club in Shoals in Alabama. Of course, if we apply and get a position on a NASA CubeSat launch initiative, that would be a good thing. David, Dr. Fields, is like director of the Rome State Observatory there in Knoxville area. I happen to live about 13 miles from the largest rocket company in the world, United Launch Alliance. I'm in the process of contacting them. They actually have an internal sort of CubeSat program, Von Braun Astronomical Society, and Spark Academy, a prime example of STEM activity. My daughter Amelia, who's a student in our audience, her STEM instructor, Jennifer Kennedy, went to Vanderbilt with David and I. They're very interested in working from a STEM standpoint. The whole idea, of course, is to get our young people involved in radio astronomy so that when we kick the bucket, there's somebody left to carry on our work, right? Okay, so in recap, here's our thoughts. CubeSat offers a unique opportunity to expand our amateur radio astronomy into space and significantly grow our outreach and STEM or STEAM efforts, whether you add art in or not, it becomes STEM or STEAM. So a SARA Sat-1 mission might be patterned after the MIT proposal for the Constellation, but just a single satellite for starters. That's Dr. Roby's work. We would employ a VLF, LF, HF transponder, directly monitor SID type signals, Jovian signals, and we would have a 1.42 gigahertz beacon for terrestrial calibration purposes. We might minimize the schedule and cost by joining an existing mission. If we can just get aboard on one of these existing CubeSat missions, that would be ideal. It would reduce the cost and schedule considerably. A lot of effort and cost on these things are centered around environmental testing and qualification of hardware. If we can use pre-qualified off-the-shelf avionics and such, boy, we've saved ourselves a lot of headache and be really good. So probably the least investment over some number of years would probably be in the $20,000 range. The Vandy effort cost them about $120,000. They had some grant funding, which we can go after. Different sources are available, particularly for STEM activities. So if we relate this to STEM, I think it opens up a good avenue for funding. So basically, we are continuing to study the feasibility of a SARA Sat-1. Ken has entered this into the minutes of the Western Regional Conference Board of Directors meeting, overall meeting. We're probably going to bring it up for a vote at the Eastern meeting to form an official endorsed CubeSat Special Interest Group, or SIG. So hopefully we'll get a lot of help from those of you who have experience and interest. And interest can go a long way, even though you don't have the experience. I'm obligated to show this picture almost every presentation I make. This was taken by my son, Colin, who is a co-author on this paper. He did most of the research, so he spent hours and hours on his computer digging up lots of reports and such on CubeSats, and I have to pay him $15 every time I show this picture. So there you go. One of the things we do at Athens State, and this is the last slide here, we are a big proponent of using the JOVE program. We have posters like this stashed all over the campus trying to get more people interested. And this just shows the interaction between the Jupiter and Io magnetic fields and the solar wind and all that. But I would reiterate what David said 10 times over in thanking Lori and NRAO VLA facility here for hosting our conference and giving us an opportunity to support radio astronomy from an amateur, non-professional standpoint. By the way, a lot of the details you saw and some that you didn't see on this are on our posters. We've kind of reached a new thing maybe in SARA conferences by summarizing presentations on posters. They're located at the back of the room there, and I'd encourage you to, if you're interested, take a look at those 2 posters. And thank you very much. Any questions? Yes, sir.
By the way, I teach a space systems engineering for a Webster College of Business, so I
all right.
So the one thing the Colorado Space, we're in Colorado, NASA Colorado Space Grant out of CU Boulder has about 5 universities that are tied to that, and most of their bachelor's degree students do the weather balloon stuff, which allows them to do multiple launches a year. They pay for it. We just need to aim the students for the research. They put magnetometers, video stuff, all that stuff.
Right.
So there's a distinct opportunity. We get a lot of this stuff done really quickly for free to do, and we always just to aim the students to give them the experiment and how to analyze it. And that'll get you a jump start on your CubeSat and do some prototyping for your CubeSat.
I think even Vanderbilt has flown some of their hardware on high altitude balloons. It's a really good mechanism for exactly what you said. Our local high school in Athens, Alabama has flown a high altitude balloon mission, so it's a good deal.
They launch them 10 miles from my house.
Nice.
Right, so
yes, sir.
What about the problem of space junk? Is there anything, do these low altitude satellites, are they designed to burn up after so many months or years?
Yes, sir. They are, and it depends on which type of commercial or military mission you piggyback on. That basically determines your orbit. But most of them last less than a year, and they re-enter and burn up by design, basically. And that is a big consideration and a big topic of conversation on CubeSats, but for the most part, they are designed to have a limited life and control burn up on re-entry. Yes, sir.
What is the hazard to the ISS when they launch CubeSats?
I'm not familiar with the details of that, but they have done extensive research on it before they started the program. The ISS has launched maybe 100 or so. I mean, they've been very instrumental in the CubeSat program, so they are very careful.
Run into any of them yet?
It's a lower orbit.
Not yet, no. Yeah, they basically shoot them on a trajectory that puts them in a lower orbit than the ISS. Any other questions? Yes, sir.
Won't you need some form of, I don't know if it's NIAA or some form of international approval to have a beacon at 1420?
Absolutely, and there's a IARU process that you have to go through, and as a matter of fact, that's one advantage of working with AMSAT, because they have the skids greased on how to do that. And if it may be that the only additional approvals we would need would be for the beacon. And yeah, I don't know of any beacons flying at 14.42 now. There may be some, but I think we'd have an easy time of it.
We won't set it on top of the hydrogen line. It'll be off if you make it.
It'll be off, yeah. It'll be in that region, but just something to use as a calibration device. Any others? Listen, I'm very appreciative of the opportunity that Ken and Dave and all of you gave us to present this concept. Let us know how you feel about it. We'd love to have you join the special interest group, and thank you very much.
Before we go to lunch, what we're going to do is, because that door over there will not be open, when you go out to eat, plan on us. We're going to open the doors at 12:30 to let you back in. It would make it easier on us if you could try to, come back to the door around like I said, 12:30. So now we're on lunch. No beer.
No!
Is the special interest group part of the college?
Well, no, I was thinking it would be a Sarah special interest group within Sarah.
Yeah? No, that's fine. I thought you already had something.
Oh gosh, I forgot to say one thing. When we start back up, let me make a two-minute announcement. I'm going to issue a $20 challenge. I've got one of these kits unassembled. Anybody that can put this thing together correctly, given the instructions that came with it, I'll pay them $20. But they have to give me the satellite when they're done with it. I tell you what, this is an Australian model here, and I don't know, I must not speak Australian or something. I'm a little worried, yeah, I'm a little worried, Ed. Oh my gosh, you're just a million? No last name? Dave Wayne. Nice to meet you. Let me give you one of my cards.
And you get this for free.
Good. Drop me an email. I think we're probably going to put a group on Facebook page. That standpoint.
That wasn't me.
No plastic comes out.
Dad, don't trip on wires or air.
Thank you. I'd love to have you. Thank you.
Here, take a card. Any card?
You're in charge of that.
Cool!
Yes, sir.
I get this for free. Well, I already had it.
I would give you, we've got a really nice trifold, but somehow I managed to leave them at the hotel. I would really like to chat with you. I work, Dr. Jim Moravich, you may know him, is a retired astronomy professor. Works with NASA picking out lunar landing sites and all. We have a very active STEAM program, and I would love to talk with you about that, because we're always looking for stuff to keep the kids active and engaged.
We're doing two special projects at the League School this spring. We're launching a little model rocket onto the big sports field we have.
Yeah.
But it's going to have a payload in it that will open legs, land, and it has a Bluetooth transmitter, transceiver. And so it transmits temperature, humidity, pressure, all that kind of stuff, and it transmits. So that's one thing we're doing. We're also doing something we call MOE, which is Mars on Earth. And we're growing radish seeds in simulated Martian soil. JPL did some research on specifications for Mars soil based on one of the Viking landing sites. We're going to do this. Yeah, except they grew potatoes. Potatoes are too big. We're on lettuces. So those are the two things we're doing. Oh gosh, the school was kindergarten through second grade. We're going to have 4th and 5th grade next year. They have a nice little lab where they do the rapid prototyping, training,
Hey, Daddy.
Our big focus right now, one of our big focuses right now is getting ready for the solar eclipse. And we're also developing, Jim and his fiance have 35 acres out near Strasburg that as a bonus came with, I hate to call it a barn, because this is like no barn you've ever seen. It's over 3,000 square feet, double insulated, 110, 220, hot and cold running water. Basically, the guy bought the place, built this, he was going to have grow houses in Colorado. Well, he didn't do his homework, because in order to have a grow house, you have to have permission from the local county government and the police. Rural Colorado isn't real big on grow houses, and he bought the place, built this place, then started trying to get permission. And of course, the county government said, not only no, but hell no. The police said, not only no, but hell no. And his neighbor said, oh, by the way, if you ever do get permission, you better have really good insurance. What? We're not threatening you. We're not threatening. We're just advising you. Well, there are a lot of them, but oh, no kidding. Where? Oh, okay. Well, I used to work there, but I was out at the main plant in Sunnyvale and some other places. Yeah, I was on special programs and different systems. Let me let you get lunch, but yeah, we'll visit some more. Yes, very much so.
Oh, what's happening?
Oh, here you are. Thank you. Great.
So, I have so there's like no
Because it is international law, and I don't know.
Pre-research here as well. Yeah, that was his suggestion. So we need to push. Yeah,
I'd like to mention.
Okay, so it was so I just wrote it. Which covers the
I got your fresh eye. I got it from
Put the computer up and.
Hey, Daddy, what'd you get?
I got roast beef thanks to.
Oh, I'm the only one that got
presentation. You brought the whole room. I did. These are all my student members here.
Yeah.
Good job.
If you ever wondered how they figure out what
Well,
next thing you know,
teaching a bunch of first year bachelor astronomy students, right? And they had the heat map. They come in here and they heat map. They have the sun map. They have to do some documentation. So I tell them, here's go figure out the distance to the size of this black hole. And they go, yeah. These guys are coming up with a scientific notation, and they love it. It's like, you guys didn't realize I tricked you. You're actually now paying attention. Where did this stuff?
Came from the professional educators.
It came from the people, but it's from the professional teaching them who don't know math.
Well, yeah, the professional who don't, like, I used to work, I was a contractor for Avaya. Those people used to amaze me.
Close it real quick. What? Just don't close it. Okay. I just don't want to come to the back. Check the little battery. It probably says 7 hours. I've got my charger. I keep that on for 2 days. I never trade it out. That's one of the reasons I got a battery. I never slow that stuff. Does everything.
It's because people well, my wife, a word person, former member of Mensa. You mentioned math and our eyeballs back there. Yes. But
people joke.
I mean, it's so weird. Or like when I was at Avaya, misplaced a comma. Oh my God! You should be drawn in quarters.
See, that's why
mention math, and they're like,
see, I'm the same way with English. You know, it's like, don't tell me about commas. Don't tell me about something. I just want to.
It's funny. The cool thing about astronomy is that women have had so much history in the astronomy field.
And all of the science.
Well, no, I understand, but astronomy, there's a lot of women that, I mean, the dark matter, the pulsar stuff. And so I keep bringing that up, and the girls in the class love this stuff. Said, women are so good in astronomy. Plus, I think they have a better temperament for observation. Guys can't stand still long enough to be observers, and women love to do that. And so I just think it's a perfect. And they were told by they're not science people. I keep saying, no, you guys are perfect. Anything else, astronomy is the place for you. Then they have a question, well, that's not really there's a different story.
Certainly not social groups.
Not social groups.
They had that in the store.
Yeah,
they'll never make one. I think it's 6.
I keep saying it's a tool. And you need to use this tool to achieve something. The problem is they teach the tool, but they never teach how to use what it's used for.
And nowadays they don't even teach the car. I'm amazed. One of my granddaughters was talking about it. And she was showing me some of her homework. Well, they said that we're going to learn about nature. We have to learn to do this way. Oh, so we're just going to take either the ball and throw it out there.
Because they don't know, the teachers don't know, they're using a book and they have no idea, they're making it up. Then they keep going, well, you'll never use this anymore. That's what they'll tell the kids. Never use this. I know.
Don't get me started on their standardized testing in Colorado.
That's a different problem. Colorado, I'm surprised.
Just don't say it very loud.
Yeah.
They'll think of.
We don't have that.
They pick every other policy up. It's horrible. It's horrible.
Oh, I can imagine. Don't get me started. Yeah. Oh, I know. I do as well.
My wife and I both have these now. These are for
Sad
I think they're just big ladies that actually.
Just remember that.
Yeah, I didn't see it out
No, the student said, oh yeah, that's right. I'm sure something else has changed.
Does everybody up here have a piece of paper and a pencil or something to write with? Yeah? She goes, you're gonna have a test. She says, I'm serious. You guys all in the school board have a test. And she goes, okay, I want you to go and, I need you to go and show the steps on how to multiply 47 by 45. And I need everybody to show your work. And she looks over, she says, I guess it was like the president of the school board. She goes, no, I'm serious. You need to write down 27 times 41 and come up with it. And use all the proper notation that we're teaching these kids, requiring these kids to try. And she goes, okay, this is the way I learned how to do it. If they have 27 over 41, you get really who did it that way? She was great. They're all fail. Yeah, because this is what they're teaching in fourth grade. That you have to do this. You have to lay out two sets of big circles around it. Now you have to do this is just like really. It's 15 steps on how to go through this. And if you miss one of those steps, you fail. So why is it that you were teaching now requiring these kids to learn things that you just
years ago.
They're totally unnecessary.
Oh, yeah, we went through it. We got shut down for the better part of the year. Thanks to the administrator. Figured out that, I don't know what this lady's problem was, but somehow she thought we were actually part of the school system. We're not. I didn't see her lots of
That's just not, I'm not sure I'll get anything ever again.
Your lesson plans. You don't have lesson plans. We have to have lesson plans.
What school system? What are you talking about?
Arapahoe.
Well, a lot of them come back from
Oh, really?
Aurora Public Schools. Excuse me. Aurora.
That's interesting.
Well, yeah, since we're a 501c3 nonprofit, all you guys do is give us a classroom.
Do you know where this is going to be next year?
Charter?
No.
Yeah, we don't have that. We have
And the school that gives us this classroom, they go out and have, this is an exaggeration, but they go out and have drunken orgies that they have more than half of a class graduate in a given year. We have 100% graduation rate for kids that go through our program. Oh, no, I mean, the principal level.
This is right on the edge of
That's prosperous. And then, so, between that and a couple of other things, they shut us down. Well, they're breaking the rules. Well, I don't think we are, but okay. Let's say that you're right. What are the rules that we're breaking? Yes, that's right, you're breaking the rules. Well, what are the rules so that we can comply with them? That's part of it. They wouldn't know.
Yeah.
Well, finally, this particular person is no longer.
Oh, cool, so you got it anyway. That's cool.
Come to find out, the big thing was, her actual position was, she was hired to promote and enhance programs like ours.
Katie and NJ.
Well, you have to
I
understand,
refused to upgrade my college.
she took her job as, oh, well, I have to improve the scores on crap or whatever they call it in the test program. And so you guys are teaching kids about improving their test scores. My job is to get rid of it.
Yeah.
Because we need to concentrate on improving these test scores.
Yeah, you don't like doing it downtown Chicago.
So your kids, even though they graduated 100%, probably didn't do as well in the tests because they're not viable tests, or?
I don't know, the tests are so meaningful that if we applied them to football, people would say John Elway is the worst quarterback in the history of football because he never scored a hat trick. They said, he said, wait a minute, hat trick, isn't that associated with talking there?
No, that's clothing.
That's about the level of relevance.
So the tests are working.
Look into Colorado, whatever they're calling this issue. I've done some research on it. And by and large,
Do you need sort of like an organization like ours to help you? Would you like it? I didn't need one, but.
I would just like to see more people get involved, and if we have high school age students, when it comes time for them to take the various tests, say, oh, by the way, this year my kids are taking.
What I'm asking is, one of the things I jump-started my entire life by doing science. And so I think most of it.
Yeah, Rich and I were talking about this, we both did.
Yeah, the science fair, right? So one of the things that our organization would like to do is like a radio astronomy science fair award, which means that all a high school science fair professor or teacher needs to do is say, hey, here's an award for $50 or you know, same thing. And radio astronomy is one of here's some of the criteria, and then students will naturally try to achieve that. Well, radio astronomy, then you start getting a bunch of radio astronomy. So people, just because somebody's given a blackout, and that's our theory is we can improve just by offering it.
That's what we do. We encourage them. And over 40-some years, our program has done existence. We've produced over 50 PhDs. Many of them have got scholarships all the way through their PhD. Our thing is, we just work with the kids. We have 3 requirements. Show up the first time, keep showing up, respect yourself and others. That's all we ask.
This is like a supplemental to the regular high school, right?
Strictly after school, like I say, show up, respect yourself and others, and that's amazing. Why than that? That's on the list. Cannot provide transportation. Probably would be liability as far away from warriors.
It kind of sounds like our product, show up, respect others, stay away from orders.
Yeah.
It's about what we're doing.
You don't respect those, you get voted off the board.
That's right.
Well, and usually we found that the kids who don't respect themselves or respect others, they find out real quick, hey, you're a jerk. The other kids, it's like, we ignore it, you know, you get ignored. And, we don't reward bad behavior.
So that wasn't
We just ignore you.
That's actually the right way to do it.
And they go away.
Go away.
Yeah. Fit in with the group, work with the group, and get rewarded.
Something like our organization.
That's what I said. Pretty much.
trucks on our government cap. Right on the edge of a mountain preserve. As you drive the
I might have been talking.
Because by the time I visited.
I'm not trying to set one up, I'm just saying.
It had already.
Easy license stuff here runs, yeah. We have a hawk every so often. It's like he's, you know, following on food. Every month or two, I see him for a while.
It's going to be a tour of a 60-foot dish.
But that's kind of, you know, kind of city. I appreciate this and stuff like that. First time we're there, we're competitors now. And they're just moving away. It's just so cool. We are, yeah, we're out. And it is quiet, yeah.
Set up the last time we did Missouri, we had about 5 telescopes, we had 2 university professors, that telescopes, we had our ham radios,
Yeah, I remember you showed up.
we had all the eats, I love it.
Leader stories about that. I don't think I've ever seen them.
We're always a little bit like third. I signed on a law, so I appreciate it.
It's not. Hey, I'm gonna do this really quick. Watch.
I think it's like, that was the one way first place in one for the plan.
We take another hard look because I got down to the wall first time before the July.
Yeah, that's why we have all these. I imagine they could jump, but they don't seem to. What we saw what happened.
Trying to lighten my load.
What's the series? Is there any example? You have a tube assembly and each part of it, you have mounting tube?
Basically, we try to have demos and everything. There's 2 or 3 that work on our front. I would really like to see maybe they move around, so we have to figure out when I grew up. I've been joking.
What's the aperture of the refractor again? 4, 3.
Cities out there is there.
I go on eBay, so we can see the Milky Way. Officially, I think it's because
we have 60-foot, that's great. Okay.
So they invite all the Sarah guys here, it's like, you know, why not even believe that they can.
We've got the word around the north side.
Really?
Hey, I just love to go out there because this guy is so pretty. We do too. Shoot all the time. Different college campuses. We don't have.
I like your 5 step project.
Yeah, well, that was theirs, you know, they designed it that way. In fact, Ed gave his, we don't have his introduction to his back in the family to the radio astronomy. And it occurred to me when I was watching it, that those are the major branches place. And that's very, that makes sense. Yeah, that shows that that's on the other part of the collection.
I bought a SIP receiver I put together. I have
By the super city.
Oh,
Oh, yeah, I was gonna say, I go back a ways, and I was first involved with the SID stuff. So, the circuit board, there's one guy, bought the parts from someone else. I had to modulate the thing until the receiver box. It was a lot of work, and like I said, I didn't get everything out of either. I couldn't get it. Yeah, that looks pretty nice. I got a nice circuit board.
I don't have a
Yeah,
I'm trying to do or well.
I think before that, he might very well be. Okay. Well, they got a new one out. You guys, if you want to start a older guys holding up. Yeah, perfect.
Travel time. Remember the other day when I showed the
Yes.
However, and I'd like to have wonderful
Assisted single operator.
Yeah, we got it. So we're just starting to get a point where we got.
That was a small one.
I will wear six. Just got to the point. Our goal is to Southwest. See something. Multiple bands.
Yeah.
I thought about that. I got a book on satellite communications. And in my head, I'm sure those casters. This is a very expensive part of the
Don't imagine any kind of theory on it, but it works. It's kind of like, what is called stick sticker. 16 foot
Slides over on 3 inch.
Yeah, I think it's
sure.
But that
I had
I would like to pick up.
Does it have a ball size?
For Ed, we have simply an elevation.
Yeah, that's
And for research trying to do, just to point this out.
That's right. That's what everybody does. That's what I do with my Aggie. And I would do the exact same thing. There are plenty of papers out there about people who have repurposed the
all this stuff.
CDAD things. What they'll do is they have there's it's like, I'm gonna say 3 inch to 6 inch thing for. That's what you use for the cold. then they show you how to put little addresses on the box, so that that's your number. That's what they.
I was gonna put a little dish, a little Michael's, because it's like, you just pick it up.
Well, maybe vertical too. Well, the horse, there's someone in the horse plenty of it.
I mean, a lot of them have like
something downsized.
So a while
Back end of a chassis mount connector.
What would you mean?
Always use that connector. That don't work. That's good.
I don't know.
Oh.
That's hard to register. Cause of migrating south into a bunch of realistic
Well, that's the other, the air spike, number 2 or whatever it is, the big one. It's also SMA connected, so I've got a big tab.
sort of migrated.
Yeah, no, I was scared, but they said, don't use that.
They're the right size.
There's no line.
No, I'm still trying to get this stupid.
Because it's an old Ajax.
In fact, one of the things we did was we got ourselves in a head up and stuck with a multi antennas. Appreciate that. Fundamentally, a lot of our guys are hands, don't know anything about history, but are interested in those guys. Most of the thing they're doing is setting up infrastructure, like power and they like to go down there and build and cut them. They're not involved for.
Yeah, it could be.
They like to eat it.
How much fun do you have driving a tractor?
I'm one of those guys. I have my hair to tractors like drive. Like being able to ground the church, right? Taking care of the stuff that's not preaching the religion.
Oh, is it? Yeah.
How much shade?
I sit down,
Well, there had some seats.
Barely alive. State diplomat was finally shot. I didn't say anything to take no hope. Two of its legs. Well, he didn't have to sell it.
That's the other problem, you know, I can't take any time off because I went to very much, but I'm still behind. It's like, come on, guys. It's nice, I got to go for work, you know, but put me so far behind I can never catch up again, so I'll never get asked for another trip.
Yeah.
No, you just scramble, you know, yeah, like this, I wanted to come yesterday. My grandfather pulled and I said, how can you do that? I said, you know, the only one thing that I like father and I pay you out for doing they're going to be all of them get paid out. Big family. They started talking about pay me out. And then it starts like boss eyes. Like I have really nice boss. This is going to be great. I have a really bad boss. And right now I have a really great boss, you know, but no guarantee of that. Seagate.
Under that policy.
Really? So it's all flex? It's all flex.
Scott party out here.
One of the things that happens okay, carbonite. So carbonite just bought.
I got started.
And we owned it. And it's just like I got. We divested it. Carbonite bought it.
This house.
Why we ever bought it? Just
happened to have one here. And
So quite a golf position. There's a laser.
Right now I'm using this big one. I really like what they've done. It's training. Like I joined. I use Dropbox for this stuff. I'll tell you what we plus I have my own little file. Good one.
Yeah, I understand that one.
Private cloud. Well, you think about,
row after stars of and these are you can pick up, don't pick your desktop, 64 colors with
Because it's so expensive. There's so much snow. Your first year of
So you could sit there and get so many of those change so terrified.
Hi, everybody, just a couple more things that you might be aware of. I put some maps for tomorrow out there if you need them. Also, it's about 10 degrees cooler out in the plains, so you might want to layer your clothes, and the sun is very bright. So if you're prone to skin, you know, that you want to protect your skin, it's about, we're almost at 5,000 feet here, you're at 7,000, over 7,000 feet there when you're at the site. So sunscreen's good, layered clothing, just because it does get chillier, to about 10 degrees cooler up there, okay? All right.
Thank you. What time are we supposed to start? 12:45, 5 minutes? Okay.
She's hanging out at my place all the time.
But I'll go ahead. You can do it. No.
Now we're
Are you ready to go?
How much are these?
I told you. You can use either one. Is this yours? Yeah. Let's see. Do you have an HDMI? I do. Yeah, that's probably good. So leave all the lights up or just
Oh, it's pretty bright. It's a white background. Put this on.
You want to use? Oh,
no, I put that on there.
Can you send it again to the screen because I'm not seeing it light up.
And I will start
I'm going to steal 1 minute from your start.
Give me a second, I'm trying to get this thing.
I'll let you get that. I'll wait on you.
Yeah, he's got money.
Skip wasn't talking.
I'll stay on the
Yeah, I got
You look real good. Thank you. Okay, especially if we can move it.
Yeah, no, that's a great Stanford may be a problem. I don't know if we replace Debbie and turn it on contact. Her husband's still there. Maybe we just have a little whiskey.
Well, I'm gonna put it out there. People are asking us to do it next year, so I wanted to get something out there.
That's a good idea. I'm all for it.
Did you get it? Or is this
It's coming.
You're fine, you're fine. I see.
Oh, yeah. Okay, perfect. How's it looking, Bogdan? Okay. You'll have to use the... What's using our things?
You're gonna go full screen.
I don't, I could probably... I could probably...
If you don't mind getting that, just give me a few minutes. What we're gonna do is I want to announce the potentials for our next restaurant. Are you really 12:45? Oh, they got a couple minutes. Let me see. If you go by the
Right as you cross the river.
I haven't played with it yet, I got it. They just came out with and man was
David has asked for some
That's fine, that's no problem. All right, let's get started. I wanted to bring up one point before. Never fails, does it? I wanted to bring up one fact before we start is our potential plans for next year for Sarah West 2018. The thought was Stanford, and then another thought was possibly Hawaii. So the thought was, because something like Hawaii, I think that's going to take a little extra planning, that possibly we would go with Stanford next year, planning on going to Hawaii the following year. But I'm open to suggestion. I'm just getting that out there so that people can mull on that and you can get back with us and give us some input on that. Big fan. I've been to Hawaii. Very nice. And as they say, there's a lot of excellent. I guess you would do the Big Island?
Yeah, this would be either probably Hilo, because that's where I have a few contacts. And I know the facilities around there a bit, so it would probably be Hilo.
Okay.
On the Big Island.
So that's, but like I said, what I want to do is, obviously I'm also thinking about Sarah East, which comes up in a couple of months. But in the meantime, we can start, David can start digging and we can look into that. So that's the thinking. It's possibly Stanford or Hawaii next year, but if Hawaii doesn't happen next year, then it will be the following year as a possibility. So, and without further ado, bye.
Thanks, Ken. Thank you, everyone, for entertaining my presentation and the facility and Lori and being at the VLA. This is such an honor to be here. One of my, well, everyone knows my favorite movie is Contact, and I weep every time I watch that movie. And so this is it, right? I'm here, and this is a wonderful place to be. So they've asked me to be part of the SARA sections, a section coordinator. This is basically through the website. There are information, distribution techniques, ideas on a variety of different topics. And I've been asked to coordinate the instrumentation, electronics and instrumentation section.
I am an electronics engineer by trade. I do software, and it's a good fit. I've collected a lot of notes and techniques, very much kind of like what we heard from Whit, of how he analyzed the receiver performance and stuff like that. And so the instrumentation section is about, making that, available to the membership. These techniques, software, as new ideas and new software techniques come up, as new receivers, as new components for your antenna systems come up, we provide that information. So I'll be doing that as a report. And I do want to thank the RASDR core team. I'll also be giving a report on RASDR, on what's going on, and I want to give a shout out to Tom, David, Stan, and Paul as the core team, and Tony has now joined the team. Tony Bigby, he lives in Colorado, and he's been a wonderful resource. He's a software developer. He's done some really great work, which we've benefited from. So in my presentation, I'll talk about the instrumentation section's mission and goals, part of an outline of the current pages that are available, the updates that I propose in the upcoming, and then kind of what I see a roadmap in the future for the instrumentation section. I'll give my RASDR 3 update, which will be the bulk of my presentation, actually. And then David will come up and give us an update on RASDR 4. Okay. So the instrumentation, so the mission of the instrumentation section is towards informing you all about the components and techniques that are available to use. I'd like, the point is that we have some curated technical documents, high quality documents that are out there, specifications on various different devices that the membership have actually tested. So, like, WIT had done testing on that. Ken has a ton of SDRs that he's constantly testing and stuff like that. I've made some tests. You all bring in your experiences, and we like to put that up, make that available so that you guys can have a body of work that's trusted to help you successfully assemble your radio telescopes. So the current instrumentation section has the following headings, and this is all available through the SARA website. There's some background and context links, links on the 40-foot dish and the Jansky antenna at the Green Bank Observatory. I apologize. The Skynet program and other online radio telescope resources, some links on Arduino, Raspberry Pi, some software-defined radios. There's a RASDR section. The Itty Bitty Telescope that you've heard about. There's a section on the 408 megahertz receiver project, and then a section on antennas, ancillary components, and test equipment. Now, the plan is for antennas to move to their own section. So there is an antenna section identified. So I think the antenna portion will be handled. I'm not sure who the coordinator is, but Stephen Tikas is sort of the overall coordinator. And I should mention a little bit about the proposed update. So the SARA board reviews all of the material that is put onto the instrumentation section. They review them once every quarter. So the proposed updates that I'll be making, I'll be submitting to the board, and then they'll approve them. And then sometime after that gets done, then the section will update. So the section hasn't updated for the last 6 or 9 months because I haven't made any updates to the section. But when we do that, so expect sort of updates every 6 to 9, or every 6 months, 3 to 6 months. Okay, so what I see as proposed updates to the instrumentation section is I'd like to sort of organize it pretty much the way you would design a radio telescope system. So I'd like to have a section on preamplifiers, a section on filters, transmission lines, amplifiers, frequency conversions, up-down converters, and then detectors and receiver electronics. And I suppose I should have a section on software as well. And so then I'll take some of the existing information and sort of put them into platforms, what hardware platforms you might be able to use. For my work, I'm using an Intel Edison Joule, which is very interesting. So I'll have a lot of a lot of things to say about that. It's an x86 processor. And so I'll be able to describe some of my experiences with that piece of hardware. I'd like to have a section on integrated systems where, our software-defined radio, Raster, itty-bitty telescope. I'd like to put links to WIT's eCallisto project and other things. And then I'd like to have a section on characterization, so noise figure measurements, using calibrated noise sources, system simulators, and test equipment. So these are all things that will be useful to you in assembling your radio telescopes and putting that all together in one place where you can go and get that information. So the roadmap, I see updates to the section links every 3 to 6 months, depending on if I'm able to meet that window. And then I see, us describing new products, devices, and integrated systems that come up. And I really would prefer to link to products and devices in which SARA members have had direct experience with. So it's not just like a clearinghouse of, a list, but actually saying, okay, well, this person, actually used this, and this was their experience, and that person did that, and that sort of thing. That way we sort of collaborate. So as that body of knowledge comes, please do contact me and send me information and your experiences and stuff like that, and I'll add them to the list. And every 3 or 6 months, then we'll review. The board will review, and then that way that information can be disseminated to you all. Okay. So now I'd like to give a update on my work with Raster. And I think, as you know, there's been sort of a bifurcation of the Raster project since the last time we presented. I've chosen to stick with the original plan of having multiple boards, but there was a new device that came online about April of last year, a Kickstarter project, and they've just now started to become available. And so a bunch of people have started working with that, and that'll be the Raster 4 team's update. But I'll give the work that I've done over this last year within the receiver design. So as a reminder, the Raster 2 basically had a block diagram that looked like this. It was a series of 2 boards. So there basically was an analog RF board coupled to a digital board. Okay? And then this was basically your antenna system. So you had your antenna, you had your low noise or block converter. You were able to tune within a frequency of 300 megahertz to 3.8 gigahertz. There was an onboard frequency synthesizer with a temperature compensated oscillator, and then that selected your sample rate, and then basically the full sample rate was delivered to the PC over the USB. No signal processing, no filtering other than the built-in filter, the low pass filter within the RF chip itself. And you could select your bandwidth from 1.5 megahertz to 28 megahertz in about 16 different steps. And you could provide a reference clock input. So that was effectively the Raster 2 system, of which I did all of my characterizations on. Okay. So the concept, as I presented to you a year ago at the Prescott conference, was to basically create a shielded enclosure, to have the digital board be basically fit within the enclosure and provide some amount of shielding and separation to the analog board, where the receive and the continuous output transmit were exposed. and then the USB connector would be provided to the back. Everything would be done on the ends of the panel. Okay, and so I estimated a cost of about $460 for the tested kit, and I had identified a corporation that was interested in facilitating the production and taking the orders and doing all the e-commerce. But we still needed to get enough people to order, and over the course of time, we only got 13 people to pledge to actually purchase a device. And so because we had to manufacture these boards, and we wanted to manufacture these boards as well to keep the costs low, we needed that initial order. That didn't happen, and the reason it didn't happen is because, well, we had to manufacture boards. And so what I realized, during the year was that really was a bad idea. It couldn't be done. It's not sustainable. I don't have the economic capability to do that. And so we had to eliminate that from being a design component. And the fact is that these boards can be purchased in single quantity at DigiKey for $300. So, half the system is available to be purchased. All we need is to figure out a way to connect this board to your PC. So, so what I did is, and this is somewhat recent that I made that realization, just because of the reality. So during the year, I set about realizing that I had to design something that could connect this board to a PC inexpensively. So the first thing I wanted to do is I wanted to characterize, okay, what is the performance of this two-board sandwich? Are there any gotchas, before we go towards, a new design, right? This design was already there, but we just couldn't produce them in quantity enough. Are there any issues with the current setup that we need to know about? And in fact, there were. Okay, so the first thing I did is I said, well, what's the response of the receiver to no signal and input? So this is basically, you fit a 50 ohm terminator on all the external ports to eliminate any signals coming into the box. The box is enclosed. And how does the receiver? So this is, in a way, similar to the receiver stability analysis that Witt did, although I didn't go into the detail that he did. But I did it more on looking at the spectrum performance, so looking at a variety of frequencies that are available within the system. Basically looking at parameters of interest of sample rate, bandwidth, and gain settings, and expecting to see flat and stable baselines. Okay, so what did I find? So the first thing I found, we first looked at the 400 megahertz band, set at 10 megasamples per second, and most of these are at 50 ohms. And I didn't like what we saw. There was a very strong interference signal, and remember, there's no, like we've done everything we could to eliminate all external signals from the box. So this is just the box on its own, right? These are internal interferences that are happening inside the system on the Raspberry 2 box, which we expect to be similar to the Raspberry 3 box if we were to assemble that system in that thing. So we see the USB clock leakage. I know that this is 400.5, so that's the center offset. 400.5 is right here, so this is 400 megahertz. That's the USB clock. There's some spurs here. There's an uneven baseline. There's a spur here, which appears to be a mixing product between 400 and 405 over here. Not overall too good. If we look at 408.1, things get better. So, okay, so we shifted the spectrum, and we're like, okay, this isn't so bad. If we stay away from 400, maybe we can get something done here. There's still a bit of baseline shift, but this isn't so bad. And the DC imbalance is always a problem, so this doesn't seem so bad. But we're at 10 megahertz, and we're losing data. And so let's reduce the sample rate. Uh-oh, that's not good. So changing nothing else but the sample rate, and all of a sudden we got all these spurs. So this is bad. And in addition, well, the baseline dropped 15 dB. So what were we doing over here to cause our baseline to be so high? right? Now we change the sample rate to 2 megasamples and our baseline dropped. Ugh, that doesn't make too much sense. So kept investigating, and basically just changing the sample rate to 4 and then 8, and this is the behavior that we saw. 4 looked very much like 2. We still got our spurs, but at 8 megasamples per second, we started getting this crazy ripple on the baseline. And what we realized is that these ripples are correlated with loss in the data stream. So if you can capture all the data, then you're fine. But if you start to drop samples, then you're basically now creating colored noise, if you will, and that's folding into your baseline. And so I think these are all the kinds of things that you're going to face when you're trying to set up a software-defined radio. So I think none of this work is lost. You're going to see this kind of behavior when you use an SDR, and so that's kind of where I want to describe these techniques, make them, make sort of procedures and protocols that you can follow to have good success with your radios. Okay, so in summary, with no signal input, we can't really move forward with this design because of these issues. We suspect the USB oscillator is leaking into the receiver front end, so we've got to deal with that. We suspect the frequency synthesizer is producing 100 kilohertz spurs and harmonics that are coupling with the sampling clock. And that's confirmed by my discussion with Mr. Stewart. And also Skip has also given me some information about that. And that's a common problem in frequency synthesizers. And there's ways to deal with that. I suspect that data loss at 10 megasamples per second is responsible for elevated and uneven baseline response. And so the DigiRed design as is cannot be used, is my conclusion. Okay. I tried to, the next thing I did is I wanted to quantify the amount of leakage. And so I did a number of measurements using the tool, and basically using the built-in markers that allow me to look at the difference between the two. And I made some notes, and I started a spreadsheet to characterize the device at various different operating points. So we look, 1600 megahertz was one of the operating points that we chose to use in conjunction. And so we would set up basically like different gain settings, different sample rates, and then make measurements of the leakage and the number of spurs, and try to sort of nail down what the performance of this device is, because when we go to the next device, or when we compare other devices, we can make some kind of quantitative measurement. So at 1600 megahertz, which is a harmonic of the 400 megahertz frequency, we have a 44 dB basically interference within the, again, this is all 50 ohm terminated input. So, okay. The next thing I did, Charles Osborne had provided for me a calibrated noise source at the SARA Eastern Conference last year with for my use. And so I used that, so now, to see if I could basically come up with a calibration procedure with a calibrated noise source. And so every telescope that you make, you need to basically calibrate your gain parameters so that you can produce normalized data, because that's the only way you can really compare your data with other telescopes or larger telescopes or someone else's telescope. You have to normalize out all of your different all of the different aspects of your system so that you produce actual absolute scale measurements. Otherwise, you're always relative, right? dB full scale. What does that mean? It can mean all kinds of things, right? Now you're just shifting around things, right? You've got to get that calibration, and the only way to do that really is with a calibrated noise source. So through that, we developed a procedure which we document within our project pages, to identify what parameters need to be adjusted so that your power and your spectrum scales, your vertical scales, can be normalized correctly. And this actually worked out fairly well. So I went out to 1420 megahertz. I'm using 2 megasamples per second. It's the behavior of the system at this frequency is reasonable. So basically, what I did is I had the calibrated noise input, and all I did was I changed the bandwidth. So I started out at 28 megahertz, and so this is basically the radiometer output of the tool. It's the integration over all samples with an integration time of 1 second. So basically, this is very comparable to WIT's process, right? With a 1 second integration. So with a 28 megahertz bandwidth inside the chip, this is my noise power. If I change the bandwidth to 12 megahertz, that's the power. 6, 3, 1. And so this is really good because you expect the power to halve every time you reduce the bandwidth by half. And so from these numbers, you can come up with calibration scales to determine, to change the scale of, to set this scale correctly, because you know what the total received power is in a 28 megahertz bandwidth because you have a calibrated noise source. So with this type of procedure, you could then calibrate the scale so that you could have actual absolute integrated power. And likewise, you could calibrate this scale to have it again a calibrated noise. And you could even get, with the right calculations, you could even have this scale in Jansky's. Okay, so that's encouraging, that the receiver, when in a quiet spot within its operation, does behave consistently and as expected. Okay. Another thing we did, David Fields had designed a up converter for the Raster project, and we worked with Mini Circuits. Carl Hayden, the field application engineer, met us on 2 occasions over the last year and provided components and an analysis. He had his application engineers look at the design, and they said it was good. And so what we did over the course of the year is we characterized it. So we hooked it up to a Raster 2. We used the continuous wave output to inject a 400 megahertz mixer oscillator frequency for the converter. I used a WinFreak technology synthesizer to create a signal that could be used to check out the output of the up converter. So there's a lot of things going on here, but basically we're receiving at 520 megahertz. We've got a 400 megahertz CW output on the Raster, so that's for the mixing of the unit. We use the WinFreak set to sweep between, we set it to 120.4 megahertz, so it's producing a 120 megahertz signal, which I'm just coupling into the antenna, so it's just like antenna coupling. And so there's the, what do we got here? So this is 0. So this is our center frequency that we're tuned to 520, and this is the 120.4 megahertz signal from the synth. So that's basically it's the signal that's been up converted through the converter. So that was basically our first light. And then what we did here is we set the tool, we set it into max hold, where it basically records, it doesn't show you the current live spectrum. It calculates for every frequency point, it calculates the maximum value and displays that, right? So what we did is then we set it in that mode, and we swept the frequency from 116 to 124, and we basically got, if this is an 8.5 megahertz bandwidth, our center frequency is here at 520 megahertz. So basically this right here represents 116 megahertz signal input. converted to 520, and then that's the 124. So we swept the signal going through the process. So the up converter worked. There's a spur here. That's not part of the up converter. Okay. This is just weird. While I was doing that, while I was forming that process, so this is about, so the previous slide was the whole sweep, right? Or maybe several sweeps, you know. I think actually this might have been two sweeps. But before I had done the first sweep, as I was halfway through the first sweep, I noticed something really strange. As the frequency was coming through toward the center frequency, I saw this artifact come in on the other side going the other way. And they both converged here. And so I haven't been able to explain that. I don't know why it would do that. But I thought it was interesting, so I put it up here. Okay, so enough of that. Another big thing that we did last year is we integrated Raspberry Proc with Radio Sky Spectrograph. So now we have a capability, just like the other SDRs, to tie into Jim Sky's spectrograph program. And so the way that works is there's a control panel here on the Raspberry software that you define the server IP, and it basically provides a network port that Radio Sky Spectrograph can connect into, and then you can get your output into that display through the waterfall. That means that you now have the ability to use a lot more programs with Raspberry. So Raspberry becomes like your SDR Sharp, or like your another tool that you're like your manufacturer's device, and then you can use Radio Sky Spectrograph to do all of your data collection, and stuff like that. Since it's a wonderful tool and it does well. We also wrote some Python code. Tony has created a waterfall that interprets the Radio Sky Spectrograph stream. So Tony's code makes the same connection as Radio Sky Spectrograph, and now you have access to the spectrogram in the Python language that you can use to develop your own signal processing algorithms. So we're slowly but surely providing ways to get the data into the programs that you like to use for radio astronomy. Okay. And then, and Tony's program, in conjunction with Tony, the Radio Sky Spectrograph limits you to 512 channels, frequency channels. So we collaborated on expanding that. So if you wish, there's an extensions that we can add, which would give you the full number of channelization that's available within Raspberry Proc software. So you can go to higher level channelizations. Okay, so one thing I did is after I had built the spectrograph, I thought about, well, how do we set the gains, right? Because setting the gains on the device is not necessarily intuitive. There's a lot of steps you have to go through because you have really 3 amplifiers within the Raspberry receiver. There's a front-end LNA, 2 variable gain amplifiers, and you have to decide, what gains to set. And generally, the rule of thumb is you go from you max out the gain on the previous stages all the way down. So effectively, you max out the LNA first, then you max out the VGA, and you max out the second VGA, which is after the low-pass filter. Well, the reality is that doesn't actually give you the highest sensitivity. So using the Radio Sky Spectrograph, I was able to use my brain as a signal processor, and I hooked up an antenna, a little whip antenna at 407.5. There's a lot of activity going on at 407 megahertz, 407.4, 407.5. There's signaling happening, and so with that antenna, you can couple into that. And there's all this digital signaling going on. And so I wanted to focus on barely visible signal. So a signal almost like a minimum, the smallest signal detectable. And so I picked this guy right here, which is this little spur right here. Actually, not that one. This one right here on the slide. So these are the limits of the RSS. So the FFT that I was taking had a lot more channels than RSS can handle. So I limited RSS to this range right in here, right? So this range maps to this frequency plot. And so this signal that I'm using to check on is this little tiny blip right above the baseline, right? And I'm changing gains to see how that signal appears, right, to my eye within this, and which one produces the highest sensitivity. And it turned out that across the different gain settings, that this one appeared to produce the highest sensitivity, right? So this is a subjective method, but the same process, I think, can be objectively determined, right? So you can codify this into a process and then make that part of your receiver calibration. And so it's one of the things that I intend to do with the software is to offer this as a tool and a process by which you can dial in the gains within a software-defined receiver. Okay. So, okay, I need to finish up to give David some time. But so basically, my new concept for the Raster device is to do it like this. So instead of building a custom board, I build a interposer board with a lot fewer components, just the synthesizer, because that's the only thing that's unique that doesn't exist anywhere else. But you can buy this board in small quantity, and there's a Cypress USB board that you can buy in single quantity for $50 that provides the same chip. And the benefit to this is that the interposer board now isolates the USB digital section from the RF section, right? So so that way the specs remain the same, the software is the same, the capabilities remain the same, but the noise is suppressed between these two. And I believe with the maker community, these boards can be produced in small quantity. And so that's what I'm going to do, and hopefully have some results for you for the Eastern Conference using this plan. I already have 2 of these, and I have 4 of these. So I just need to make a few of these, and I will probably have to cannibalize some components because they're long lead items from the existing Digireds. But I'll basically make these boards, and then we can characterize them going forward. So manufacturing now changes to the kit contains the interposer, PCB, cables, cases, and CD documents. The customer purchases mirrored RF from DigiKey. Then the customer follows instructions to assemble, perform system tests, and calibrate. And now you have a working calibrated Raster 3 system. And this is much more viable economically, and it does involve the user in part of the process, which is good. I've shown this slide before, showing similar SDR receivers, and this is the unit that the Raster 4 is based on. And so now I'll turn it over to David. I do have one slide that David doesn't have, just so you can see the difference between the Raster 2 and the Raster 4, because some of you have expressed their confusion. Which one? What is it? What's the difference? So basically what a Raster 4 is, under the same kind of nomenclature, is the Raster 4 is a Lime SDR board inside an extruded aluminum enclosure. Again, with a kit that connects all of your outputs into and out of it. And so it's, again, you buy the kit from the Raster team, and you buy the Lime SDR separately, and then you follow the instructions to assemble it. So in a sense, we're both thinking the same way, it's just that we're going on to different directions. And so with that, information can be obtained from raster.org, raster.com, and rasterllc.com. And this is them, and I'll Well, I'll hand it over to you.
Thanks, Bogdan. This is a short update to let you know what happened last year. Less than a year ago, it turned out that we were working on Raster 2 and Raster 3, and Lime Microsystems Limited announced, well, they're going to produce a new chip. It's not going to be the 6002, which we used in Raster 2 and Raster 3. It's going to be the 7002. And, you know, so what? Well, it turns out it's got lots of capabilities, and it's really intriguing. So do I push the up arrow down, or left to right? Ah, I should say which way. So this gets back to why we're doing this, and it's just to couple into SAR members to give us some new tools. And the things we would like to know from radio signals are, what's the spectra, what's the time variation, does it correlate with anything else, can we do polarization measurements, and what are the power profiles. The big deal that we keep coming up with is sensitivity and noise. Noise is just a killer. Small changes in temperature are really kind of dicey sometimes. If we want to compare two things, two antennas, are we going to do interferometry? Or we want to look at two polarizations, V and H, or right and left, or we want to compare, here's our source and here's the sky. We've got to do lots of switching. We've got to switch in two places, but we want to do it synchronously. So that's a real challenge. And the interesting thing about 7002 was it's not a receiver. It's two receivers and two transmitters. This fact of two receivers makes it a different animal entirely. So it looks like to me, this is just some of the things you can find other places. We serve SAR well by having different devices, and we've gone through lots of stages from just a kludge of parts. It looks better in a case, right? This is the Raster 2 and 3, and this is the Raster 2 anyway, with mirrored RF and the DigiRed boards, and a nice box, which has really got some good design. And now we're going to Raster 4. So the Raster 4, we've done 4 runs of laser cut cases, panels I should say, with engravings on them telling what's going on. And we put together a little kit, I'll tell you why. But the kit has the case and you can assemble. We don't sell the boards. The boards are sold by Crowdsource. They made this available on Kickstarter, and you can buy into it. They said, we need $500,000 to start doing this. And for this, we produced this fantastic board with 2 transmitters, 2 receivers, and temperature stabilized oscillator. And they overshot. They got a larger amount of money, which looks really good. If you buy it early, it's about $250. If you buy it late, it's $289. And send them an extra $100, you get a plastic case, which is kind of, send them $599, and that gives you the board and the case. So $300 case, which aluminum cases are nice. So we said, well, we don't know if we want to go that way. The comparison of details, Raster 2 and 3, Tony and Bogdan have done a lot on that software. Paul Oxley did too. Everybody talks about Tony. How many of you know Tony? Yeah, right. Stand up, Tony. Come on. Okay, thanks, Tony. So, good characteristics. Bandwidth is everything, and this goes up to 28 megahertz, which really puts it out there pretty special among the SDRs. The Raster 4 gave us bigger numbers on the bandwidth. That's a big number. It gave us a wider receive range, and 2 transmitters, 2 receivers, and lots of connectivity. So it looked like we should make this thing available to the community and to ourselves. And you can make comparisons. I don't think any of you can see it, but if you start comparing all the salient software-defined receivers, 2 things come out. The first is, if you care about cost, get the RTL SDR for $10. Okay, it's temperature sensitive, it overheats, it's noisy, it doesn't interface well, it's kind of flaky, but it's fun. The Lime SDR looks pretty good in terms of bandwidth, coverage, cost, 2 receivers, things like that. So we talked the line people out of a prototype. This is a version 1.2. If you play with it, it actually works, and that's First Light. That's Paul Oxley at the observatory. We didn't make it work inside. We took it outside, connected things better, and it worked. But the software was a little flaky. In my opinion, the software remains a little flaky. But we did have a prototype. With the prototype, we designed the case. So what you see here is the case kit. If you go to the website, LIMESLLC.com, then you'll get something like this in the mail. And it contains the parts except for the board. And then you mount the parts in the case. It's kind of fun. It worked out pretty well, except I had to, screws went in kind of hard at the end. But since that happened, if you order now, you'll get 2 screw kits. You can go different ways. So that took care of that. So that's kind of, I guess, the first Raster 4. That's the line board. It's pretty cool. It's got an FPGA. That's the other nice thing about it. Lots of programming possibilities for both the FPGA and the Lime chip. And digitizes, sends the output via USB 3 to the PC. The board's version 1.4 S board, which arrived, is a little different. It's got extra connectors, so not only do you have a clock in, so you synchronize it with an external clock, which is what we did when we took Raster 2 over to Green Bank. But you have a clock out, and the clock out, I just put a big long cable in it and ran it over here. The clock out lets you chain this to others. So if you want to have a chain of these things, 6 of them, controlling 12 antennas, then you can do that sort of thing. Sounds too good to be true. It is really. The software is crappy. It's not designed for radio astronomy. It's developed for, it's just not finished with development. But it works to some extent. Tony had it going last night, and we've got some screenshots. And, there are several different types of software out there. So the case, I won't go through all this stuff, but the case has a lot of attention to matching up things so we don't get corrosion. It's got the stainless laser cut panels. It's got all the cables. It's got 6 cables with UFL connectors on one end and SMAs on the other. Pay no attention to the D-sub connector. It's there, doesn't cost you anything in the case for eventually connecting to a little board, which you're going to produce, that will connect to the GPIO pins. That will give you some input-output connection to the board. And we just haven't done it yet because we don't have the software that controls the FPGA to control the GPIO pins and test it. So it's just frustrating to build something and not test it. So this is just, the connector's included for fun. Plugs the hole. Makes the ventilation work better. This thing works for passive ventilation. You really need to use a fan if you're not going to use it in an air-conditioned environment. Things do get warm. The little fan is nice. Depending on how you choose to plug it in, it turns on automatically when you need it. Or I sort of recommend you don't do that. I recommend you plug it in a different way, and it runs all the time. There's some noise considerations there. There's RasterLLC.com if you want to get one. There's a discount if you get it today, I guess. I think you get $5 off, and we have 5 of them here. So 5 of the kits. So I pretty much said that. What else is needed is, anybody know? Yeah. And I don't want to talk about software. Tony, you want to say some things? Okay. So, this is what it looks like.
I agreed to talk to this real briefly. Apparently there was a shortage of white male speakers here, so. So there's 2 things about the software. In 2017, it's good to be alive. There's a world of open source software out there. That comes with time challenges. The other thing is that when you talk to people about operating systems or languages, it turns into a holy war pretty quickly. So there's actually, David characterized it, software being flaky. There's a lot of software available, and what we're trying to figure out right now is what the best approach is. So there's two kinds of things here. One is user-facing applications. So how do I make the Raspberry 4 go, the Lime SDR board go? So the one that's supplied by Lime is extremely complex. Across the top there are 20 tabs. Within each tab there are dozens of controls. So it's bewildering. The other pieces of software, the applications that a lot of you are familiar with, fortunately tend to work out of the box. They're very simple, but they're good for tuning to a certain frequency and then just letting it go. So I have complex, simple, and then there's some unique kinds of software like GNU Radio and Pothos, which maybe they're just right, but Pothos is not yet ready for prime time. And GNU Radio's got a long history to it, so that's a possibility. So these also overlap with the application programming interfaces and the software development kits. So Lime supplies one for C, C++. It has 100 functions, I counted them. So again, there's some complexity there, but it gives you access to every detail that you would want to drive the SDR. They also supply a very interesting version of that in Python, so you can do the same kind of thing. And then finally, Josh Blum has written an abstraction layer called SOAPy SDR that works for not just Lime, but for a bunch of other RTL SDR, AirSpy, all the major ones are supported. But it's not the same as this. There are far less functions in here, and there's certain things you can't do in SOAPy SDR that you can do with Lime Suite. It's simpler, but you can also do things in Python. So one of the strange things is Lime is now recommending that you calibrate the unit with a Python SOAPy SDR application that's just a few lines long, and then you can start up. This is just a graphical environment, the display environment for Lime Suite. So it's a wide open time. I wanted to just end by talking real briefly about the extended RSS work that Bogdan led. It's brilliant work that he's done, because it's not just for Raster-Proc, but he's implemented these as libraries, and he's extended the RSS format. So if you're willing to connect to something that produces it, you can have as many channels as you want and as much metadata as you want. So it's fantastic work. And so this screenshot is just tuning into 90 megahertz. So it's a very basic display. And one of the things, if you use Raster-Proc that Bogdan has evolved, you can appreciate the fact that all the controls are in one screen, and you can make one click and see something happen instead of going to one of the 20 tabs and hunting. So Bogdan's put a lot of work into Raster-Proc, so it's a very nice piece of software at this point. Any questions on software? Yes?
I can only have a comment. The new radio moves about 10 times faster than its support. And so you have to spend almost all the time keeping up with what they're doing. Or at least that's been my problem. And to get it up and running on a Linux box is painful. Not only painful, half the time you can't do it. So I really don't recommend it unless you are, in fact, a Python/C++ programmer, and you can read things that are extremely impenetrable. GQRX, I had problems getting it up and running too. It is extremely simple, and when it runs, it's okay. I haven't tried SDR console, but I just got my Lime SDR. I need to get one of your cases. And as I looked through the Lime Suite and the other things there, I was flabbergasted. The page is hard to read. You don't know where to start. And so it's going to be an uphill battle to get something going. I agree with you. It's scattered. The problem is the same as with all these things. The hardware, the speed of development of hardware outstrips the development of software radically. And
So you just have to be prepared to slug it out.
I appreciate your comments. I develop in Windows, Linux, and Mac OS. I would prefer to develop only in Linux if I had my choice. But I would estimate for Lime SDR, the community, just roughly speaking, probably 50% of the users are Windows users. Maybe 30, 20% are Linux, and 10, 15% are Mac OS. Fortunately, most of these are cross-platform. I find Paul Oxley, who's a member of our Raspberry 4 team, had to push Lime to release signed Windows USB drivers. You don't have that issue with Linux and Mac OS 10. So the software side is now moving pretty quickly. The forum that Lime has put up, there's a lot of discussions by hams, very few radio astronomers on that discussion list, but there are a few. So the community is trying to push Lime to make things more usable. But for us, for radio astronomers, what we need to do is come up with something very compact. It's very similar to what Bogdan has done, and incorporates a lot of the things that you need to actually do valid scientific work, and not just see a signal and go, okay, I've seen my signal. So a lot of work ahead of us. Any other questions? David, do you have a concluding slide? You took the kit down, but for the low price of no postage, we have 4 left today for the enclosure kits.
Yeah, in conclusion, you order online, and then I'll give you this.
Yeah, if you order online, we'll give them to you today. It's through PayPal. It's wicked easy.
Since you're coming just after you realize that there's little holes in this one, you get 2 free kits.
Do you have another question? Okay.
We're running a little late.
Yes, sir.
Are there any drivers currently to support the operating systems? I mean, from the standpoint of being able to talk to this?
Yes. Oh, yes. So all these applications right now will talk to the Lime board, and it depending on which one you choose, they use either the native one or they use SOAPy SDR. So yes, you can talk to the board right now.
Okay. But are there any source blocks in GNU Radio, for example?
There's only been a little bit of that work done. I think some of that is reusable. That's one of the issues I've been in conversation with about the developer of SOAPy SDR is, why isn't this mimic this? Well, he supports all these SDRs, and he was late to the game, so this is complete and this is not. But this has got some nice things that this doesn't have in terms of user functionality, and this data flow. This is very much like a new radio where you just stitch together blocks visually, and it's very easy to do. Thank you.
Lights for a second, just so
I could use lights for the first 3 slides.
What's that?
Could use the lights for the first 3 slides.
Okay. All right. Get you plugged in, make sure that
Do you know how to work these things?
she does.
Can we have some of this?
Really show. There we go. So light time for the first couple?
Yeah. Well,
Turn the lights on.
just a little bit for a while.
I'd like to thank everybody, particularly Sarah, for allowing me to present my first presentation to the Sarah group.
Louder.
I'd like to thank everybody for allowing me to present my first presentation to the Sarah group, and NARO for hosting Sarah. My presentation is kind of splits with what you just saw. I'm going to sort of teach a little different philosophy here. What I designed here and for my presentation was my a low noise block down converter that's intended for use with a 30 megahertz direct sampling receiver. Now what I want to try to get you guys to think about doing is start using direct sampling receivers, and I'll talk about what those are specifically, with low noise block down converters. But first I want to talk a little bit about me. This is, I'm the owner of Valon Technology, a limited liability corporation that was established in 1987. I consult to a wide variety of customers and clients and help them design and develop RF and microwave equipment. We also design and manufacture our own high-quality RF products, including RF frequency synthesizers, programmable frequency dividers, phase gain detectors, frequency translators, and other products. These products that we manufacture, we sell these worldwide to a wide range of customers, typically defense, military agencies, research centers, universities, and a lot of radio astronomy sites. In fact, that's sort of how we got started with the frequency synthesizers. Was a lot of our frequency synthesizers are used to clock the Roche processors, which is a big DSP processor that are used at a lot of radio astronomy sites. I have over 40 years of experience in electrical, optical, and metrology engineering. But metrology is not the same as meteorology. You all know that, right? Okay. And I hold, I've been awarded a lot of, earned a lot of patents, but mostly in cognitive radio, signal processing, and digital optical signal processing as well. And I have some of the early patents, 1987 or 1986, on some of the first digital camera devices. My partner here, Lorraine Rumley, she's the, I don't, you probably all met her when you logged in. She's the Vice President of Operations, and she does all of the business involved with manufacturing, sales, marketing, and most important, accounts receivable, so that we get paid. That's a big part of our business. We're located in Redwood City, California, which is midway between San Francisco and San Jose. I don't know if you all know where the Bay Area is, of course, I'm sure you do. Stanford University is very close to us. UC Berkeley and Berkeley Wireless Research Labs and the Space Science Labs at Berkeley and SETI are across the bay. Some of our neighbors, Redwood City is considered part of Silicon Valley, a name that I've never really liked, but because right now there's no silicon there, but it still is a valley. Some of our neighbors are Facebook, Google, and Oracle, some of the big companies. There's many others. My hobby, of course, has always been amateur radio. I started out maybe 8 years old, like probably many of you did, tearing apart radios. Took apart a lot of tube radios, put them back together. I'm currently, well, I was licensed, first licensed 1963, so you can kind of, I was older than 8 then. You can kind of tell how old I am. But I was first licensed in 1963. I'm now a KI6QP, which some people call me quasi-peak. I don't operate much. I don't know, a lot of you probably are operators, but I don't really operate much. I like building equipment, and I particularly like building equipment for noise analysis. And it seems to me that you know, much of life is separating signals from noise. So if you can tell noise and signals, then that's pretty much universally man's quest for knowledge. I don't hunt, I don't fish, I don't like sports, but I've always found woodworking is a nice break from electrical engineering. So I like to do fine woodworking. I've made a lot of cabinets and tables, bookshelf systems, and This is an example of a 4-door cabinet I built for my daughter. It's made out of Wenge and maple. Last year I was at the Prescott conference, and I was thinking, I am a director of Sarah, and I thought I probably should volunteer to do something. And I was trying to think of something to do, and I wanted to, let me just back up. I should explain, I am not a radio astronomer. I don't know anything about astronomy. And I can't tell the difference between Cassiopeia A and Pizza Pie, but I do know a thing or two about radio. And I thought maybe I could contribute something to that. And what I've seen a lot of people doing in amateur radio astronomy is working with what I think are receivers that are not really quantifiable. And I wanted to provide a stable, quantifiable receiver platform specifically for the 21 centimeter band, because if you think about it, you're not going to be doing radio astronomy in the GPS band or PCS or cell phones or Wi-Fi or mobile telephone. Is that you would like to probably do you would probably like to do your radio astronomy in a protected band, and this 21 centimeter band is pretty ideal. So that's where I wanted to concentrate. Also, I wanted to make something that was replicable. So I see a lot of stuff going on that I don't feel is really replicable. When I make something, I don't want to just make a box full of parts and that you can't make or I couldn't supply easily to you. So that was one of my goals. The other one, I wanted to improve performance over dongles and low-cost SDRs. And I've looked at a lot of these boxes as part of my business. For the last 20 years, I've designed a lot of direct conversion radios. So I know what the warts are on direct conversion receivers. And I set as a goal it had to be less than half a dB, because what I see a lot of people doing with the low-cost SDRs and dongles is sticking LNAs on them. And let me tell you, maybe you know this as an amateur radio operator, when you put gain in front of a weak receiver, you're just asking for trouble. And so what I wanted to do was to build a converter, a low noise converter that took care of all that and provided you with low noise figure. I wanted stable, low drift gain. Would just talk to you about Allen variance deviation and gain is very important when you have small bin widths, long integration times. You want to make sure the gain is not changing. And that's another problem with low-cost receivers. Phase noise is an issue. I also wanted a system that's verifiable. There's something that you can put on a bench and measure. So if you look at the low-cost radios that you see, you cannot connect connectors to it end-to-end and measure gain and noise figure. You just can't do it. There's no way to do it. You can only do it by some indirect method. And then another big problem I wanted to minimize was spurious responses and interference to jamming and all those other things. And I always like this guy right here. He's kind of a nut job if you read about him. If you like history, this is Lord Kelvin, which is not his real name, but really William Thomson. And he has this quote, which is, "To measure is to know." And I think if people paraphrase that by saying, if you can't measure it, you don't know what you're talking about. So the other thing that always interested me, this is a little bit of brief history. I won't bore you with it. I know you're radio astronomers, you've probably all seen it, right? This is Doc Ewan's early experiment of detecting the cosmic radiation in 21 centimeters, the Huntington line. And here he is. I don't know if that's Purcell or Ewan, but I'm assuming that's Ewan. That's Ewan. Now, these photographs, I got permission to use these from NARO. They're very nice. They have a limited archive, but they'll happily send you the documents. And here he is looking into the horn of his receiver. And this kind of stimulated my interest. So I got the drawings. I don't know if any of you have ever seen the drawings. These are the engineering drawings for his horn. And you can, the dimensions are right here, and you can look this up in the antenna book. I had my buddy Tom Birnbaum do the calculation, but used to did it from charts and graphs. This thing has a gain of 24 dBi, which is not a lot of gain. It does have some nice, you can see the beam width 10 degrees, which is not that great, right? It's the Down East microwave ring. Yankees have narrower beam width. But it has this, I estimate the noise temperature of the antenna is very low, 55 degrees, because its feed looks at the sky. Feed does not look at Earth. So we could assume that this antenna is probably very efficient. Here's his receiver topology. And I think you'll recognize this as a radiometer, right? This is not a complex receiver. This is a total power receiver. You can see here's this first mixer, which is a 1N20B diode. Does anybody know what a 1N21B diode? One guy. We got one guy. Got one in your pocket? Two guys. Okay.
It's a successor to the 1N34.
Right. It's a microwave version of the 1N34. So just some interesting things. There's a slotted line, a preamplifier, 27 megahertz NBS3 receiver. And this is some form of method of separating, it's not a Dickey switch, but it's some method of looking at noise and not noising, doing some phase reversal stuff here. And here's his SDR software. This is a Esterline Angus strip chart recorder. Everybody knows what this is? It's in the book.
I got about 2 of them in my
Excellent.
file.
Hold on to that. Make sure you get the paper.
Yeah. I think I got some.
And this is this local oscillator, which I understood came from radar teardown. It was a local oscillator. Does anybody see what's missing in this block diagram? Hands? Nobody? You'll know. Oh, what do you say?
Audio.
Where's filtering? No filter, no LNA. So I'm going to guess the noise figure of this thing. I'm going to give them a lot of room here. I'm going to say it's 8 dB. It's probably more like 10 or 12. So, and then here's the, why this is the slotted line, by the way. And you probably wonder why did he have a slotted line? It's like, when I first saw this, I thought that it probably really wasn't a slotted line. Somebody just added that to the block diagram. It might have been a slide screw tuner. So I'm not really sure. But the fact that he has a piece of coax coming out of it, maybe somebody hooked a probe up for the photograph. And this is the mixer, and there's the LO. And this is really interesting. So here's the NBS3. Everybody knows what that is, right? SX17. Allographers. And this box on top is the preamp. If you look at the previous slide here, you have this preamp here. This raised the noise figure, I guess, of the NBS3. Gave it a little more gain. But anyway, I don't know what that box is. I'm pretty sure it's not a piece of HP gear. And it might be homebrew, but it's some kind of selective tuner. I'm guessing it might be General Radio. Had a selective tuner that went to 30 megahertz. I didn't include, I had to take some slides out because I thought it might be running short. Anyway, so what I wanted to do is see if I could maybe, I was hoping I could get it done by this time, was to actually observe the hydrogen line. I'm very interested in not just observing it, but I wanted to measure it in quantifiable terms, right? Everybody knows what a Jansky is. You know, that's 1 times 10 to the minus 26 watts per meter squared per second. So, your receiver's not calibrated that. You're going to have a hard time getting your SDR play to give you Janskys on your plot. So I wanted to concentrate. There's a lot of areas you have to think about when you're going to do one of these small radio telescopes. One is of course, the antenna, the gain of the antenna. What's the noise temperature of the antenna? You're going to want to find out those things because that's going to make part of this investigation fun, right? Can you tell me what the noise temperature of your antenna is? Wouldn't you like to know what that is? Also, your system noise temperature, which is your system being your receiver and LNAs and filters and all that. What is your noise figure? What is your noise temperature? What is your system noise temperature going to be? And so what I wanted to do was concentrate on what is the receiver, what's the ophthalmology. And I'm going to teach something a little different here, which is kind of I guess a split in what's being done in radio astronomy now, amateur radio astronomy. And I don't know anything about software, so I'm not even going to talk about software. But it's an important part of what you're going to want to put together. So everybody knows about receiver classes. Whit talked about two, I think. One was the total power receiver, the radiometer. And these can be made to do that, but these are really what I consider complex receivers. And I'm going to start up here in the corner. This is the outliers, right? Does everybody know what a TRF is, tuned radio frequency? That's the way all receivers were built up until about 1924. So Lee DeForest built TRFs. Armstrong came along and he built the super heterodynes, but he started first with a super regen. So everybody knows what a super regen is? Yeah. Up until about 1999, super regens were the most prolific receiver types ever built. There were more super regens built than any other type because they were used in garage door openers, keyless access, burglar alarms. There were just bazillions of them made, more than television receivers combined. So I'd like to talk about receiver classes, and let me start over here. This is what I call indirect conversion, or the super heterodyne type. This is the most common type of receiver that you have, like your Hallicrat, your SX17, or your ICOM, whatever, your hot water, your Heatkit H101. All of those receivers are super heterodyne. These are high performance receivers. They're designed to be high performance because they have dedicated local oscillators. They have high performance filters. Gain stages are divided so that the gain is balanced. They have complex AGC systems. These are the best way, up until recently, to build a receiver. And most test and measurement equipment will have super heterodyne. You know, if you get a spectrum analyzer, a signal analyzer, any of those things will be a super heterodyne type receiver. Over here, this is a direct conversion class, and probably right now that is the most common class of receiver. And I would guess there's 50 people in here in this room. I'm going to say there's 250 direct conversion receivers in here today. If every one of you has a cell phone, probably has GPS, Bluetooth, Wi-Fi, and maybe 2 cellular bands. And each one of those is a separate direct conversion receiver. So there's a bunch of them in here. And all your Bluetooth, Wi-Fi, this little gadget right here is Bluetooth, so it's got a direct conversion receiver at 2.4. All your set-top boxes, you know, if you have a Comcast set-top box, those are direct conversion television tuners. But what I want to really talk about is what I think is where things are going to go. And the trend is going to be for direct sampling receivers. The direct sampling receivers have no conversion stages. It's essentially an ADC. And right now, I think if you see Tektronix has a 3 gigahertz spectrum analyzer that is a direct sampling receiver. It's also an oscilloscope, but it has no conversion. There's no local oscillators. There's no Yiga tuning. There's nothing. It's just a high-speed ADD. So I want to recap a little bit on super heterodynes. This is what they look like, right? You're all familiar with the box. Looks like this. This happens to be an AOR 5001D, I think. But see, the characteristics of the super heterodyne are these multiple LOs, right? There's a first LO, a second LO. These can be optimized to tune over small frequency ranges, to cover large bands. You know, they do band switching. One of the characteristics is there's minimal gain usually in these stages, and these filters can be optimized. These are the crystal filters, mechanical filters, all the high quality filters usually go into the super heterodyne class receiver. This is a modern one because it's got an ADC on it, right? Normally that'd be headphone jack in the old days, but this has got an ADC on it. This is the direct conversion class. This is the one that's most common. This is cheap, economical, and effective for what it's meant to do. And this is, I'll show this little box here. It's like, this is your Wi-Fi wireless access point. These things are characterized by the fact they have a lot of gain in the front end. Typically, the direct conversion, like the ones that you see in the AirSpy or the SDR plate, are this is the topology. They'll have typically a 40 dB of gain at the RF frequency, followed by complex mixers, IQ mixer, and they convert directly down to baseband. That's why they're called direct conversion. And in baseband, they'll have maybe 60 dB of gain. That's a lot of gain. And since it's at baseband, it goes to DC. So that means that's like an op amp at DC with a gain of 1,000. So a microvolt of offset will give you a millivolt. Millivolt of offset will give you a volt. 2 millivolts of offset will overload your ADC. So these things always have something going on inside them to correct the baseband gain DC offset. And this can be a problem if you're doing long integration times. So I've built a lot of receivers using direct conversion, and these things have issues that I think are to be avoided. This is what I really want to talk about. This is what I think you all should be using. And if you don't have one today, buy one right away. This is the direct sampling class receiver. You get one of these and you'll love it. If you have a ham station, you use this as a spectrum analyzer, as an alternate receiver. Typically, they cover 0 to 30 or 0 to 50 megahertz. Some of them go as high as 0 to 60. But there's no conversion stages. You'll see no spurs. Well, there are ADC spurs, but you'll see minimum spurs in these things. And they have very high dynamic range. I just want to digress here. I'm going to get back to this. This is another common receiver topology that I think should be avoided. And you'll see this a lot in universities. In fact, this one is University of Iowa. But this is a lot of guys like to rack and stack stuff. They think they really got something going on, you know. They got a big box full of parts. But this is a bad idea. It was a good idea in 1984, but it's a bad idea now. This is what's usually at the feed horn, right? This is a NEMA box, plastic, that big box. It'll have 2 LNAs in it, maybe 1 filter. A lot of gain, 40 dB, that's fine. Big long cable coming down at 1.4 gigahertz, you know, whipping around in the wind and the snow and the noise. This is triple conversion. This comes down at 1420, 70 megahertz IF with a whole bunch more gain stages. Another mixer, some more gain. This is 10.7. No, this is, 70 to 10.7. And then it mixes again down to 1 to 3, I think. Anyway, you can see there's a lot of gain stages going on here, a lot of couplings. So you can imagine what the Allen deviation is going to be with this thing over time, right? All these things are going to be moving around in the heat, the noise. So if you try to do a long integration with this, this could be a problem. And typically, they solve that problem with this. This is that Dickey switch. Everybody knows what a Dickey switch does. This is how you compensate and calibrate. You continuously switching in the known cold noise or hot noise against the sky noise or whatever you're trying to observe. But you don't need to do this anymore. And this thing has a flaw that I've also seen is very common in this kind of rack and stack, is if you look at this topology, he's got a there's no filter in the front. That's fine. That's how you preserve the noise figure. There's this filter, which gives you some band shaping and image rejection, but not much. See, this first IF is at 70 megahertz. So he is not getting much image rejection. And there's no image filter between this amplifier and that mixer. So he's actually getting the image noise of this amplifier converted down. And he can improve the system by adding 1 more filter. So here's what I think is what you ought to be doing. This is the optimum topology. And I know it's optimum because direct satellite broadcasters use this topology. It's a block, the low noise block down converter, feed mounted at the antenna. And it only tunes a narrow band, right? That's why we call it a block down converter. This one only, in this example that I'm going to show you, tunes 1390 to 1450 megahertz. at the antenna. And then the feed line can be anything, RG58, RG6, can be 75 ohms, 50 ohms, doesn't matter. Because we don't care what the loss is here. All of the gain and noise figure of the system noise figure is established at the low noise block down converter. So here we go back to direct sampling receivers. You need to get one of these if you don't already have one. This one will cost you $1,000. And this one maybe even more. You don't need to get these. There are others. So if you do a Google search, don't do it now. If you do a Google search, you'll find maybe 100 direct sampling receivers. They're all very typical. They have sampling rates of 50 to 100 megahertz, and they tune 0 to 30 megahertz. And they have nice things, right? So they usually have large A to D ranges, 14 bits typically. 105 dB dynamic range is typical. High IP3s. All of the software that we talked about today usually works with one of these, not multiple software. There are other direct sampling receivers, by the way. Do you know what a picoscope is? Have you seen these? These are little analytical things. Yeah. So you don't need to use a so-called direct sampling receiver. A picoscope is a direct sampling receiver. So any digitizer that gives you the bandwidth that you want will work pretty well. So now, this is what I developed after that last meeting. I said, you know, these guys actually need a low noise block down converter for the 21 centimeter band. And this is the, I'm going to pass this around. This is the low noise block down converter. And this is the separate LO that goes with it. And I want to talk to you about the separate LO. There's a reason for doing that. So this has 40 dB of gain. And by the way, if the DSRs that you're looking at, like the dongles and low-cost DSR, those have almost 100 dB of gain in them. So, and in order to get the noise figure that they are promising, you have to use all of that gain. And when you start to use all of that gain, you're going to run into stability problems. So this has 40 dB of gain, has less than half a dB noise figure, has a fairly high input IP3, very stable gain, and when you use it with a 5009, you get good phase noise, and it's cheap. So here's how you use it. This is a typical cartoon of how you would use it. So this stuff, the thing that we're passing around right now, that gets feed mounted. This goes in your antenna at the feed. And if your neighbor has a C-band antenna laying out in the snow, if you're in the East Coast or in the desert here in California, you want to see if you can grab it. That's how I got a lot of them. That's the setup. So you use, this is the IF port. This will come down at 20 megahertz, and this will go to your direct sampling receiver, which you will love once you get it. So here's the block diagram. Looks just like a superhet, right? But it's a special kind of superhet. It's designed for a specific band. That's what makes it a low noise block down converter. We can optimize the LNA. This one uses a Skyworks. It's a Sky 67151. Out of the box, this thing will give you 0.3 of a dB. And I know 10 years ago, you know, you'd have to go to Directive Systems, or who was it before it was Directive System? It was anyway. You know, there are people making these amateur LNAs, big box, full parts, but this is easily simulated and designed so that you can get, I said 0.4 of a dB, and I'm going to stick with that number for now, but I think it can actually be lower. And for filtering, and I see a lot of amateurs using, I think Directive Systems and maybe Amateur Supply or Amateur Radio Astronomy Supply has a one-pole can. Do not buy that thing. Well, I shouldn't say that. If you buy it, make sure you put it on your VNA and you understand what it's doing. It's fragile. It doesn't offer a lot of Q. It's not very selective. It's got a lot of insertion loss. You can get these filters from Integrated Microwave. These are 4-pole ceramic dielectric filters. They're like $25 a piece. They're 50 ohms, no tuning. They'll never break. You can put them on your board. And you notice I use the second one here. This gives me a total of 8 poles. And I have an interstage LNA here. This is a TriQuint part, which is now Qorvo. So this combination with this mixer, I can always get the less than half a dB noise figure. And then I convert down to 145 megahertz. This is a duplexer. This keeps the LO power. This is actually a fairly high level. It's a level 10 mixer. It's a passive mixer. Passive mixers are good because they have good dynamic range. They don't have many spurs. And the spurs that they do have, you know where they're going to land. This is a 145 megahertz first IF. Gain stage, this 6-section LC filter at 145 megahertz. And then there's a second passive mixer. This is another mini circuit level 7 mixer. And then I pass the IF out at 10 to 30 megahertz. So I can instantaneously cover 20 megahertz. If you want to cover a different 20 megahertz section of the 21 centimeter band from 1950 to 1390 to 1450, you can move this LO in the 5009. You can program it to go somewhere else. This is very important, low noise voltage regulator. We don't run anything on USB or 5 volts. The USB is to be avoided at all costs. For power, you don't want to use USB for power. It's the dirtiest power you're ever going to see. And the way the translator works, if you want 1420.405, which is a hydrogen line, you tune your direct sampling receiver to 20.405, so you can easily subtract 1400 megahertz in your mind. And this is the way it looks when it's on the tower. Here's an example. The 5009, the synthesizer, this is a dual LOs, provides both LOs, has a TCXO installed in it. It's a 2 part per million TCXO. It's a rotation part. We have a port here that you can provide an external reference, either 10 megahertz, 20 megahertz, 50 or 100. And I know some of the DSRs can take an external reference, but usually they want some oddball frequency, like 24 megahertz. Now, I've never been to a lab yet that had a 24 megahertz reference standard, so this gives you a convenient way if you want to synchronize this to your lab reference standard. This is a plot of just the front end up to the first mixer of the low noise block down for the front end. This is 100 megahertz to 3000 megahertz. You can see 1420, that's this marker right here. This says 38 dB a gate. It's actually, the VNA, with the way I set this up, this is probably a little bit low. But anyway, you can see there's like 100 dB of rejection in this band. And right above it, all the way up past about 2.4 gigahertz, you also have 100 dB of rejection. It is extremely important that you get this kind of rejection. This band right here is where the ATC air traffic control radars are located. And you're going to see more and more ground-based radars to keep track of all those LEOs they're putting up, and those CubeSats. In fact, they're going to be putting LEOs up in swarms to provide broadband to various areas of the country. So you're going to need this rejection. This is a schematic. I'm sure you can all see it in your book. Can you magnify that? 5 minutes? I got 5 minutes?
Yeah, 5 more minutes, yes.
Wow. All right. And this is the LNA design close-up of the LNA. You can copy this design if you want. It's easily creatable. I did it on 370HR, which is very similar to FR4. You don't need any special dielectric. I did pull a solder mask away. This is what the construction looks like. Everything we build in boxes like this. So if you're going to build something to work at 1420 and you want to get the noise figure down to half a dB, you pretty much have to do it this way. This is the 2 ceramic dielectric filters. The LNA is right here. The second stage LNA is right here. This is the first mixer, second mixer. This gives you really good isolation, good EMI isolation. It makes the filters work as well. Here's a performance test through that. This is the way we measure noise figure. we typically measure noise figure on this thing of around 0.3 dB. We use this setup. And we sent one unit to Sanders Weinreb at Caltech to measure on his LN2 cooled system. And he measured the noise figure at about 0.52 dB, and I was actually very disheartened. It was half a dB. And so I took it to Gary Lauterbach, AD6 PF. He's got a setup in Saratoga, California, and he measured 0.52 as well. So I figured there's something wrong here, and I don't know if you look at the schematic previously. I used an ESD diode, and my experience is that for consumer devices, you almost always need the ESD diode in front of your LNA, or reliability is pretty suspect. So I took the ESD diode out, lowered the noise figure by over 1/10 of a dB. So I'm pretty sure right now we're at about 0.4 dB noise figure at room temperature. And this is a little example of, this is another way to measure noise figure. If you don't have a noise figure meter and calibrated source, you can do the C over N naught method, which means you put in a signal of known amplitude. The problem with doing that is not very accurate, because you have to use a signal of known amplitude, which is difficult to get at 1400 megahertz. Maybe it's plus or minus half a dB. And if you're trying to measure something within 1/10 of a dB, that's not going to be good enough. And then if you have a stack of attenuators to get you down to, see, these are two signals at minus 140 dBm. And I'm measuring it using this type of spectrum analyzer, the 8563. It's an old boat anchor. And it's got a 22 dB noise figure. That's a high noise figure, right? Real high noise. Your DSRs might have noise figures of about 10 to 11 dB. And here's a little stylized equation. It's not the exact Friese equation, but it gives you the idea. If you had a 0.4 dB noise figure, like in the block down converter, with a 22 dB noise figure in your second stage receiver, like this thing does, and you have 40 dB of gain, which we have, which is a minimum amount of gain, that's only going to affect your system noise figure by 0.062 dB. So you don't want to use a lot of gain. And here's the example with the ephedri. I showed you of the direct sampling receivers. The ephedri is kind of a bargain. It's $200. And with the ephedri, you can see the two tones are present. And that's, I think, this is a 1 hertz resolution bandwidth. That's pretty neat. That's a nice thing about SDRs. You can get 1 hertz resolution bandwidth. And this is a 35 dB carrier to noise ratio with a minus 140 dBm signal. So that means the noise floor here is, below KT noise, which, as you know, is not possible. Just saying, with the errors stacked up, you can see that we're getting a pretty nice result. Do I have time to talk about phase noise?
You're a minute over the 5 minutes.
Oh, okay. Well, I did want to talk about phase noise. Here's an example of phase noise. This is the SDR play, and this is the Val 2100 down converter with our 8563 receiver. They both have the same spectrum width. They're both looking at about 690 kilohertz, 690 kilohertz. This stuff here, that's the phase noise on the SDR play. That's the phase noise you're going to see on any one of these receivers that uses that Realtek 820 or the Myrix TV chip in it. So, and the reason I'm pointing that out, and a good example of that, is if I take two signals, one at 1420.42 and one at 1420.46, and this is the bigger signal, or the lower signal right here, minus 105. Here's one at minus 65. You can see the two very clearly on the ephedri. You can't see it over here on the SDR plate. It's actually in there. And if I go to the next slide and I kind of expand it, see, here's the signal at minus 65 and 105. Here's the signal at 65, and there's the one at minus 105. And then if I turn that signal, the big signal off, now you can see it, right? So the takeaway here is that, well, you're not going to see a big signal in the 1420 band. But if you're using one of these dongles, low-cost SDRs, direct conversion receivers at 1420, and you got kind of soft filters and you feed it a whole bunch of gain, there's a whole bunch of signals around there, and you're going to get this cross-modulation problem that's going to essentially raise your noise floor. And you're going to see that noise floor raising and lowering temporally, depending on what's going on in those other bands around you. So I think it's really, if you want to do some serious science in this band, you need to think about using some serious equipment. So here's my, this is just a recap showing this signal at minus 140. As you can see, if you put in a signal at minus 140 dBm, you'll get 35 dB. Slightly exaggerated because we don't know exactly that that's minus 140. Let's say plus or minus a dB. And you can see you get the 35 dB carrier noise ratio, which indicates you're getting less than a dB noise floor. And if you do the same thing with just the SDR play, if you just put that minus 140 signal into the SDR play, they claim it's got, what, 3.5 dB noise figure or 6 dB noise figure? I get a 20 dB carrier to noise ratio with 140 dB, so that tells me the noise floor is, or the noise figure is 14 dB. So now here's what I really wanted to tell you about. I know I got 2 more minutes, right?
No, way over.
Okay, so why do you want the separate LO? The reason you want the separate LO is you can use multiple of these block down converters because they can all use the same local oscillator. So now you can implement circular polarization by using 2 down converters. At NRAO, they have a hybrid at the LNA, and they do it at the RF. But we're smarter than that, right? Because they're using 1984 technology, and we're using 2017 technology. We can combine these signals in quadrature digitally, so that we could actually make left-hand, right-hand, vertical, horizontal polarization, anything you want. And we can do little mini VLAs here, right? We can use 2 of these. We can separate them. We can have extended aperture. We can have kind of a very large baseline. And because these synthesizers have an external reference that you can sync to your cesium or atomic standard, you can actually lock these at distances apart. And how did I do? I made it. There you go. So anyway.
One more slide.
So the takeaway here is I want you to do correlate down converters with DSRs.
Okay, all you cats, we're gonna be out here taking a photo. I say that because it's gonna be like herding cats.
Okay, I'm gonna get the 2100 back and who has the 2100 and the down converter?
I think they thought it was a door.
You've already installed it? I'll give you my card. I don't have it here, but.
I don't know how much the synthesizer. Oh, okay. Yeah, we're gonna get a photo taken.
And so almost everything you were talking about, I didn't understand. Obviously, it was cool. But
Obviously, it was cool.
Yeah.
It's the best part.
They've just installed a 2-dish interferometer here on the campus. Yeah, and I'm just wondering.
We're pretty cats.
Yeah, we gotta go. And I wonder whether they know about your gadget.
No, they should know.
I wouldn't mind making sure they know.
I want to order one of these.
Oh, are you? Okay, we have to call Lorraine. Did she give you a card? Seriously? Okay, yeah. Okay.
I know.
good planet glitches, but basically it's very, very good.
No problem. Okay, cool.
When you get through, we have a talk about tomorrow. Is there anything special to say about it at all?
Yeah, well, Frank's going to do it. Frank
Okay.
Schnitzel. And he says it's all set up for the tour.
Okay, good.
Yeah, so he'll be there, stationed at the LWA. You guys just walk up the hill, and Frank will give you the tour. He's expecting 3 different groups to come through.
Okay, great. And then he's going to head out on his trip
Yeah, then he's gonna
after
take
lunch,
off.
basically.
Yeah.
So after lunch, we're basically free to wander around, but there's no special
That's right.
attention or anything.
You're free to wander around. If you want to go back out to the site, to the LWA site.
Yes.
I don't have a problem with that. Just make sure you close the gate when you leave.
All right.
Yeah.
All right. Yeah, I'll make sure.
And I think if you've all been through the site, it's you've seen it.
Yeah, right. Okay. Terrific. Okay, thank you.
Sure.
Then, great. Thanks a lot.
Appreciate
He's hanging on. I got it.
Let's go see what I do. It's like, I wish I had all those tools and I wanted to, I'm just doing a simple. Yeah, I was doing the hard way.
Sorry, Greg, hopefully we're not going to. Are we still on? Oh, no, we're over.
We're almost on time. Well, we're just a couple minutes late.
I'll give you. 2:35.
Okay. Yeah. Straight big I know I've seen that shirt before. Trying to. I don't know, maybe.
It was 2 years ago when we were here.
Oh, yeah, I didn't give a talk, but I think I gave.
You might have given.
Frank gave a talk.
This would be if I was able to. As soon as he's done, I'll
Okay, yeah.
Second names, but I faces I can. I'm gonna go get out.
Okay, yeah, roust him out.
Okay. Yeah, thank you.
Still in contact with Joe
I'm thinking he did a lot of, he was a project engineer on Joe Craig. Joe Craig. Oh, yeah, Joe, he's going to come out next month. Yeah.
I'd like to get his email address from you. I got some questions.
Are we ready to go?
The guy with the red hat says you're on.
All right.
All right.
So thanks very much for the invitation to come and talk about my telescope. So my name's Greg Taylor. I'm the director of the Long Wavelength Array, which is a facility that you will see tomorrow. You will see one of the stations. We actually have 2 stations, and this is the view from our second station, which is a little bit closer to us here. It's just 20 miles north, just west of the interstate at the Sevietta National Wildlife Refuge. And what we have is an array of dipoles, very much like the array of dipoles you will see tomorrow, our first station. And this is showing us what the sky is overhead. So this is a real-time display. This updates every 5 seconds. And this is what the sky looks like at 38 megahertz. and right now, and so you can see the sun is not the brightest thing in the sky. The sun is also going down, which is, not surprising given the time of day. This big bright thing, so this is the galactic plane, and the brightest sources in the sky are actually SIG-A and CAS-A, SIG-A a radio galaxy, CAS-A supernova remnant. I'm a radio astronomer, not an engineer, but I've had to learn a bit of engineering in the course of my career. I used to work here at NRAO. Actually, for 10 years, I was on the scientific staff at NRAO. Now I'm at the University of New Mexico. So that's just, I just wanted to show you the sky, and this is, anytime you can see it.
What's the two differences? Polarization?
Yeah, this is total intensity here, and that's circular polarization. And I just want you guys to know this resource is available. So if you're interested, like, is the sun flaring right now, or what's up at 38 megahertz, at least we can answer that question in New Mexico. And now the rest of this, my time, I want to tell you about the instrument and some of the science that we do with it. Right, so this is the view, this is what you're going to see tomorrow, the first station that we built about a little more than 5 years ago. And that consists of 256 of these antennas, and they're each dual polarization, so we deal with 512 inputs. Each one covers from 10 to 88 megahertz roughly, and we can actually go into further up into the FM band, but not terribly useful for most scientific purposes. And the Sevietta station, we modified the analog receiver, which we'll talk about in a little bit, and so that we could go down to 3 megahertz because the Air Force was interested in doing some ionospheric experiments, and at the lower frequencies, the ionosphere becomes opaque. You can reflect signals off it. And so that's why they wanted to go a little lower. So at Sevietta, which was funded by the Air Force, we go a little bit lower. The first station, we cut off at about 10 megahertz, which is pretty close to where the ionosphere cuts off most days. We have a couple of different observing modes. So the one I was just showing was the all-sky mode, where we take a little bit of bandwidth, just 10 kilohertz, 100 kilohertz, sorry, just 100 kilohertz from every dipole and cross-correlate it and image the whole sky. Or we have another mode where we take the full bandwidth that's available to us and then form beams and give us the full bandwidth in certain directions, right? So we get that way much more sensitivity. So a lot of the science we do with the beam forming mode, and then but then there's other stuff that we do with this narrowband mode, the all dipoles mode. I'll tell you, depending on how fast I can keep going, about joint observing with a very large array. So the VLA has some dipoles on it, and so it's possible for them to observe from about 50 to 80 megahertz, and so we can combine with the LWA with the VLA. And then what do? We look at meteors, pulsars, the sun, Jupiter, the ionosphere, lots and lots of projects. I won't have time to talk about all of them, but I will try and hit some highlights and try and just give you a flavor of the science. We're funded as a university radio observatory, and we're open to all users. I was helping a user make their session schedule, helping Skip get his session schedule so he can observe this weekend. So anyway, if people are interested, if you have a project, feel free to get in touch with me and see if we can get you some data. Okay, so we just added, we're very proud of our new addition at Sevietta, the station there, which wasn't here when you met last in New Mexico. I think that's safe to say. And so again, 257 dual polarization. We don't have quite as much bandwidth on the beamformer. We're currently doing 20 megahertz, but hoping that we might be able to expand it. We made some changes in our digital signal processing in the Sevietta station. Some advantages and disadvantages of that. We have a 70-kilometer baseline, and so at 74 megahertz. That gives us an angular resolution of 10 arc seconds when we use it in combination with the station. The image of the sky that I showed before, which was the whole sky, had a resolution of about 2 degrees on the sky. So we get about 2 degrees angular resolution with a station which is only 100-meter aperture. But once we go to 70 kilometers, then we dramatically increase our angular resolution. Let's see, and then just the other day, we've been struggling with the beamformer. We had the station built fairly quickly. It only took us about a year to build all the dipoles, the beauty of student labor, got all these set up. But getting the beamformer, getting the software, I think echo what somebody said in the previous talk, is that the hardware is actually the easy part, and the software is where a lot of the challenge is. So we finally got the beamformer working, and so here's a detection of a pulsar from a week or so ago. And that's really good because now that we've got the beamformer working, now we can actually do this combination that of combining the two stations. Yeah.
How long was the collection time for the pulsar work?
We sat on this guy, so this is pretty good signal noise, as you notice. We sat on a fairly strong pulsar for about an hour. But we can detect pulsar, now that we know things are good, we can detect a bright pulsar in probably a minute. And I'll show you a pulsar that we can detect in a second, coming up. Okay, so I thought it'd be fun to say a little bit about the construction activities. So these are some student volunteers putting things together, right, there's lots that goes into this. We laid stuff down, so you have to do trenching. That's required because you want to stabilize. You want everything to be phase stable, so you don't want the cables to be stretching when the sun warms them up, things like that. But we put everything in conduit, so you can see. So here you can see the cables. There's 50 kilometers of cable underneath each station. We ran it in conduit. We run it down these major trunk lines, and in LWA1, like I said, we put it in conduit, but that turned out to be a terrible mistake because we basically just made this giant hamster run, and for the critters to go. At first it was the mice, and then later the snakes moved in. If you go out there tomorrow, ask Frank to show you the rattlesnakes. I'm not. They might be around. There's a good chance. Okay. Anyway, then there's ground screen antennas. Antennas are easy to set up. Here's a little video I made. All you need is we get the antennas from China, sent in bulk, and then I just grab a couple of students. If for NSF, I say tell NSF that these are college students, but I'll admit to you guys that these are my kids. It's just like building IKEA furniture with your kids at home. You just get an Allen wrench and set things up. It goes together in about 10 minutes. We speeded things up a little bit here. Yeah. Okay, the sky at these low frequencies is really, really bright. So this is an image here. It goes from, blacks from 20, so the coldest parts of the sky are like a couple thousand degrees, and then the brightest here in this map are 8,500 degrees. This is at 60 megahertz, made with LWA. We're just about with the first station, and we're about to resubmit this. We've submitted it for publication. We're about to resubmit it. And I'll tell you a little bit more about that. But anyway, so this is in galactic coordinates. So here's the galactic plane. Here's the North Polar Spur, some bright sources over here, Sig A. And okay, so we can see, and a lot of diffuse emission, right, which is actually the challenging part. There's lots of diffuse, lots of galactic emission here. But it is very bright, which means there's no point in cooling your receivers, so you just want to be sky noise dominated. That is, and we are sky noise dominated by about a factor of 4. Here's a capture just from a single dipole, so you get the feeling for what what we see. So here's the sky. The sky's actually getting brighter and brighter and brighter, but then our antenna performance turns over, and we have some filters, and so that's why that hump is here. This is covering from 10 to 98 megahertz. This, of course, is FM up here. Whoops, wrong button. That's FM, and then this is, a variety of things, CB radio, whatever. So the antenna, you'll see it. So it's this inverted V dipole. Basically, just take a dipole, but a dipole has no sensitivity at the horizon. It has sensitivity overhead, which is good, because that's where our signals are coming from, but not much sensitivity at the horizon. So we bend the dipole down to kind of open up the power pattern. And here's the power pattern simulations, so that we get a little bit of sensitivity. We've detected pulsars that are as low as, I think, minus 27 degrees declination. So we can look into the southern sky with the station with reasonable, our sensitivity drops off, because if we look straight overhead, then we have the full collecting area, but as we look down to lower elevations, the array projects into a smaller collecting area. So we intercept less of the waves coming from the radio source. So we do give up sensitivity, but we still have, thanks to the large number of dipoles, a pretty good sensitivity across the sky. And that's kind of shown here as well. That's front end noise. Okay, as frequency, never mind. Anyway, so here's the, so that's what it looks like. It's very easy, simple mount. We have this Oz post. We can just put that into the ground in like 10 seconds with a big hammer, and then build the antenna on top. Well, stick the mast on, put a collar on it, and then build the antenna. It's an active front end, and I have a couple of front ends that I can pass around. So these provide some gain of the signal, and have this fairly low noise figure, at least in comparison with the sky. Then after the signals come, so we had that first stage amplification, and the front end's also impedance match, so that we can tune over that 10 to 88 megahertz. And then after the signals come to the electronic shelter, the first thing we do is we send them through this analog receiver boards. So here's an ARX board. This is actually the one we did for Sevietta. We made a few modifications to it, but each one of these columns can handle one polarization from one dipole. So there are 16 on here, so basically take 8 antennas. So you got to have 32 boards roughly per station. So I don't know, this one is, you don't have to worry about handling this one. There's some kind of short on the board, so it's dead. we tried really hard to resurrect that board, but we could not. So now it's used for demo. And anyway, this is sort of the filtering that we can do. So we can get lots of gain, 8 to 68 dB in 2 dB steps. So we can control the signal level coming from the sky. That's useful if we're looking at, say, some faint pulsar, or maybe we're looking at the sun and it's flaring. And then, so there's a huge difference there in the strength of the incoming signal, so we need to be able to compensate. And so we can observe, so like this blue line, that's like wide open to the whole spectrum. Or maybe the interference environment is like during the day often happens that the interference environment's a little challenging at these low frequencies, so we got a lot of signals coming in here, and so instead we'll use this green filter, and we'll narrow down what's coming in. We'll suppress the interference at the low frequencies and the high frequencies, and then we can observe all the time. And then we have the paranoid filter setting. It's like, what if the environment is like much worse than we thought? what do we do? Well, so we have this other filter setting that we've actually almost never used. That's you know, a little bit more narrow and pushed up to the higher frequencies. We coexist with the local wildlife, more or less. These guys, we learned very quickly that you got to keep the cows out. So the first thing you build is a fence if there's cows around, because they will just tear things apart. And then they actually stomped on cables that we ran there's an outrigger actually over here. And initially we had a cable lying on the ground. The cows just came and they just trashed it. And then the mice, or kangaroo rats, are very keen on the optical fiber we found. They like the colorful cables. They leave the black ones pretty much alone, but anything with color they really love. Yeah, this is what happened to this is our very first antenna that we put out at the site. You can see there's no fence, and we just put out this prototype antenna, and somebody uses a back scratcher and destroyed it like overnight. Didn't even last a day. The other natural hazard we have to work with in New Mexico is lightning. So this is lucky antenna number 83 that took a direct hit from lightning. These are pieces of the cap that were scattered around from the lightning, and of course it fried the electronics in this board, the front end, and then the signal ran over to the shelter and then ran back out to all the other front ends, and we lost about 60 front ends from this one lightning strike. So that was painful, but these things happen.
Did you put surge protection on the antennas after that?
No, we have lightning arresters, and you'll see them tomorrow to prevent the lightning from getting into the shelter. The lightning was riding on the ground, and it rode on the ground of the cable to the shelter, and then, which is grounded, but then it still decided that it would rather ride back out 60 other cables that were nearby to the one. So we have 83 where that goes, the panel that it goes into, and all the other antennas that were connected to this big panel, it got fried.
Ohm's law doesn't apply.
Yeah.
Have you had trouble with like a nearby strike riding the cable to an antenna or into your electronics?
Well, no, there aren't any nearby cables really. I mean, the only thing would be the power line. So there's a buried power line. So I suppose lightning maybe could come in on that power line, but maybe it's well enough grounded but we haven't had that trouble. And at first we thought that it was just like some big induced current, that there was a cloud to cloud, like right over the array, and then induced current. Because you could see, if you looked on a map of where the bad front ends were, they made like a big stripe across the array. But then when we went out there and we saw this, we realized that we took a direct hit. Also, we realized that the reason it's a stripe is because of just how we have these main trunk lines, and from one main trunk line, all the antennas kind of group together and go to one panel.
Also, just kind of curious, how deep did you bury your cable?
We did various measurements to see how deep we had to go, and we found that 18 inches gave us good thermal stability. So our requirement's 18 inches, and most of the places it's 3 feet, 2 to 3 feet.
Thank you.
Okay, so on to the science, and I kind of highlighted. All right, yeah, I mean, I don't want to get bogged down in too much detail. I highlighted in red what I'm going to try and cover. The other, so there's astrophysics, there's cosmology, high redshift, 21 centimeter line. I'm not going to talk about that. Propagation, turbulence in the interstellar medium. We have an exquisite probe using pulsars of the conditions of the interstellar medium, and we also can directly look at supernova remnants, and so we'll. I'm try and cover some solar science, space weather, transient universe, meteors, which are a lot of fun, ionospheric physics. So we'll keep going. And like I said, if you have an idea of some project, cosmic ray physics, another whole area, you know, these showers, high energy cosmic rays, a shower, and you see in the radio, but that's just a whole nother topic. We're hoping to get more into that in the coming years. Here's the sky. So this is a paper that's about to come out. So what we did is we made images of the sky between 35 and 80 megahertz. We use about a megahertz of bandwidth. This is a different mode that I didn't really explain, but in addition to capturing 100 kilohertz all the time, we can take the full 100 megahertz, but we can only record it for about 60 microseconds, and then it takes us 5 minutes to read it all out because it's a lot of data. It's about 20 gigs in each capture. So this whole, this observation of the sky was made from many short captures, and if we add up all the data, we have about 3 seconds that goes into each one of these maps. Anyway, so we're covering the sky, and so this is nice. This is much better than images that people have done in the past in this frequency range, so we're really getting a nice image of the sky. Let's see, and that's important. Why do we care? Well, especially for the cosmology stuff and trying to understand what the if there's any redshifted 21 centimeter from the first stars and galaxies lighting up in the universe. If you wanted, the real challenge with that work is understanding the foregrounds, and so this is understanding the foregrounds. Question?
You're missing data on the gray. Are you missing data?
Big gray holes. Oh yes, the big gray holes. That's right, because the Earth gets in the way. So we can only go down to. But if we could build an LWA station, it's a great point. If we could build an LWA station in Australia, then we could fill this in. So all hope is not lost. If anybody wants to donate to the cause.
Between the 40 and the 80 megahertz. So double the frequency, it looks like double the resolution.
That's right. So it's just the wavelength over the diameter. The diameter is fixed at 100 meters. As we double the resolution, as we double the frequency, we'll double the resolution. So you can see more detail. You can the little point sources start to pop out all over the place. The sky is just littered. There are millions of sources. Most of them are active galaxies, but there are millions of sources in this.
That's such a great direct illustration, isn't it?
Yeah, I think so. And I omitted, for honesty, I omitted we have every 5 megahertz, but I didn't put them all, Yeah?
Yes, can you tell us a few things about the LEDA project and the California array?
LEDA project? Sure. So LEDA is looking for cosmic dawn, the first stars and galaxies, this 21 centimeter signal that I mentioned, and it's so we're part of LEDA at LWA, and when you go out tomorrow, you'll see these white fences, and they have an outrigger. They have one LWA dipole inside each one of these. I think there are 4 picketed areas, and those were taken where we're trying to do this total power. So we try and look at the spectrum from 10 to 88 megahertz. With these nice isolated dipoles that are seeing the whole sky, and then we look for a little inflection, a little dip that might be redshifted 21 centimeter. So, and that is being done here in New Mexico, and it's also being done at Owens Valley. So at Owens Valley, Caltech runs the Owens Valley Radio Observatory, and my friends at Caltech asked me if they could have the LWA design, and we gave it to them and helped them build a station over there. And that is one of the things they're studying, is the LEDA. Yeah?
Software to produce these images from your...
Yeah, so that's all. We developed a really nice software toolkit. It's called the LWA Software Library. It's all free, and you can get it at lwa.unm.edu. And yeah.
Do you want to say a little bit about what you've detected with fireballs?
Yes, I will. Let's go on. Here's Jupiter. So Jupiter bursts, you guys all know that, right? Radio Jove and all that stuff. So here you just see images of the sky. Jupiter flaring, when Jupiter's really going, it outshines pretty much everything else except for the active sun when that's going, which is even brighter. But it gets up to 10 megajanskis, so it's a fun target. We are doing a lot with Jupiter. This is the decametric Jovian emission produced at the poles of Jupiter by strong magnetic fields, and particles, especially those coming from Io, produce regular flares. There's a paper on this by Tracy Clark using LWA data, and what's happening this coming week or so, over the next couple of weeks, Juno is a satellite that is studying Jupiter, that's at Jupiter, and it has a really nice instrumentation suite on board. And so they're able to detect the decametric emission from Jupiter on board Juno, and of course they're close to it. And what's happening is here we are. Okay, so starting there's March 10th, here's March 21st. So starting the 21st and going until about the 27th of this month, the satellite Juno is going to be approaching the perigove, the closest place in its orbit that it gets to Jupiter. So we're approaching the fifth PJ5, the fifth perigove encounter of Juno, and so we'll be taking data with the LWA over the course of fairly intensely over the course of the next couple of weeks, and trying to better understand this decametric emission, the mechanism, where it's coming from, details like that. So that's Juno and Jupiter. Pulsars, so we have a regular pulsar monitoring program. This is a kind of a standard plot that we just crank out for every observation, which shows us the pulsar, the best profile, sort of average profile. And then here's observing time. So this observation was over a couple hours. And so you have this is the pulse here. So you got a nice strong pulse. And then this is one period later. Here's the pulse again. And then here you can see it as a function of frequency, so nice strong signal from 40 to 80 megahertz. Right, so we learn a lot from pulsars. Here's the one I promised where we can detect a pulsar in a second or so. So this is the Crab Giant Pulse. So every once in a while, for reasons we don't really understand, the Crab pulsar, which is a pulsar that's about 1,000 years old, so it's a relatively young pulsar. And every once in a while it emits this pulse, which is like thousands of times brighter than a typical pulse from the Crab. And so you can see this sweeping along here in a plot of frequency against time. The pulse arrives earlier at the high frequencies at 85 megahertz, and then it arrives later at the low frequencies. And that's because there's free electrons in the interstellar medium, and the pulse is traveling through this dispersive media, and so it slows it down at the lower frequencies. So this is just a nice illustration of what Crab Giant Pulse looks like. And I had a student working on those. I'll say, I think, a little bit more about those in a minute. We've looked at about, I think we've got about 98 pulsars detected at these low frequencies with LWA1. Kevin Stovall, some of you heard yesterday, he's the main instigator of this. He's the one who does a lot of the monitoring work, and he's going after pulsars at low frequencies with LWA. And Kevin is trying to get, he says the title of the paper is going to be 100 pulsars below 100 megahertz. I've been telling him that 98 would be just fine, but he wants to get like 2 more. And he's got, he was talking a lot about his millisecond pulsars yesterday, and so we've got 4 millisecond pulsars that we've detected. Maybe it's up to 5 by now. And so that's useful because some of those same millisecond pulsars that they're looking and using for nanograv, we're looking at them at much lower frequencies. And the reason that's interesting is because the dispersion we are really sensitive to small changes in the dispersion at these long wavelengths. We have really good sensitivity. So we can measure the dispersion measure to 1 part in like 10 to the 5, which is better than what they can do at the higher frequencies. It goes like a wavelength squared, so you get to longer wavelengths, you got a much better handle on it, and so we can do more accurate measurements of the dispersion, and that's important because it may be that you have to correct the dispersion very accurately before you can see that gravitational wave signal. That any variations in the dispersion could show up as a noise that would mask the signal. So that's something that Kevin's been working on. This is another use for the dispersion variation. So if we look at a pulsar over time, so here we are making all these measurements, and then all of a sudden we see that the dispersion measure is shot up from 9.0045 to 9.0070, right? So a pretty small change, but we're sensitive. We're easily able to see that change. If we subtract out, there's a general trend here, and if we subtract out the general trend, then it's even more obvious. Now, why are these points in red? The points are in red because they're actually points taken when the pulsar was closer to the sun. So if we plot now instead of in time, but we plot in distance from the sun in angle, then we see that these high points are clearly because the pulsar is close to the sun. So it just means that when a pulsar goes behind the sun, that we can see that change in the density. Now we're seeing the solar wind, the enhancement in the local density around the Earth because of the solar wind along that line of sight. Right, so we can measure the electron density in our solar system in this way, and this plot shows that the traditional model, which is in blue, is not a particularly good fit, that there's a number of points that are below the line when you're far out, so it overestimates the density further out, and it underestimates it close in. So we're in the process of making better measurements of what the solar wind density is. Yeah?
Are you able to see relativistic effects when you get that close to the sun with the pulsars?
I don't think we can get that close. Yeah, so I don't think we can. They can do. I think you need to have like a neutron star, like a double neutron star system, where you're really going quite close in order, to see those kind of. You got to get into a pretty strong gravitational field. I don't think. We can also get, in addition to using the dispersion measure, getting a handle on the density, we can get some idea of the magnetic field by measuring this quantity called the Faraday rotation measure. And so, this is, so we've already heard today about CMEs and the excitement about them. I always love these figures, right, that put the Earth in mortal peril. Right? Here's the sun. Oh my God, CME's going to come out and just blast us. So not to scale, okay? But anyway, we caught a coronal mass ejection. So this is a camera from a satellite looking at the sun, and we blocked out the sun. The solar disk is that little circle. So we blocked out the sun, and then we look over time. And meanwhile, here's this pulsar that's kind of marching along across the sky. And we were very fortunate that there was a CME. It wasn't completely luck. We were waiting for it. The CME came out, and it just crossed in front of this pulsar. So we got to probe a little bit of the shock front around the CME on this in 2015, August 21st. And then if we plot this up as a function of time, here's the dispersion measure. So that's measuring the density. So we can see the enhancement when the CME crossed. And then again, this is with the optical instrument also saw the. So we saw the CME very clearly, both in the white light from the optical and also in the radio with the pulsar. Whoops. Okay. And And then we didn't get the magnetic field though. We put a limit on the magnetic field strength. The magnetic field is very important because how the magnetic field is oriented and structured in the CME is going to relate to how and how much damage it does when it hits the Earth and interacts with the Earth's magnetic field. So that's why that's something we're interested in, and hopefully we'll do better with that. Here I want to say something about meteors and fireballs. So here's meteors. This is supposed to play. So here's if we just stare up at the sky and we look at a frequency where there's a lot of emission. So we look at a TV transmitter, and then and this is the return signal, right, in X and Y pole. And so you see all kinds of fun stuff here. There's airplanes running around on mostly on the horizon. There's meteors. There are little flashes of light in here. There's sporadic E, which is an ionospheric effect reflecting. So there's all kinds of stuff going on when we light up the sky at, this turns out 55.25 megahertz, and then just look at the return signal. So that's a way, that's sort of a different, we call it meteor mode. That's a way we can see like thousands of meteors in an hour. Lighting up the sky, just using a transmitter of opportunity that's down in Mexico that hasn't made the conversion to digital TV yet, fortunately. We can also see meteors. This was probably the most exciting discovery with the LWA, is that there are these big fireballs that come into the atmosphere and explode, and when they do, they can emit this trail of radio emission. And the show goes on for sort of tens of seconds, maybe for a minute. There's a bunch of profiles of different ones. They have similar profiles. And at first we were concerned that, well, we thought that what we were seeing was some kind of a reflection, just like I showed you reflections, right? But we were thinking, this is at 38 megahertz. There's not supposed to be any transmitters. But we still thought, oh, somebody could be transmitting at a band illegally, more or less. And we could be picking up that signal, but further study has shown that it's not a narrow band reflection, as is the case that we generally see the ionization trails of meteors, but it's a broad band emission from the meteors. Let me skip that slide. Here's the broad band emission. So we've caught a couple of these fireballs in a broadband beam, and so we see here from 25 to 40 megahertz, there's a continuum of emission. There was some RFI that we flagged out here, but you can see that there's very broad emission here over more than 20 megahertz. So we think it's a natural phenomena related to the explosion of the fireball in the atmosphere. Yeah?
It was gratifying to me, the author of the paper you had up a second ago contacted me because I run an all-sky media camera nearby, and in case there was a simultaneous optical detection of one of these things, he got my radio, and in fact there was, and that was a lot of fun.
It's good. Ken's a great guy.
Yes.
He's a PhD student working on this, and he's still working. We're still doing other experiments. One of the things we're looking at are these so-called persistent trains in the optical, where
I think it was one of these.
Yeah, it was one of these, and we're trying. It's hard. These are rare, and so it's we need to find enough of these, and we're trying to see if there's a connection between these long-lasting optical afterglows, which last tens of minutes, and the persistent radio emission, and that's a linkage that we're still trying to explore, and your help is very much appreciated. Okay, another clue that we've learned about the nature of these things is that the radio emission comes from these ones that detonate at high altitude at about 100 kilometers. The meteors that make it to lower elevation, they produce an optical signal, of course, but no. And an ionization trail, but none of this fireball activity. So, and we think what's happening is that when the meteor comes in and it ionizes a bunch of material and sets up these waves, Langmuir waves, which then oscillate, resonate, and give rise to the radio emission. But if it happens down low, then they get quenched. The density is higher, and they get quenched too quickly, and they can't, and so we don't get any radio emission. So that's, you have to see Ken's paper for more details. We have also, with the LWA1 and Sevietta, seen fireballs now jointly. We've seen a dozen with both instruments, and that allows us to triangulate and say exactly where the fireball was. And it also really rules out anything except for emission, because there's no way that we would have the transmitter. If this was a reflected signal, then where's the transmitter? And there's no way that you could get a reflection to both of these with the right intensities that would mimic the 1/r² decay due to just the fall off. So we're now very confident having two stations at the origin of these. And this is just one of the meteors that we've seen at the two stations at the same time. And I bet I'm probably out of time.
You got about a couple more minutes.
Okay, well, I want to leave some time for questions, so I'll just very quickly say, here's there's a transmitter in Albuquerque, and the Air Force guys will transmit a signal. Here it is, and then we can observe that signal after it bounces off the ionosphere. So here's our map of the sky, and then we can also see it after it bounces off the sky and then the ground, and then bounce off the sky again. So we see 2 hops. 3 hops. So that tells us something. We look at this pulse train, tells us something about the ionosphere. So we're basically mapping out the bottom side ionospheric structure with the LWA. And now we have 2 stations, so we can look at Sevietta, we can look at LWA1. So we're doing a whole bunch of different experiments with the Air Force Research Lab. Last thing is I've talked about, so now we can synthesize an aperture using the LWA station and the VLA stations. We've been doing some tests. So this was the first round of tests in 2015. We synthesized this aperture, and this is the visibility data we get. In white is the LWA1 baselines, which are less noisy because we have much better sensitivity. Here's an image. It's kind of boring. It's a Radio Galaxy 3C196, especially at this resolution. It's still pretty boring. It's a bright radio source, but the interesting thing is that we've increased our resolution from 2 degrees down here to about 30 arc seconds or so. And so, it's like a huge increase, factor of 200 plus increase in our angular resolution. Now there are 16. There were only a few antennas that were outfitted at the VLA. Now we're up to 16, so this was from a few months ago. And this is the aperture now that we're synthesizing. Although unfortunately, our beamformer wasn't working, so we lost all these baselines in red, and all we got was this, basically the VLA and LWA1 baselines. It still is some improvement in resolution. And this is an image that I've just been processing with the LWA1 and 13 VLA antennas. But we'd really like to double the resolution by adding Sevietta and increase the collecting area. So for the future, lots more stations around New Mexico, we hope. Cost is kind of getting in the way. It's about $1 million a station. At the rate I'm going, I'm going to be very, very old by the time we get to 50 stations. But, we're working on it. And so I'll just stop there. Thanks very much for your attention.
I thought about using these antennas for Jove. With one antenna, if we could get over the
it's been done.
amplifier on top, we could build the antenna, but I'm worried about the one on top.
The front end?
Yeah, would these antennas replace the 2 wire dipoles?
Yeah, and it's been done. Stan Kurtz, I know, has done this down in Mexico, set up Radio Jove. He had Radio Jove antenna and LWA antennas. And So I'm sure it works just fine.
One antenna be sufficient.
And the person you talk to is Whit here, so Whit can set you up with an LWA antenna.
Yeah, and I've got that information from him
Okay.
3 years ago, or 2013. But the amplifier on top would pretty much stop me. I could build the mechanical thing.
Well, he has a solution for that.
Like you supply those ready to go. They just basically drop into that gray box on the top.
Yeah.
Yeah, or mini circuits, I guess, is, if you want to go that way, probably put something together. Yeah.
Have you been able to catch any sprites or jets? Thunderstorm.
Oh, yeah, thunderstorms. Well, thanks for asking.
I had to.
So here's lightning. Here's what lightning looks like. We used to be very brave and observe during the lightning. We thought, we won't get hit. Then we got hit. Now we're not as brave. But so you can see these, the lightning, and we can zoom in. This is one frame. So you see sort of like the lightning overhead. We can zoom in and we could go at milliseconds or even microseconds and step through it. And in fact, there's lightning research that's done here on campus at New Mexico Tech. They took a bunch of data with the LWA1, and unfortunately, I've never seen a paper. But there is certainly a lot you can do. Looking at the lightning, that's not my science, but how it branches out, this sort of step leader, and you can watch it develop over time. We have very good time and frequency resolution for this sort of thing.
Can you get a distance estimate from that?
Can we get what?
A distance estimate from the lightning?
I'm sorry, I can't
Distance.
hear over the distance. Can we get the distance? Ken is doing some interesting things. He wants to, can we get distance to a lightning bolt? I mean, well, with only 100 meters, I don't think we can very well. But with the 2 stations, we could triangulate. So Ken is doing some things where he wants to see lightning, and then actually he wants the lightning to bounce off the ionosphere and tell us about ionospheric structure. I know there is this lightning mapping array, and the folks at New Mexico Tech, where they have dipoles all around, distributed around the country, and I think they can use that to triangulate. Certainly you can get distances and map out where storms are based on the lightning, and that's a fun thing to do, but not really well done with just a couple LWA stations. If we had all of New Mexico, 50 LWA stations, we'd know where every thunderstorm was to exquisite detail.
Suppose you had a few of these in orbit processing them. Have you considered that? Small satellites, but
Put these guys, put
exactly.
Go up into orbit. We've actually thought about going to the moon. So we got funding from NASA for a while to do studies of, we did layouts, array design for how we would put a station down on the moon. And the moon is nice in a couple of ways, and it gives you a nice platform to sit and work on, to put your station down. And then the other thing it does is it blocks the interference from the Earth. So for 2 weeks out of every 4, you're protected from the sun and the Earth, and so you have this really nice radio quiet. It's the most radio quiet place in the inner solar system. So that's good. Whereas if you were free flying out in space, there'd be a lot of challenges with calibrating the instrument, a lot of challenges, and you would also be open to interference from the Earth and the sun. So that's why we thought about the moon. I think there have been a couple of conferences about what can you do with astronomy on the moon, and always low frequency is the best thing that you can do on the moon.
Is it possible to scale your techniques, your general approach to a higher frequency, like 408 megahertz?
Yeah, absolutely. Well, I was one of my collaborators wanted to build an array. Let's go up to 400 megahertz and see. Below a gigahertz, this technique works basically. Where look at the whole sky, and cross-correlate, beamform, all that kind of, and there's a lot of advantages, like I think I've demonstrated, that one advantage is we can move anywhere in the sky in just milliseconds instead of slewing a big, the VLA will take minutes to get there. We can be on there in milliseconds instead of minutes. So there's a lot of advantages to this technique. Yes, you can certainly scale it up. There's an experiment at Westerbork where they're not doing the whole sky, but they're tiling a large array. There's the LOFARs working up at the high band, and they're imaging the sky in a similar way to what I'm talking about. So yes, it certainly can be done. And we thought about it, but I just didn't want to branch out into take on too many projects. We're trying to get the most with the nice thing about this part of the frequency, this frequency range is so little explored. And so it's so interesting to see this, the decametric emission, all the fun science that we can do down at these really low frequencies where people just haven't tried. Whereas up at 400 megahertz, the sky's a little better known there.
For you.
Oh, thank you very much. Get a picture?
Oh,
great, terrific.
Oh, yeah, thank you. Okay.
He's working on Colorado Springs area. Is there some stuff that we could do at like the high school tied in with this?
Quite possibly.
I just think we've got at the end of we're at a high school in Aurora, Colorado. We've got 45 acres out there by Strasburg. Spelling it nowhere.
Yeah.
And I've been listening to you.
Anybody interested in assembly instructions for SR4?
More than one. Thank you.
Sure, yeah.
But you can sew back up on
Why don't we use my mouse? I got it.
Excellent.
All set?
Very good.
Everybody got a stretch?
Yeah, is everybody stretched?
I know it's late in the afternoon.
Do you have any small, like firecrackers?
Yeah, that's what we need. Just something. I'm a little tired from driving down last night. Got here about midnight. But so if I end up too light, just raise your hand in the back, and I'll try to pick it up a notch. My name is Bill Miller. I'm with the Deep Space Exploration Society in Colorado Springs. There's 4 of us here today. Our president, Dr. Richard Russell, our vice president, Stephen Plock in the back, and Dave Moulter, our technical consultant, and I'm Bill Miller, the secretary of the organization. We've got a group there in Colorado Springs, probably about 20 of us now and growing, and we've got people all over that are starting to join our organization, but we're kind of fortunate to be in this and fortunate to be here. I want to thank the NRAO and the SARA Conference Committee for hosting us. I got to admit, I'm not a radio astronomer. This is new to me. This is something that I've just started in about a year ago. And when I saw what these guys had, I said, I got to get involved in that. So we got into this thing. We happen to be, let's see, there we go.
We're going to give 3 papers today. I'm going to give the first one, and so I'm going to try to rush through this as fast as I can, try to get through the introduction and my part in about 15 minutes. We're very fortunate in that we've been given this incredible gift, the Paul Plishner Radio Astronomy and Science, Space Sciences Center. And that happens to have a very large dish on it. We have this, here's some old pictures from 1972 when this thing was operational. That's a 500-foot tower there that was used for some VHF work. That's gone now, but the dish is still there, and it's a 60-foot dish that was built back in, starting about 1955, and it was operational from sometime between 1955 and 1974 when it was decommissioned. This was used for all kinds of things. One of the biggest ones was troposcatic radio communication. What they were trying to do was get long-distance communication that was reliable for a high data rate. And so they had some very large transmitters in the system, and they were running that. And I think with the internet, with fiber optics, and with satellites, the interest in that sort of communication for government usage fell off. And so it was decommissioned back in 1974. I guess the other thing I should say about this is there's 2 additional dishes in Boulder, on Table Mountain in Boulder, that are on the National Science Institute site that the organization originally ran those dishes for a while on Table Mountain. But the trouble with Table Mountain is there's a lot of experiments there, and the organization didn't want them up there doing whatever they were doing. So they kind of got them kicked out of that, and we came across this here in Paul Plishner, who was a pioneer in microwave radio and an entrepreneur. He had a large company that was doing microwave transponders, microwave communication systems. He actually bought this, and I don't remember when he bought it, but couldn't really do anything with it. And the reason he couldn't do anything with it was it didn't have any power at the time. The power was taken out. Let's go this way. This is an amazing thing. It's kind of like if you're a kid and you think about, the evil scientist, and you want this really cool facility out in the middle of nowhere. That's what this is. We have a bunker. This happens to be one of our main guys, Ray Ubrecken, who's the primary radio guy in the group. He's standing in front of a large pile of tumbleweeds in there. And so every time we go down to this site, usually we have to clear those tumbleweeds out to get to the door. And then behind that door, we've got a bunker. There's about probably about 1,500 square foot bunker down there that's about 15 feet underground. It has a cistern, a bathroom, a little kitchen, a lab, a large service area that we can use to have meetings in and build stuff in. And so we've got quite a bit of capability in our bunker. This is our communication trailer. This was originally part of a trailer with NIST, and it was, I guess it was given to the group up in Boulder, and they transported it down. That's where we have all our radio gear. It's right next to the dish, and we also have all of our ham radio gear in there, and our solar system for the dish. The little shack over there is a generator shack. We've got a 25 kilowatt propane generator that generates power for when we're on site, so we can do anything with it. We can weld, we can run power tools, we can run the dish. And then there's the dish there. Antenna specifications are shown here, up to 2 gigahertz at 60 feet, about 42.5 dpi at a gigahertz. We think the beam width is about 2.6 degrees at 400 megahertz and 0.8 degrees at 1.2 gigahertz. So for you guys that have optical telescopes and you have aperture fever, this is like aperture fever for radio telescopes for most amateurs, right? This is something that was just finished. There's Ray Ubrecken built this tri-band feed antenna, and it runs 144, 432, and 1296 megahertz, and it's also designed for hydrogen lines. So we have this, we just got this installed and just got this operational about 3 weeks ago. And then this is our club station. K0PRT is the club station call, and that's our QSO card. And then there's some of the inside of the communication trailer. So I'm going to talk a little bit, since I'm the rookie in radio astronomy. The guy said, well, you need to contribute something. And they said, you know, we need this power, and we'd like to run all of our computers and all of our experiments off solar power. And I said, well, I know a little bit about solar power. I worked at Lockheed Martin years ago and did some solar stuff, and I can probably do some solar analysis and figure out what we got. And so they said, yeah, why don't you go do that? So we thought about it, and we said, well, we've already got some solar panels people have given us, and we put them on the communication trailer, and what can we really do with it? So here's our system criteria. We're off-grid most of the time. We've got the generator when we're on site, but we want to be able to do some experiments and get the data back when we're not there. This site is about 100 miles from Colorado Springs. The nearest town is 5 miles away, Haswell, Colorado. There is no power. The power was used to be, there was a 400 amp 3-phase line that came into this for the massive transmitters that they had for the original site. That was all torn out by the farmer who owned the property around it, so he didn't have to plow around the power poles. So there's no power. It's going to cost us around $35,000 to $40,000 to bring power in off the REA to run the site. So we decided, well, what can we do with solar so we can run it when we're not there, and the rest of the time we'll run the generator when we are there. We've got a 1,000-gallon propane tank, and so it's no problem when we're there, but when we're not, we want to be able to do this. So what do we want to run with it? Well, we got remote computers between about 75 and 500 watts. Rich wanted me to put in a bank of servers, and I said, well, each server is going to be about a kilowatt, and if we put a whole bank of them in there, you know, that's tens of kilowatts of power that we'd have to have. So that's probably out of the question, but we could run some, you know, some computers with the thing. We got the experimental electronics, the Radio Jove, some of our receivers. They're fairly low power. The system parameter telemetry, we'd like to have a Puck or a Arduino or a Raspberry Pi collecting the data off the solar systems, collecting the data off our batteries, and be able to send that up with telemetry so we can read it afar. Also the GPRS and Edge to Wi-Fi connection for our computers. We want to drop the Wi-Fi part of that eventually and have a direct plug, just go direct to the GPRS that's local, so we get our data back over the AT&T cell system. The other criteria is we want to run through 2 days with no sun, okay? And so we got to have enough batteries to do that, and then we have to have enough solar panels to charge those batteries back up in 1 day of full sun. And so if we just set that as our criteria and say if we could do that, most of the time we'll be online in Colorado. We're pretty sunny. Not quite as much as New Mexico, but pretty sunny. So that means we have to work this backwards. Most of the time when you design a solar system, you know what your loads are, and you can go out on the internet and find programs all day that'll say, okay, if I want to run a 300-watt load, what do I have to have for batteries? What do I have to have for solar panels? But here's a case where we had the solar panels. People have been giving us solar panels. Everybody who's worked on the site has contributed a solar panel or some batteries or something. So we've got all this stuff laying around. We wanted to use it before we invested any more money. And of course, we're an amateur organization. We really don't have any money to invest in a full solar system. So we said, well, what can we do with what we have? It is what it is. And so what we need to do is determine the capacity of that system that we already have. So this is it. So for our main computer solar system, we've got these 3 panels. There's, I don't know how this thing works. There it is. Got number 1, number 2, number 3 there. This other one is driving some batteries in this little shack right here, and it's separate. We're just starting to use that for our SpectraCyber and our hydrogen line drift scan. So we're going to have a separate panel there. But for this presentation, I'm just concentrating on Solar System 1, which is those 3 panels. So to refresh you a little bit, I don't know how many people have solar experience in here on how it works. Quite a few, I would expect, in this group. But basically, you have a VI curve where you got V along the x-axis, I along the y-axis, and it makes this kind of a curve where the voltage is fairly stable here, and then it drops off, and current's pretty stable here, drops off in the voltage, and there's a peak power point up here, and if you plot the power on the other axes, you can actually get this power hyperbola here. The solar panel or solar cell model that we typically use is this model here, and if you put that into the right mathematical model, you can actually use that to calculate exactly where you are on this solar curve. And I used to do that when I was with Martin, where we built a whole solar program. This is back a long time ago before we had all the new stuff. But we built a whole solar program based on this model, and we dumped the climatic atlas tapes into that. And then we could simulate what an array would do in a particular location. Now, we're kind of lucky today because NASA went out and did this for us. And they've got a database online at the NASA site where they have pretty much every area on the planet down to about 1 kilometer in resolution in a 2-hour resolution of time, the solar data integrated so that we can use it, and I'll show you that in a minute. But generally in a solar panel or a solar cell, you've got at 1,000 watts per meter squared, which is basically our standard on the surface of the Earth. So incident to the sun, you got about 1,000 watts of power falling in a square meter, okay? If you tip that over and you lay it down on the ground, you have less because there's an angle there. So you might have 1,000 watts over a larger area depending on the time of year. If we have only 500 watts, say it's a little hazy, then the current directly falls off, okay? So let me show you some more. So we can take that model and we can put cells in series, and as we put them in series, we increase the voltage. We put them in parallel and we increase the current. So it's just like batteries, so you can build up most power systems this way. So our first challenge was, okay, we've got these 3 panels, what can we do with those? And we have to characterize them first. So we were out there one day and we didn't have any test equipment. I had a small space heater and a little heater out of a water heater, a small water heater, and we had about, I think, 4 different loads. And we said, well, let's just characterize these panels while we're here and find out what we've got. Remember, we're 100 miles from home, and every time we go down there, we got a 2.5-hour trip. So I said, okay, let's just characterize them. So if you see the points along these are the actual points that I was able to measure. And I just used Excel and curve fit these curves. But panel 1 looks pretty good. So we've got about 30 volts of open circuit voltage, about 8.5 amps of short circuit current. Its power level, we've got about 125, 140 watts of power from that panel at full sun. And of course, I'm making some estimates here because I didn't have a radiometer to measure the sun intensity, but it was a bright day and we've got the panels just almost perfectly 90 degrees to the sun. And so I like this panel. This panel here is same size, but these are old panels. All these panels are old, and we don't know how old they are, but this one looks funny. And in fact, it has this inflection here, and its output isn't very high. The power of this panel for the same size is only about 80 watts. And this area here makes me suspicious of this panel, so we probably ought to replace that one. And then the other curve here, this is actually the panel that's on the ground, and it has a much steeper slope for one thing, and its power output though is pretty good because it's a new panel. Somebody just donated this about 175 watts here. We had this hooked up wrong to begin with, and that's this other curve over here. It was hooked up as a 12 volt panel. Some of these panels are configurable. You can change the series parallel combination with the diodes in the back. And so it was hooked up the wrong way, and so when we married this with these two 24 volt panels, we had a current loop, and there was just current flowing in this panel. And so we didn't want that, so we hooked it up the other way, made this a 24 volt panel too, and now we can parallel all these together. There are diode isolators in most of these where you don't get backfeed. So a little bit about the definitions. This is important because if you know what the peak power output of these panels is, then you can take the NASA data and you can figure out, well, what's my power for my location? So most of these panels are rated on a standard test condition of irradiance of 1,000 watts per meter squared, okay, with a solar spectrum of the air mass index of 1.5 at 25C. So that's kind of important. I specified the air mass index there, and then the other electrical characteristics: open circuit voltage, short circuit current, and the peak watts. So the important thing is that all panels, if they rate a panel, you buy it, it's a 200 watt panel, it's rated at this 1,000 watts per square meter direct incidence, okay? So then I can take that and I can go to this website, the NASA Atmospheric Sciences Resource Center, and they have data. You just put in your lat long and you'll get the data for your site. And so what you'll get is a monthly average direct, monthly average direct normal radiation, kilowatts per meter squared per day. This one happens to be for all of Colorado. And I do have the data for our actual site, and I didn't plug it into the model since we did this original presentation. So for best winter tilt angle, and that's where we're set. I looked at the winter tilt angle and I said, we've got to set it for that. These are the numbers. So in January I get a 4.58. So what that really is 4.58 kilowatts, it'd be kilowatt hours per day, okay? And then our worst case is over here in December, 4.47. And then the summer tilt angle, better position, it's lower in the, it would be lower in the winter if I set the panels to these tilt angles. It'd be lower in the winter, but higher in the summer. But our worst case is the winter, so that's the one we want to stick with. So then we take that data and we plug it into our panel outputs that we measure, okay? So then I can calculate the power from each panel here in this table, and we can add those all up and take the worst case one, which is December, which is 1766. So what that tells us is I've got 1,766 watt hours per day in December, okay, from the 3 panels that I get. That's all you get, 1,766 watt hours a day. So then I said, okay, you got that, and then we've got the loss. And so for this is all hooked up with number 10 wire. And I said, well, maybe we're getting too much loss from the wire, so what does that really come out? So when I plug that into the system, a number 10 wire and its resistance and the round trip, we end up with about this 51 watts of loss in our total instantaneous output of 395 watts. So that's pretty significant. And then the other piece is the PWM solar controller. There's 2 kinds of solar controllers in common use. There's PWM and there's maximum power point tracking, or PPT, sometimes they call it.
And the one is much more efficient than the other. The maximum power point tracking actually converts the power at the maximum power point of the array. It watches for it, it dithers back and forth and finds that maximum power point, and then it actually does a DC-DC converter that converts the power at a high frequency to the power you need for the battery. And that's much more efficient than a PWM, which is nothing more than a switch. It's a transistor switch that turns the array on and off. Whoops. I've got to go all the way back. Can you get used to this?
Hit the wrong button.
Are you planning on using just 2 of the panels or all 3?
No, I'm using all 3 right now. That 325 watts is all 3.
About dust on the panels?
Yes.
Yeah, we've got a problem out there with birds. We have a lot of hawks in the area, and they love to sit on these panels. And you know what they do when they sit on panels, right? And so when I took this data, in fact, I'll show you here. The first data is before I clean the panels. These are all 2 data sets. First data is before I clean the panels, and the second data is after I clean the panels. So it's surprising that with all of that mess from the birds on those panels, it really didn't affect them that much. You can see the difference there. And of course, there is some difference in time here. So the day was moving. So let's see. So I started talking about the peak power tracker and the PWM. The PWM is just a switch that switches in the panel to the battery voltage. So every time it switches in, it drops the panel voltage along the curve down to the battery voltage. When it's off, there's no power transfer. And so it's fairly inefficient. So I use 75%, but it's different for every point that it checks on that panel. But the overall efficiency with the wire loss and the PWM is 65%. One of the things I didn't include in this was the battery efficiency. Let me move on here. So we've got the batteries. The batteries are they're a railroad use battery. So it's an industrial battery. It's a gelled battery in a special case. Doesn't look anything like a car battery. Those have a capacity of 264 ampere hours per cell, and we put 6 cells in the string to get our 12 volts, and then we have 2 strings. Well, these batteries are 20 years old, and so just guessing, I said, okay, let's just take them to half their capacity because they're over their lifetime, and so that only gives me about what was it? So the total new capacity 528 ampere hours, and so I just said it's 264 ampere hours. Now what we have to do to make this better is go characterize those batteries. So then if I take the battery capacity and I divide it into our load, so say we have a laptop and an experiment load of 75 watts. I can run under a full charge at that 274 or 264 for about 48 hours. For a full desktop computer, 150 watts, only about 24 hours. So that says our battery capacity for a laptop just about meets our criteria, right? 2 days. But for a desktop, it wouldn't. So then, if I take my 1765 winter ampere hours, okay, or watt hours, excuse me, and the efficiency, and that ends up with 1152, and then I have my 3-day criteria in there. That drops that to 384, and then I get, what can I do? Well, I can do 16 watts, 24 hours a day with my original criteria, with those batteries, or with that solar panel, okay? That's not very good, because I really need 75 watts, just minimum, to get started, right? So that says that I'm about considerably undersized. And I've got to replenish those batteries, so we're kind of in a bad spot there. So even with 3 panels, we can't do what we want to do. So the conclusion is, I need about 3 times as much solar capacity as I have, and I'm about right on the batteries for a 75-watt laptop. But if I want to go up in size, if I want to go to a desktop, I got to have more batteries by that ratio, and I've got to go up on the solar too. So I might have to have 9 times the solar capacity to drive a desktop. So that'd be, instead of 3 panels that are this kind of efficiency, I'd need 9, or I'd need 9 times. 20,
About 6 good,
7,
6
yeah.
good solar cells.
Yeah. So some of the caveats are that we don't know the battery capacity. We got to figure that out. We got to, if we use new solar panels, they could all be 200-watt solar panels, and we'd get a lot more out of it. And we could use a more efficient maximum peak power packing controller, power tracking controller, and we could use a larger wire size and not have as much loss. So we'd have more for our loads. So future work is do a better job of characterizing the solar panels, do a better job of characterizing the batteries, and use a solar flux instrument to make sure that we're measuring at full solar flux so that we know exactly where we are. To measure is to know, right? And then characterize the batteries with loads, and then use the NASA data for our actual location rather than all of Colorado, and that's about it. So our goal in this is to come out with understanding what we can do and then what we have to add to get what we really want. I'm going to answer like 2 questions. I'm going to turn it over to these guys and we can catch it all later.
You've got power coming in from the panels while you're working, plus the battery power. Did you consider you've got all that incoming power? When you don't save it to the battery, you can use it very effectively.
That's true. Well, what we're not using coming in from the panels is charging the batteries on the controller, right? So during the day when we're online with the computer, we're powering the computer and the batteries.
Yeah, but you've got all that power coming in from your panels during the day, so that helps a lot. I don't know if you put that in your calculation. That plus the stored battery power.
Right, right.
The other thing, I have it connected to the panels. I have the panels, and I've got a maximum power point unit. And I'm thinking about this thing. It's connected to a 50-foot antenna going up to the panels. I'm wondering if it's going to radiate much. Do you know what the RF noise generation is?
Well, that's one of the problems with any of these controllers because they're all switching controllers.
Yes, right.
And even if it's a PWM, we're going to have that problem. So if you're in a quiet time where you want to make an observation, you're pretty much going to have to turn this off and just run off of batteries.
How can you move the batteries closer so that cuts down on your line loss?
Well, we did move the batteries closer, but we still have the panels on the roof and the panels outside, so all that line loss is on the panels. I'm going to turn it back over to the rest of my crew for the other presentations. I'm running way over, and I know it's late in the day, so we'll get that done. And then if you have any more questions, we'll pick them up at dinner.
Okay. No. Oh, you going the right way?
Yeah, you're on the right way.
To start over again?
No, you're going the right way.
Oh, going the right way, okay. Well, as you can, I'm Dave Moulter. My normal job is I work on the GEOD system on big telescopes. They're 3-foot optical telescopes. And I've been working on there for about 16 years. And part of the thing I do is I'm making it move. So as soon as I got to a ham radio meeting and these guys found out that I actually know how to make big things move, I became their best friend. As you can see, we do have the dish. It moves back and forth. Right now, we only use it have a hand paddle to make it manually move. When we're down there, the hand paddle is on like a 100-foot cord, and so we can stand outside and look at it. We also have inside the trailer, there's a control panel that we can use. You always saw about that stuff. So inside the trailer, we do have this, there's a couple switches up there, and that's where we can go ahead and use it as a you can be inside tracking stuff a little bit. They're not really tracking, but we can see where the dish is moving. The problem is that we didn't have any way to know exactly where it needs to go. So what they did was they had, when I got there, there was already two 12-bit absolute encoders. One sitting on azimuth, one sitting on the elevation, and it just sat there. So what I did is I went and came up with this circuit, and I had been working with these data acquisition units previously, and that's the only reason I picked them. If anybody's curious about did I do a real big search for any? No, I already worked with them and I knew they'd work. Come in here through signal conditioning. So you come in, you 12 discrete bits, and that's 4096. If you think of 360 degrees, that gets it down to about 0.83 degrees of resolution per bit. So they come out, they have a open collector, so the line is either open or grounded. Computers don't like that. So I put in these pull-up resistors. That's what the signal conditioning board is. And as long as I got it doing pull-up resistors, I just put a LED in line, and that goes and also lets me know what the logic is, inverse logic. It goes into the data acquisition board, comes out of the data acquisition board as RS-232. The cable we have takes both those in to a single USB port. We put that into a Raspberry Pi, and then on top of the Raspberry Pi we have a small 2-line display, and that'll go and give us the ASL. And then that goes across Ethernet. It goes down to our display computer that's going to be down inside the trailer. So this is what one of the encoders looks like. And over in the side, I've actually got the box over there. Some people looked at it already. We didn't have it up there, still working on it in my house, so I just brought it down to let you see what it looks like.
Don't break it.
Yeah, that's, and we're on such a shoestring budget, I paid for everything in the box except for the encoder. So I have the spare encoder laying out there. There's one sitting out there. It's an absolute encoder. If anybody knows anything about encoders, you have absolute encoders. You also have incremental encoders. We use an absolute encoder on big antennas because you don't, with a incremental encoder, you would have to bring the antenna all the way down to a known position, which is usually at the bottom or the top end, or you'd have to rotate it around to figure out where it is. And then once it's turned on, it can continually tell you where it's at. An absolute encoder, as soon as you power it up, you know exactly where it's at. Because it's such a big antenna, we got a lot of gear ratio there. It takes us about 10 minutes to go from zenith all the way down to horizontal. So a lot of metal up there. So this is just a hacked together set of inverse logic LEDs up there. I built 2 of them. One's azimuth, one's elevation. Too far. And this is our digital acquisition unit. It's got 16 channels coming in the side. They can be either inputs or outputs for digital. We've got 8 analog channels out here, plus there's 3 analog outputs there. And then this comes out as standard RS-232. Down here we've got a Raspberry Pi, and the only thing we modified here was a piece of electrical tape. This is a little kit that they sell, Adafruit. Anybody's doing Raspberry Pis, you all know about Adafruit. Little board, you throw it together, it takes about an hour and a half to solder the thing up. And the tape's there because this guy will sit right up on top, and it gets shorted out by the USB ports on the back. And then it just got a power supply, run plus or minus 12 volts, and that's so I can future things. The Raspberry Pi runs off 5 volts, the encoder runs off 12 volts, the DAC runs off anywhere from 7 to 15. I'm powering it up with 12. And then I have also negative 12 volts because I won't have to have a differential op amp on there. But that'll be later on the thing. This is what our controller box looks like. It's a nasty looking rat's nest there. But it works. We've got your elevation over there, and because we had the, we can't go out and pay a bunch of people to come in and redesign this stuff for us. They're using the actual the original synchronous AC motor. And so we have a VFD over here on the right for elevation. They replaced the synchronous AC motor for the azimuth with a DC motor, and that's why we've got a motor controller over here. You've got a plus or minus 15 volt power supply down here. There's relays down in the bottom for lifting the brakes. And someday we'll get around to rewiring it and make it pretty, but right now it works. And then the other guy, Glenn, was going to be here. He couldn't get down here. I don't know anything about software. I know hardware. So I enlisted him to go in. He was the guy that, a company I worked for, Northrop Grumman, and he'd gone and been working with these DACs before on this other project we did. So I'm just going to mainly just let you know, we hear some of the highlights of it. Return of value between 0 and 4,095. DCS is the digital control system. He went and wrote a GUI that displays out on a laptop. What we want to do is ultimately have that sitting on our one laptop. Anytime we're running this, though, we're not really concerned with power because we've got a 25 kW generator. We don't run the mount anytime when nobody's there. So there's always somebody to keep an eye on the thing. So this is the display that I showed you there. And that's just for when you're up there locally and you want to go ahead and store the, stow the antenna in a baseline configuration. That way you can just have your local ASL display. So this is kind of the same thing. Because down here is dish control software. I apologize, it said digital control software. And so this going out to the GUI display, this is the Ethernet. There's the two pieces, they're sitting inside the box. And so one of the first things he did is, because he didn't want to have me going, and we're trying to work at the same time, he took the DAC out for a couple of weeks and he built a simulation. That way he can be sitting there writing software at his house when I'm sitting there wiring stuff up in the box. So this is the different parts of the software that he designed. So you guys are software people, you're just loving this, I'm sure. It's not going. Oh, go back one more. This is just his different threads that he goes through the GUI, and that's just the different portions of the software. It's modular software, so he could go and change to smaller things around.
Can Sarah give him a special award for using Java?
Sure, sure.
He'll take it. Yeah.
The laptop runs on Linux Mint, so get started on that.
Special award.
Oh, okay, cool, cool. But no, Glenn's a guy. He really believes in open source. The stuff that he's got to work with, he's got to work with some COBOL. He works with Ada. They have a lot of proprietary stuff. C, C++, Java Beans, Java. He works in some Python, and just I don't know. It's all Greek to me. I had to take one software class, and I went and passed it, but it wasn't that great. So here's what our LCD display looks like. There's just nothing to it. But you also see that he's going to take in time, and so he can go and we have RA DEC, but he's also going to be able to be pulling in so he can be sitting there, well, that's what RA deck is. So you mix as L with time, and then you can get your RA deck out. And using RA deck, that's where you can go and track. And that's where we're ultimately going to be is maybe in a year, have it all up and tracking. So you can sit there and put it into a manual mode in the software and just use, take your mouse over the top of the button and click on it, and you could just incrementally bring it up if you want. So let's see, what's this? Okay, the comm trailer. One of the biggest problems we had was we're trying to run the from the Raspberry Pi down the tower underground and over into the trailer. We're running about 150 feet, something like that. It runs right next to some power lines, and so we're having some issues with that, but I think we've got a solution. We're going to have a couple switches along the way, so we'll go reformat the signal. One of the things we did with the VFD up there, it goes and puts out a lot of RFI. So I just got finished putting that, was in a plastic box. We thought, oh, now I'm putting it in a metal box, and I'm going to have it all grounded and everything, so it shouldn't have as much RFI effect in it. So this is part of his testing, what he went through. So once we did we don't really have any way to bore sight this antenna. So we sat there and said, okay, what looks like it's orthogonal to the beam? So we found a piece of metal up there, stuck a level on it, and started tweaking it back and forth until we figured it was pointed at 90. Said, yes, this is 90. Went ahead and pulled the dish down until that same bar was sitting vertically. And we said, okay, that's 0. Now we started going back and forth a couple times, and all he does is he looks at his counts. Back in the old days, we had to go and take a synchro, and you had to null a synchro and loosen up the shaft on it and make sure it's all nulled and everything. But now with the computers, you just go and tell it that number is at 0, and this other number is at 90, and just go with it. Same thing goes, but what we did was we took found that a place that looked like it was one beam, and we went out and used Google Earth, and we came up with different bearings to different locations. There's a big grain elevator in Haswell. There's some corner of some guy's barn that's 3 miles away. There was a cell phone tower that was a couple miles away. We knew what those bearings were, so what we did was we just went and jogged the antenna around until we said it was lined up. Glenn reads off what number the count is off of the encoder, and then he went ahead and converted those back, and he found out they're within about 1/4 of a degree of being correct. And it's over to Rich. So if you got the box over there, I'll be around afterwards. Anybody wants to talk about it? I'm just going to go ahead and let them push on through.
I'm glad Whit gave his speech first, because I wanted to use all his stuff and redo this. But my experience is doing production runs, and part of that is to do the Six Sigma, statistical process control. So every time you do something, you can repeat the process and reduce the variability in your production runs. So I said, but based on doing that, you need control charts and things like that. And what does a control chart look like? It looks like just the runs we come out with on SkyPipe. It looks exactly the same. So I said, well, why don't I try doing that? Because one of our things we're going to have to do is we got a lot of prototyping going on at the site. And how do I know that prototype's better than the prototype we had or we didn't have? How we show that we're going to continuously improve when we put new stuff on, or that we actually make it worse. So this is a process. The whole thing's I sort of prototyped an approach so that we can every time we change something, we can identify that we've reduced the variability, and we've improved the system, no matter what we're trying to measure. So view it that way, that, okay, so statistical process control, what you're looking at is that you want to make process stability, going to improve the capability by the reduction of variability. Okay, so Whit was talking about using standard deviation and not using it for the RF stuff. I use standard deviation mostly for this. I might shift to his approach here, the next variant. I don't know if you can tell right here, but what I did is my prototype was a UHF 13 beam antenna. I had a small preamp, mass mounted preamp. I have a TS2000, which I went to an audio box, audio to USB converter, and then I went to my computer with SkyPipe on it. That's my prototype project. Simulating this thing, we've got our feed at the Plishner, which would be this, which has preamps in it, and we would have our receivers, and then we'd have basically SkyPipe, almost the exact same setup after the antenna. So this would allow me to come up with the processes and the approach. And I want you to notice all the trees here, nice pine trees. They suck up a lot of stuff. So I'll show you some of that stuff at the end of the thing. So this is what a run chart is fundamentally time over signal level. So this is just an example of a run chart. Looks very familiar with what we do now, right? We suck up this kind of signal we get out of our radio telescope. So I just want to show you that's exactly the kind of stuff they use for statistical process control. They could have production runs versus variability, but it looks just like that. Okay, so how does this work? I take my data, I come up with a mean, and then I have, you take the statistical standard deviation for that, you add that to the mean and subtract that from the mean. Now you've got basically your upper control limit and lower control limit. So doing nothing, assuming that that's the way that the production run works, what will happen is that when you do a measurement, everything should be in that. If it's running normally, if your control processes are correct. If it goes any above or below that, your control processes have somehow changed. So from our viewpoint is, if we got this thing working perfectly as we're doing radio astronomy work, what's the thing that will cause us to change would be actual source hit us, and then that will cause us to go above the upper control limit. So one of these things is, if it goes above the upper control limit, I might have an actual source that's causing, or an interference or something that's, but it's not Gaussian steady state. So, from this, by the way, just examples. If I make an improvement, so say right here in time, I made a process change. I improved my amplifier. I cooled the amplifier. I steady stated something, and I caused the variability to go down. I would actually then change my upper control limits. It may change the mean, but it also changed the upper and lower control limits. So that becomes the new standard. Now I know I've improved the system. So this is how so the approach here is, every time we're going to do some baseline measurements of all the equipment down there, using like SkyPipe to take our data, come up with our baseline, and every time we change something, we're going to redo it, and hopefully I'm coming lower in variability. Otherwise I know that I messed it up and I need to go fix that. That's sort of the goal. And I can keep track of that and quantify it. Okay, some of the control chart limits. So this is a control chart, and you notice the number, and I don't have as many data points here, but you got a lot of data points in between these control limits, upper and lower control limits, and you got a mean, okay? So if one or more of those control limits are outside the control, more points are outside the control limits, I have a problem. I have to consider, these are issues that, if any of these happen, you have to consider I'm not in control anymore. There's something going on. 4 or 5 consecutive points on one side of the mean, right? So now it's trending up, it should be almost random between the two. But if I start getting a trend between the mean and one of the control limits, I'm now out of control. A run of 8 consecutive points on one side of the center line, 6 points in a row, steadily increasing and decreasing, an unusual or non-random pattern in the data. So I can look at that thing and I say, this is not random. I should be getting almost a steady state between the two. Okay, so let's make the assumption. My prototype was really trying to receive background noise, and I had a 50 ohm resistor on the end of it. So I took the antenna out, put a 50 ohm resistor, so I'm not trying to get signal in. I'm just trying to put the 50 ohm resistor on the outside, right before the preamp, the mass mounted preamp. Okay, so my first run, I've got a 50 ohm resistor on there, and I'm getting this. Okay, so what does that give me? That tells me that this is actually the mean of all the data. Here's the first standard deviation above that, standard deviation below. So even though it's in control of all the data, I am getting data out of control limits. All right, so that was my first, and I've seen this on the data before, but I didn't really know how I can deal with it. So, so the next thing you do is you do a cause and effect diagram. This is usually called a fishbone diagram. So what you do here is to say, hey, here's my defect, and here are all the different methods, materials, machines, measurement, personnel, and then what you do is you list off all the you do brainstorming, list off all the possible things that could cause that error to happen. So now you're tracking it. And then the next thing you're going to do is figure out, let's go change something based on methods or personnel or measurement. You know, let's change something, and then you go do another run and you measure your control limits and see if you changed it properly and by how much. Sometimes there's a combination, so this really helps you to deal with combinations of issues. So this is an important feature on that. That allows you to get the engineering team together and brainstorm, come up with this picture. So here, based on that picture, I had receiver overheating, manual temperature measurements, and I had a sunrise sunset issue. So here I'm looking at, these are my 3 thoughts. Here's the corrective actions that I came up with that I could add to that as a process change. So add external fan, add weather station. So maybe I'm not measuring temperature right, and add more steps in the procedure to add this documentation. So this is my first cut. So realize what I'm doing here. I'm just coming up with, this is now a process, and I'm trying to come up with the whole process to do it. I'm using this as an example. Okay, so what did I do? I found out that my TS2000, every time one of these blips came down, the internal fans were starting, and it caused a power drop in the preamp, which caused that dip to happen. And as soon as it hit that point, the fan went off, and it took a little time to go back up to normal. So my TS2000, so your internal fans you're using, this is what's happening to the outputs when the fan goes on, at least in my TS2000. So I found that. So what I do is I put an external fan on top of the TS2000, and then I got this. So what happened from a standard deviation, I was doing 74, plus or minus 74 points above and below the mean. As soon as I made the correction, I now only have 24. So I've improved the variability by that amount, and I could document it. Okay. So that's my process chain right there, and then there's my new data run. So this showed that I can use this approach to document this stuff on that. The next thing I had is now I'm running this thing and realized that I've got a 50 ohm resistor outside with a mass mounted preamp, and then I had this just happened that night, is it went from 55 degrees down to 28 degrees, and I'm monitoring this thing, and all of a sudden, whoosh, my data goes like that. What does that mean? That means that now my standard deviation went up to 86. This is after I had the fan on. So now it did even worse because of this temperature decrease. And I was noting the temperature at the time because I hadn't corrected for that. So at this point here, my thought was, I'm just gonna model that temperature decrease, and I'm gonna add it back in, because if I can model the temperature, I can add it back in. And so my corrective action was to take that and manually in Excel model it back in, which gave me from 86 down to 16 variability again. All right, just simply by adding it back in to correct for the temperature variation in Excel. So that's another approach where, I don't know how legal that is, but that worked fine there, and that gave me a lower variability. And so now if I had something pop up here, I would be able to see a real signal in there instead of a temperature variation. Okay, so but that shows you how your corrective actions can improve that variability. Now I know that was a better answer there. Last thing I did, just to show you, is I did I hooked the antenna back up, and I went. The biggest question I was having is, what if I'm sitting on the meridian and I'm taking data, snapshots of data up and down from 90 south to 90 north in 10-degree increments. What is now that I've got all these corrections happening, what is my background, so that I can see if I'm aiming down, how much variability is my data based on taking like 10 minutes at each of these data points. And here you can see that south, looking straight south, I've got a lot of variability here between 0 and 20 degrees, ground temperature, trees, whatever. I got a nice little clean path right here with little variability. So you see my standard deviations here. I got 374 to 214. And then all of a sudden I get a little cleaner with the closest at 50 degrees. And then for some reason at 80 degrees, I get to jump to 492 again. All right, and then at the end, let's see, where did I jump up here? Oh, I'm sorry. Yeah, I was actually pretty good at the northern side. I thought I would go get ground temperature again. And then I just, if I plugged the 50 ohm resistor in at the end, I had a high point, but I had a little variability. Okay, so this is the actual signal levels here, and the variabilities here. So you can sort of see if I don't want to take measurements at these points because I have high variability and I may not see a low signal there. And if I did, I would have a lot of variability at these. And this is another picture just with the standard deviation plotted. I'd have a lot of variability at these angles looking at that. So you can see if I wanted to take something right now, I'd be taking it at these angles. Okay, so lessons learned, that statistical process control is possible doing this. You have more ways to gather statistics. That would be better. That's what I'm saying. I was I loved Whit's thing because I'd be using some of his statistical stuff. But then you add that with your cause and effect diagrams and your all your process changes, and you can actually document, quantify how well you're getting over time. So you can get down that you have minimal variability. You can pick up those sources very well. Here I found that the signal spikes here, temperature, external temperature variation is significant, and elevation angles are significant. That was just on my little prototype. Now we're going to apply the whole process of doing this to the big dish, and so now when everybody comes in, they're going to have to do that measurement. We're going to keep those. And every time we change something, we're going to be able to say, hey, that improved or did not improve the science, the accuracy of the system. Okay, we have the best photographers, by the way, on our team. They have all sorts of pretty pictures, but we have a dsays.science website. We have dsays.org, which we inherited. Looks prettier, but it hasn't been updated since 2012. So go to the dsays.science. We're posting a lot of the stuff there. Any of you guys can join. And we accept, we do two meetings a month, a science and an engineering meeting. And we're always looking for, we take anybody who wants to sit there, and we got electricians, and we wired this place up. We got a couple astronomers, but not many. And, but we got a lot of people who just, are just happy to do this stuff. Very good group to play with. As I say, one of our meteor shower pictures of you guys. All right, yeah.
Where are your meetings, in the Springs or out of?
In the Colorado Springs. Yeah, we're out of, all of us in an hour out of Colorado Springs. We have a couple people in Longmont. We can Skype people in. We got a Canadian moonbounce guy who calls us. Now, we also, on this thing, we do tropospheric, moon bounce. Now we got this dish up, with this feed up. So tropospheric moon bounce and at 1296, 435, and 144. And then we have hydrogen lines set up. So we got a Spectre Cyber, we got a whole, we got our 2-wire dipole, Radio Jove, I got a Super SIDS, we got itty-bitty telescopes, we got all that stuff we use. So that whole radio observer program, we got all of, we're one of the few clubs that can actually do all of those radio observer programs, including the hydrogen line. So, and I got the gold, and so I sort of proved that we have all the stuff, all the right stuff for the, so if you want to go work on that, we've got all the equipment and we've already done it. And all the club members are all going to get that as their minimum qualification to run to do the site. They got to go and get the gold level. So that's sort of our goals. Any questions, any of us? Okay. Oh, yeah.
What was the cost on those little encoders? On the encoders?
Yeah.
Those encoders, they still make them, and they're about $450 a piece. You can get a lot cheaper ones.
I'll talk to you about that.
Okay. Yeah, I'll just stand over here. Anybody wants to talk about it?
Sure. All right, anything else? All right, hey, thank you very much.
All right. Thank you all for coming to the conference. I hope you all had a good time, and I hope you're all clear on how to get out to the array tomorrow, and all transportation issues are resolved. If any questions come up, please ask me now, or you can call me on my cell phone if you need to, I guess. And thanks again.
9:45. 9:45.
Yeah, be there at 9:45, definitely.
Don't, because it's going to start right at 10.
Yes.
So if you can be there, if you want to be a little early, I did find out that the Welcome Center opens at 8:30.
Yeah, right.
So, you know, get there a little early, you can go inside and check it out. So.
Can I say something really quick before you leave?
Oh, yes.
You're responsible for cleaning up.
Yeah, please
Yes,
have.
please help clean up
Look around
everything.
your seat.
Definitely.
Make sure you haven't left us. If there's a wrapper or a water bottle on the floor.
Last call for mouse pads.
Where's Bill? I need for some Sarah merchandise.
Coming.
No, I've already paid you. I need to pay Bill.
Hey, Gary?
That Bill? The can
Bill.
around
Bill. Hey, Gary? It's Gary. Take a picture, please.
Is that your mouse? Okay.
Watch how you handle it. Okay, so I've got, do you mind, William?
Oh, that's great.
Those
are really nice.
Wow, look at this.
Thank you.
That is gorgeous. Unfortunately, oh, excellent. Is it 1L?
1L, exactly.
Oh, I was so afraid.
Oh, no, you're perfect.
Okay, where is it? Okay, gentlemen.
I'll hold your thing up, Bill.
Okay.
That's absolutely gorgeous.
Okay, all right.
Couple pictures. More.
All right.
Okay.
Thank you. Thank you.
Took about
Oh, hey, Gary. I need one
you,
more.
Ken.
Wow.
I need one more.
That's gorgeous.
Wanted to, hey, Dave, can you come up here for a second, please? It was hard to help, so he's trying to move it.
One more award to give?
Yeah, one more award for Dave for help. He makes the Western Conference possible. I know a lot of people help.
Thank you very much.
Thank you all. Wow, clean up.
Hey Dave, whose picture is on it? Whose picture is on it?
Jansky.
Oh, good. Good. Nice. That's good. You guys still have a Rodney Howard. Great. How about the lady? The lady who's got it in California. Yeah, I think she was. She came to Sorrow. Like 10 years ago.